First of all, I would like to thank to organizing committee, especially Professor Ekrem Aydıner, to organize such a prestigious meeting. So first of all, I would like to start with the inviting director of Istanbul University, Professor Mahmut Ak, to give his speech. Please, could you give your talk, Professor Mahmut Ak? Thank you very much.
Değerli hocalarım, teşekkür ediyorum. Saygıdeğer konuşmacılar, değerli katılımcılar, 16. Fizik Sempozyumumuza hoş geldiniz. Bu fizik festivalinde dünyanın en seçkin fizikçilerini uzaktan da olsa üniversitemize görmekten mutluluk duyuyorum. Dünya fiziğine yön veren ve alanında çok önemli çalışmalar yapan seçkin fizikçilerin bir araya gelmesi fizik tarihinde yeni yerini alacak ve daima hatırlanacaktır. Burada yapılacak konuşmaların bir kitapta yayınlanacak olması da başyapıt olarak öğrencilerin okuma kitapları arasında yer alacağına yürekten inanıyorum. Ne yazık ki COVID-19 salgını nedeniyle toplantıyı fiziksel olarak gerçekleştiremedik. Fakat bu salgın döneminde bile bilimsel araştırmaların sürdürülmesi, bilimsel işbirliklerinin geliştirilmesi ve bilimsel ilerlemelerin takip edilmesi için sanal toplantılar bizler için bir fırsat oldu. Salgın döneminin geçmekte olduğunu ve yüz yüze buluşmaların gerçekleşmeye başladığını görmek de bizleri mutlu ediyor. Değerli konuklar, izin verirseniz mensubu olduğumuz üniversitemizden kısaca söz etmek isterim. İstanbul Üniversitesi sadece ülkemizin değil, aynı zamanda dünyanın sayılı üniversitelerinden birisidir. Üniversitemiz kuruluşu 1453 tarihine kadar gider. Esasında üniversitemiz Anadolu medeniyetlerinin köklerinden filizlenmiştir. İstanbul Üniversitesi 17 fakülte, 14 enstitü, 2 yüksekokul, 2 meslek yüksekokulu ve 733 diploma programıyla Türkiye'nin lider üniversitesi konumundadır. Üniversitemizde örgün eğitimde 60 binin üstünde, açık öğretim programlarında ise 580 binin üzerinde öğrenci eğitim almaya devam etmektedir. İstanbul Üniversitesi lisansüstü eğitim potansiyeliyle de Türkiye'nin yüksek öğretiminde ön plana çıkmaktadır. Üniversitemizde 351 yüksek lisans programında 10 binin üzerinde, 220 doktora programında ise 6 binin üzerinde öğrenci akademik çalışmalarına devam etmektedir. Üniversitemiz uluslararası öğrenci sayısı bakımından da Türkiye'de lider konumdaki üniversiteler arasında yerini korumaktadır. İstanbul Üniversitesi'nde halen 136 farklı ülkeden toplam 9390 uluslararası öğrenci öğrenimlerini sürdürmektedir. 2 Nobel ödüllü mezunata sahip tek Türk üniversitesi olan İstanbul Üniversitesi, 77 uygulama ve araştırma merkezi ve 145 araştırma laboratuvarıyla zengin bir araştırma altyapısına sahiptir. Üniversitemiz bünyesinde yer alan her bir araştırma birimi konusunda uzman ve araştırma niteliği ön plana çıkan akademisyenler tarafından yönetilmektedir. Öte yandan belirtmek isterim ki, uygarlıkların ve medeniyetlerin beşiği ve köprüsü olan ülkemiz ve güzide şehrimiz İstanbul bir tarih ve kültür hazinesidir. Sizleri gelecek sene yapılacak olan FFP17'ye davet etmekten ve İstanbul'da misafir etmekten üniversitemiz ve ülkemiz adına onur duyacağımızı bilmenizi isterim. Nobelliler toplantısı olarak bilinen bu önemli toplantıda bir araya gelen seçkin davetli konuşmacılara, toplantıyı organize eden üniversitemizin değerli öğretim üyesi Profesör Doktor Ekrem Aydıner'e, Uluslararası Düzenleme Komitesi'nde yer alan seçkin fizikçilere, toplantının yönetilmesinde önemli katkıları olacak seçkin fizikçilerden oluşan oturum başkanları ve moderatörlere şükranlarımı şahsım ve üniversitemiz ve ülkemiz adına sunmak isterim. Sizlere tekrar hoş geldiniz diyerek katılımlarınız için teşekkür ediyor, saygılarımı sunuyorum.
Thank you, sir. Thank you to Professor Mahmut Ak. Now we will translate his speech in English, please. We cannot hear you. Your microphone is mute.
Dear participants, dear distinguished invited speakers, I'm glad to welcome all of you to 60th Frontiers of Fundamental Physics Symposium. I am happy to see the world's most eminent physicists at this physics festival in this virtual platform via our university. I sincerely believe that gathering the most eminent physicists who guide the physics studies and give the significant contribution to their field will take its place in the history of physics and will be always remembered. I also believe that the book which will be published and include the speeches will be among the most important reference book of the students and researchers. Unfortunately, we cannot physically meet due to the COVID-19. Of course, this is not a serious obstacle for our meeting. The virtual meeting have been good opportunities for us to keep on scientific researches, develop the scientific collaborations, and follow the scientific progressions since the pandemic period. We are looking forward to days when the pandemic period will finish and we can physically meet again. Dear guests, let me briefly mention our university. Istanbul University is one of the world's oldest universities. The foundation of our university traces back to 1453. In fact, the roots of our university are based on Anatolian civilization. Our university continues its educational, research, entrepreneurship, innovation, and community activities with 17 faculties, 14 institutes, 2 colleges, and 2 vocational schools. Over 65,000 students in formal education and over 580,000 students in open education programs continue their education in our university. Istanbul University also becomes prominent with its postgraduate education potential in the higher education system of our country. Over 10,000 students in 351 semester program and over 6,000 students in 220 doctorate programs continue their studies at our university. 9,390 international students from 136 countries continue their educations in our university. Istanbul University is the only university in Turkey whose 2 graduates were awarded 2 Nobel Prizes. Our university has a rich research infrastructure with 77 research and application centers, 145 research laboratories. Each research unit within our university is directed by the academics whose expertise and research qualities are prominent. On the other hand, I would like to state that our country, which is the cradle and bridge of civilization, and our beautiful city, Istanbul, are the historical and cultural treasures. I am honored to invite you to FFP17 in the next year and host you in our beautiful city, Istanbul. On the behalf of me, our university and country, I would like to express my gratitude to the distinguished invited speaker for this important meeting. Our university's esteemed Professor Ekrem Aydıner, who organized the meeting, the distinguished physicists in the International Organizing Committee, the chairs and moderators who will significantly contribute to the management of the meeting. Welcome again and thank you for your participations. I wish you a successful and effective meetings.
Thank you very much again. So next, I would like to...
Rector's speech.
So thank you again. I would like to invite the Professor Ekrem Aydıner to give his opening talk.
Thank you, Mohammed. Dear guests, welcome to FFP, which is a great physics festival. I am happy to see you at this meeting. I would like to thank all eminent invited speakers to join this meeting, and I would like to International Organizing Committee chairs, moderator, and participant. We had planned this meeting 2 years ago, but because of pandemic, therefore, the pandemic period, therefore, we decided to organize this year online. You can follow this meeting on the Facebook and YouTube channels. And let me now, I would to give my short speech as opening talk. Therefore, I want to share my screen. Okay. My speech about the interaction between dark matter and dark matter and dark energy toward to a new physics. Sorry. As you know, the standard cosmology is general defined by the Big Bang model. Our universe is we assume that our universe is consist of matter and matter, which are fermions and bosons. Everybody knows that Big Bang theory has some important complications, such as singularity, emergence of galaxies, and time evolution of the universe. Therefore, it is impossible to obtain a complete cosmology theory without solving this problem. Another important question is that is the matter alone in the universe? Our answer, no, because we know that today our universe is consist of different components such as dark matter, dark energy, and atoms and radiation. To solve this complication, we need a new model, and 3 years ago, to solve this cosmological problem, I suggest a new model which is published in scientific reports. Okay. This model has potential to solve some important of the physical cosmology. My model suggests present dynamical evolution of the universe, covers the Big Bang and cyclic cosmology, and suggests continuous universe. On the other hand, this model can solve singularity, cosmic coincidence, big rip, big crash, and other problems. This model presents a realistic mechanism for emergence of the galaxies and can explain large-scale formation of the universe. At this point, we have two different questions. What are the dark matter and dark energy? We don't know these answers at the moment, but this question is fundamental problems for particle physics and cosmology. Other main question is that how do dark matter and dark energy interact? Really, we don't know answer also these questions. On the other hand, additionally, I want to introduce my second study briefly. This problem, late time transition problem, which is known late time inflation. This indicates that now we know that our universe accelerated expansion today. Actually, universe has different time evolution era. For example, as you know that there is different era. For example, radiation dominated era, matter dominated era, and dark energy dominated era. Late time transition is a transition which is transition from matter dominated era to dark energy dominated era. We consider dark energy, dark matter interaction model, and we analytically obtained a hybrid function in this study. This is it is the first time we obtain and we published this study results in APC. According to the model, scale factor, as you see that in equation 1, consists of hybrid form. First term is a power term, correspond to matter dominated era, and exponential term indicate that dark matter accelerated era. And we obtain analytically this hybrid scale factor first time, and we found, for example, some parameter alpha 2/3 exactly, and we show that this transition appear at TC 9.8 billion years approximately 3 or 4 billion ago, and obtain Hubble parameter precisely. And we study dark energy, dark matter function behaviors, and plot this behavior at figure. Finally, now we have two main questions. For example, what are the dark matter and dark energy? What are the physical mechanism of dark matter and dark energy? And other question, how do dark matter and dark energy interact? I believe that new physics may born from the answer of these questions. Thank you.
Thank you, Professor Ekrem Aydıner. Is there any question? We are opening for questions. So, if not, then I would like to ask a question about the. I'm just wondering what is in the inflation when we talk about the Big Bang after Big Bang. I'm wondering what is the reason why we have inflation. I mean, this is the explanation of how this universe evolved, but do we know the reason why there is an inflation?
I'm sorry, sorry. I didn't heard because.
So.
Yeah. Yes.
So is there in page 12 you show some king?
Yeah.
In the dark matter behavior, I think. Is there any physical meaning of that king?
Actually, we don't know. At least I don't know. I don't know physical origin, dark matter and dark energy. But some observational and experimental study indicates, and some theory indicates dark matter can interact matter, ordinary matter, and maybe in the future we can understand some physical origin, mechanism, and origin of the dark matter and dark energy. I am not sure, but interaction between dark matter and dark energy and matter may play important role to understand some physical problems, such, for example, in standard model and cosmology. Without obtain without solving solving this problem, we cannot complementary theory, particle physics and cosmology theory we cannot obtain.
Okay, thank you. So if there is no other question, then finally I would like to invite Professor Marisa Michelini to give her opening talk.
Oh, it's not an opening talk, it's just a welcome. Many
Okay.
thanks. Welcome to FFP16 Symposium, a great international event realized this year thanks to the wonderful work of Ekrem Aydıner of Istanbul University, Turkey, where we will probably meet next year. Let me thanks, in addition to Ekrem Aydıner, also the scientific committee of the symposium, with which I have worked very well in recent months. For over 2 decades, the International Symposium series FFP has attracted some of the greatest physicists in the world, as well as many other eminent physicists. The symposia has been held in India, in Italy, in Spain, in Canada, in Australia, and in France, many times for each country. The selected paper books of almost all the symposia paper in the series has been published by the University Press Orient Longman, Clunware Academic, Springer. You can see here the last one. Springer is Fundamental Physics and Physics Education Research, and also in the American Institute of Physics were published. The broad objective of the FFP series has been to enable scholars working in slightly different areas to meet on a single platform and exchange ideas. The areas covered have included astronomy, astrophysics, particle physics, theoretical physics, gravitational and cosmology, computational physics and related area, and physics education research. I consider a great honor to have founded the physics education research section during FFP9 in Udine 2008, and to be requested to maintain the responsibility in keeping this section rich, active, and high level up to now. I have to thank for this the broad and inclusive vision of Burra Siddharth, Douglas Oshelov, and more recently, Christian Corda and Fernando Quevedo of the International Center of Theoretical Physics in Trieste. The eminent physicists who have delivered the special lecture over the year, sometimes more than once, have included Nobel laureates and EUPAP ICP medals in physics education research. In the physics education research section of FFP16, we wanted to touch on 8 different perspectives of what is the content-related area, content research area of the physics education research. First is general, solved and unsolved problem in physics education research, a global vision. The second one is thematic, the entropy as the heart of the thermodynamics concepts. Then modern physics in the school, quantum mechanics, the physics of condensed matter, superconductivity are the main topics that we have to face as problem in the school, and research is contributing, and here we have good contribution. Third, instruments and methods to improve learning, student self-assessment, conceptual understanding and reasoning ability, open lab work. Fourth, teaching learning path, design and validation, method for designing and validation paths from student ideas, examples in surface phenomena. Fifth, research in the history of physics, the contribution of Majorana and Pontecorvo scientists in the development of physics now, and the first attempt for an AU interferometer gravitational wave observatory. Sixth, inquiry in physics education. Inquiry-based learning in an interdisciplinary approach to STEM and how to solve, anticipate, modify, reflect, implement, inquire strategy, contribute to engage teacher in co-designing rich tasks for use in the physics classroom. In addition, the impulse of reflection, practitioner inquiry based on small sets of data collected during classes. Last but not least, a very crucial point, explanation and critical analysis. 7, contribution of multimedia in physics education, resources and research-based activity development, digital competencies for teachers, example of computational investigation in the case study of collision, for example. Last but not least, the MAPS model in prospective primary teacher education, my closing talk. Many thanks to the colleagues contributing to FFP16 Symposium and to all of attendees. We do our best to build an interesting, rich of contribution environment, and I hope it will be useful for you all. Many thanks.
Thank you very much, Professor Maria Michelini. I'm closing this session. Then next, I'm inviting Professor Ali Ulvi Mazer to chair the next session. Thank you very much for all.
And I invite people from FFP Physics Education Research to join the session, the parallel session. Already, I believe it's ready. I hope it's ready.
Thank you. Okay, so let us start with the first session. Welcome, dear colleagues. Good morning, good afternoon, perhaps good evening, everybody. So cordial greetings from Ankara to all the participants. It is a great pleasure and honor to listen to talks by the distinguished physicists of our time in this online Symposium of Frontiers of Fundamental Physics, FFP16. In every session, the speakers have normally 15 minutes and 10 minutes is left for the question and discussions. So the first speaker is the Professor John Ellis. So let me say a few words before inviting him. Okay. So he is currently Clerk Maxwell Professor of Theoretical Physics at King's College London. His research interest is, as you know, quite wide, from phenomenological aspects to particle physics, astrophysics, from cosmology to quantum gravity. He made outstanding contributions in all of these areas, and he is pioneer of the research at the interfaces of these fields. Starting from BLEP and LHC, he played a major role in shaping Collider's physics research programs and made immense contributions. He is awarded Maxwell and Dirac medals and prizes in 1982 and 2005, respectively. Let me add, besides his legendary career, he continuously supported and encouraged the physicists of all over the world to collaborate so that his efforts fostered the international character of the CERN and the particle physics community. Thank you very much, Professor Ellis. So it is a great pleasure and honor for me to invite you. We are eager to listen to your talk on probes of gravitational physics using cold atoms. Yeah, yes, please, Professor.
Okay. Thank you very much for the invitation and the kind introduction. So I hope that you can see my screen okay.
Yes, it is okay. Very good. Yeah.
Okay. Unfortunately, I can't figure out how to show my own picture, but maybe you don't need that. Anyway, I know, here we go. Solve the problem. Okay, so I admire very much your objectives in this international and interdenominational, shall I say, physics conference with a very wide scope, both geographically and scientifically. So what I'm going to do in this talk is discuss how various different areas of physics come together in the study of gravitational physics. So I'm going to be talking about cold atoms. I'm also going to be talking about research for ultralight dark matter. I'll be talking about particle physics, astrophysics, and cosmology. And at the end, I'll say a little bit about other ways in which one can use cold atoms in space, in particular for monitoring climate change. So, without further ado, I'm sure that we're all familiar with the fact that Albert Einstein proposed the existence of gravitational waves back in 1916, very shortly after he proposed general relativity. What's perhaps not quite so well known is that in 1936, he actually tried to retract his prediction. But his paper was sent to a referee, and the referee said, well, Professor Einstein, I think actually your original idea was correct. So eventually Einstein changed his paper and republished the prediction that gravitational waves should exist. As I'm sure you also know, gravitational waves were first discovered indirectly by Hulse and Taylor, who observed the change in orbit of a binary pulsar system over many years. And as you can see in this picture down here, there's a perfect agreement with the prediction of Einstein's general theory of relativity. And Hulse and Taylor shared the Nobel Prize in 1993. So the study of gravitational waves opens up many opportunities in fundamental physics, astrophysics, and cosmology. And I just mentioned on this slide here a few examples. So, like electromagnetic radiation, we expect that the gravitational wave spectrum should extend over many orders of magnitude, with a wave period extending from the age of the universe down to milliseconds and maybe much smaller times. So some examples of astrophysics: there's a possibility of observing neutron stars, supernovae, and of course compact binaries, which were observed by the LIGO and Virgo experiments a few years ago. Eventually, we can hope to observe binary supermassive black holes in galactic nuclei, and I'll come back to that topic later on. Then, of course, we have cosmology. Many models of cosmological inflation. There is a tensor perturbation that corresponds to quantum gravitational waves, and there are a series of experiments planning to look for those quantum fluctuations in the very early universe. Another example of possible manifestation of gravitational waves is the observation of pulsars, not individual binaries like Hulse and Taylor, but many pulsars which act like lighthouses and whose signals could get perturbed in their passage to us by gravitational waves. And I'll say something about that later in my talk. So how do we detect these gravitational waves? So of course, the direct detection was pioneered by the LIGO and Virgo collaborations using laser interferometers. Eventually, it is hoped to do laser interferometry in space, for example, with the LISA experiment. Also, there are Chinese projects in that direction. But one of the central themes of my talk is going to be the use of interferometers using atoms, which is one of my own personal research interests. And I'll come back to that in a moment. So here is a summary of the results from the LIGO and Virgo collaborations, who've now been joined by the Kagura collaboration in Japan. So this very pretty picture shows you the masses of astrophysical neutron stars, of some examples of neutron stars merging to form black holes, as observed by LIGO, Virgo, and Cagra. And then up here in blue, we have black hole binaries measured by LIGO, Virgo, and now Cagra. Up in the top right-hand corner here, I've mentioned one very interesting topic, which is if you look at the expected spectrum of black holes, you expect to find a mass gap somewhere around 100 solar masses. Depending on the precise modeling, it may start around 50, it may extend to 150, but somewhere around 100 or so, there should be a gap in the black hole spectrum. And this is because of an instability associated with pair production of electrons and positrons. I'll come back to that in a moment. So I already mentioned that we're interested potentially in observing the mergers of supermassive black holes as occur in the centers of galaxies. And here I have an artist's conception of the LISA experiment, which is supposed to be taking data in the 2030s. And I also mentioned here a couple of parallel Chinese projects. So if I look here at the gravitational wave spectrum, as I mentioned, it's expected to extend over many, many orders of magnitude. And there are many interesting astrophysical and cosmological processes which may be observable. So LIGO, Virgo, and now Cagra are in this range around, let's say, 100 Hertz. And they observe the mergers of black holes weighing several tens of solar masses. Here is the range around 10 to the minus 2 Hertz, where LISA is the most sensitive, and LISA and its comparable experiments will be looking for mergers of massive binaries, maybe 1 million solar masses. Over here on the left-hand side, we have pulsar timing arrays, which, as I will discuss later, are potentially sensitive to gravitational waves with frequencies around 10 to the minus 8 Hertz, as might have been generated by massive black hole binaries very early in the history of the universe. Now, if you look at this picture, you're struck by the fact that there's a couple of gaps in our experimental coverage. So one is a gap around 10 to the 0 Hertz in between LIGO, Virgo, and LISA. And another one is the gap between LISA and pulsar timing arrays. And I think one of the instrumental challenges for the coming decades is to find techniques for exploring the gravitational wave spectrum in these gaps, and also, I would add, at high frequencies. Okay, so that's a general overview of the situation. So, as you know, LIGO, Virgo, and Cagra use light interference. And this is an illustration of the general principle of a light interferometer. You have a laser beam, which is split, and then the two sub-beams follow different paths, and then they merge again, and you look for interference patterns in the light fringes of the merged laser beams. So the underlying concept of an atom interferometer is similar. You start off with a beam or a cloud of atoms. You split them into two sets using a laser, which excites, let's say, half of the atoms to this state here, indicated in red. Then you apply a second pulse, called a so-called mirror pulse, which converts the excited atoms back into ground state atoms and the remaining ground state atoms into excited atoms. You then bring these atoms together and you can look for interference patterns. And here's some typical examples of the sort of atom interference fringes that you can hope to observe. So atom interferometers are sensitive to modifications of atomic properties generated, for example, by ultralight dark matter, and also to the passage of gravitational waves, which cause variations in the effective lengths of these two paths which meet to form the fringes. So as I mentioned, this is one of my own research interests currently. So I'm a member of the AON collaboration in the UK. So we're a grouping of universities and a national laboratory. AON stands for Atom Interferometer Observatory and Network. Network because we collaborate closely with a parallel MAGIS project in the US, which is building a detector at Fermilab. So what we envisage in the AON project is a staged program. So what we're currently engaged in is stage 1, where we build 1 meter and eventually a 10-meter interferometer, which will be located in the Oxford Physics Department. And we've got initial funding for this program from the UK funding agency. Then, if we're successful in that, we hope to get follow-on funding for constructing a 100-meter device. Eventually, we hope maybe in an international collaboration to build a 1-kilometer device. And eventually, and I'm sure this will be an international collaboration, to put an interferometer in space. That'll be sometime in the future, as I will discuss later on. So here is a planned location of the AON 10-meter device, which, as I mentioned, would be in the basement of the Oxford Physics Department, a very stable seismological environment, and it's got a nice location for a laser laboratory, which could produce the laser beams, which would be used to split and mirror and reassemble the atom beams so that we can observe their interference patterns. And this is a picture actually in the basement of the Oxford Physics Department. So here are some of the members of the AON collaboration. And you may recognize me down here taking a picture of the official photographer higher up. So at the moment, the AON collaboration is busy putting together laser laboratories in various different universities. As you can see here, London, Oxford, Cambridge, and Birmingham. So we will be using strontium, which is, for our purposes, the most appropriate isotope. It has a suitable excited state with a long lifetime, and we will be looking for interference effects which are generated by the varying phase due to either dark matter or gravitational waves. Perhaps one thing that I should explain is that we actually plan to use at least 2 and possibly more clouds of atoms simultaneously, which are interrogated by the same laser beam, because I talked about an atom interferometer. In essence, it's a differential atom interferometer looking at the difference between the changes in the fringes in 2 different clouds. That enables us to remove the noise due to laser, also helps us tackle the seismological noise. Now, your sensitivity increases if you bash the clouds of atoms many times. So we call large momentum transfers. And we have very ambitious aims for how many kicks we hope to give to the atom so as to get the maximum sensitivity to dark matter or gravitational waves. So this is one thing that the Aeon team has been working on, in particular on the problem of getting a stable laser, and they've been very successful in this. The level of laser stabilization that they've achieved is sufficient to exceed our science objectives by a very large margin. Of course, the number of large momentum transfers that we can achieve depends on many other things, but at least the laser system seems to be suitable. So, as I mentioned, the 10-meter Aeon device would be located in Oxford, and we're scouting locations for the follow-on 100-meter device. And those of you who know CERN will know that it's got the LHC collider, which is at a depth of about 100 meters. And so there are many vertical access shafts. Not all of them are being used, and we've identified one specific access shaft which may be suitable for doing the Aeon 100-meter experiment. And we're currently collaborating with CERN engineers to explore things like radiation protection, electromagnetic interference, seismology, and so on. So far, I've described the Aeon experiment, but there are many other experiments around the world. For example, there's the MEGA experiment in France, and I'll mention a little bit about its sensitivity later on. So here I've got a couple of examples of the sensitivity of the Aeon 100-meter device to gravitational waves. On the left, caused by the mergers of black holes weighing, let's say, between 1,000 and 10,000 solar masses. We should be able to observe them out to perhaps a redshift of 1. And on the right, I illustrate the sensitivity to a cosmological phase transition in the very early universe associated with some extension of the model of particle physics. So these are both physics topics that I'll come back to in more detail later on, but this just illustrates that already the 100-meter device has some interesting capabilities. Now, I talked about the sorts of black holes that LIGO and Virgo have been observing, and I talked about the fact that supermassive black holes exist in the centers of many galaxies. For example, our own. There was a picture of this released just recently. So the question is, how do you make a supermassive black hole? So a natural conjecture is that you make them by sequential mergers of intermediate mass black holes, masses intermediate between LIGO, Virgo black holes and the very large ones. And these intermediate mass black holes could possibly arise from a very early generation of stars, or they could be generated in proto-galaxies with smaller masses, which then subsequently merge to form the galaxies that we see today. It's clear that if we want to understand the astrophysics and cosmology of the formation of supermassive black holes, we would like to see intermediate mass black holes, let's say with masses 10 to the 3, 10 to the 4, 10 to the 5 solar masses. And this is where atom interferometers come into their own. So here, as a function of frequency, I show you the sensitivity of LIGO and a proposed follow-on experiment, the Einstein telescope. On the left here, we have the sensitivity of LISA, and in between, there is a gap. And it's in that gap that we would expect to see the mergers of intermediate mass black holes, the building blocks of the supermassive black holes at the centers of large galaxies. Measurements in this frequency could also give you advance warning of LIGO-Virgo black holes. So if you look at these dots here, potentially an hour or a day or even a month before a LIGO-Virgo merger occurs, an atom interferometer experiment could predict that it would occur, when it would occur, and which direction in the sky. So as I mentioned, eventually we would like to go out into space. And I hasten to say that if we do, then it's going to be after LISA. LISA is supposed to be launched in 2035. And I think that realistically, a space atom interferometer experiment would be at least a decade later. Anyway, big science projects had to be prepared well in advance. And so we made a sort of conceptual proposal for an experiment called EDGE, which we submitted to the European Space Agency. 3 years ago, they issued a call for ideas for science experiments that could be done in the period around 2050. So this gives you a sort of appetite what I was saying before about the potential sensitivities of atom interferometers to intermediate mass black holes. So far I've talked about AON. I also mentioned briefly the mass gap around 100 solar masses. These would be great for measuring the mergers of heavier black holes, and LIGO in the Einstein telescope, smaller mass black holes. So this is what EDGE could do. So EDGE could sort of fill in the gap in the row of what looked like shark's teeth, extending the search for intermediate mass black hole mergers out to the epoch of recombination, looking at possible mergers of black holes in that infamous mass gap. And they will be sensitive to the mergers of neutron stars with black holes potentially as heavy as 10 to the 4, 10 to the 5 solar masses. So EDGE would be a wonderful complement to the earlier ground-based and space laser interferometer experiments. So I talked a little bit about the astrophysics and cosmology that you could do with these devices. How about fundamental physics? So let me just mention one topic, which is constraint on the graviton mass. So by observing the structures of the gravitational waves coming during the infall towards the final merger of LIGO-Virgo black holes, they've established an upper limit on the graviton mass of about 10 to the minus 23 electron volts. You would get much greater sensitivity if you could observe such events over a longer period of time, and if you could observe the mergers of heavier black holes. And this is something that Vyacheslam and I analyzed a couple of years ago. We showed that, for example, AON 1 kilometer will be sensitive to 10 to the minus 24 electron volts with LIGO-Virgo type events. With heavier black holes, potentially around 10 to the minus 25 electron volts, and EDGE could potentially take your sensitivity below 10 to the minus 26 electron volts. So these detectors could potentially contribute to fundamental physics as well as astrophysics and cosmology. Another way in which they could contribute to fundamental physics is if there was a first-order phase transition in the early universe. And we've looked at various examples of this. So this is an example of a possible phase transition associated with an extra U1 vector boson. And just as an example here, we took a mass of 100 TeV with a sort of normal gauge strength coupling. And this would produce a gravitational wave signal, which could be observed by LISA and or by Aeon and Edge. So that was gravitational waves. Now let me just take a couple of minutes to say something about the search for dark matter. So as you know, dark matter, cold dark matter, provides a much larger fraction of the overall mass energy density of the universe than conventional matter. Of course, an even larger fraction of the universe's mass energy density is carried by dark energy. So one of the key topics for atom interferometers will be the search for cold dark matter in a different way from what has been done so far. So here I illustrate the population of cold dark matter candidates that people often discuss. So on the right, in the blue shaded region, we have candidates for dark matter which act like particles. So the characteristic example is the weakly interacting massive particle that might be provided by the lightest supersymmetric particle. But there are many other examples over in this blue region. Then over in the green region, we have bosonic fields that act coherently, forming a stochastic background of waves throughout the universe. So the first example of that was the QCD axion. There's many other types of axion. The axion, of course, is a pseudoscalar particle, but more generally, one could also consider scalar particles. And there's this broad category of axion-like particles that are considered by many experimental proposers. I should say that whereas WIMPs, I would say, had maximum popularity a few years ago, in the absence of dark matter particle detection at the LHC, more people are thinking maybe about this sort of ultralight dark matter candidate. That, I think, explains some of the increasing interest in this green region. So here I show the prospective sensitivity of various different experiments to ultralight bosonic dark matter of the type that I've been talking about. So you can consider various different ways in which such a bosonic field might couple to ordinary matter. So it might couple through the photon or the gluon or the electron or through quarks. So if it does have a non-trivial coupling to any of these particles, then it would in general affect the excitation energy of an atom. So here I have the excited atomic state, the ground state, and the interaction with dark matter could introduce oscillations in these energy levels, which would be detectable through changes in the interference patterns of the atoms. So that's the basic idea that is exploited in an atom interferometer. Now, in these two bottom pictures, I illustrate various sensitivities to dark matter coupling to the photon and dark matter coupling to the electron, and various different experimental probes of these couplings. So this horizontal line here comes from the microscope experiment testing Einstein's equivalence principle. And there is an idea, which I'll return to later on, for doing an atomic probe of the equivalence principle in space. But let me focus for the time being on these sort of triangular sensitivity lines here, which are the estimated sensitivities of various different generations of Aeon and eventually its space-based version, Edge. And you can see that these potentially could improve the sensitivity to dark matter couplings by many orders of magnitude. Now, there is one complication with the terrestrial experiments of this type, which of course is the Earth is a relatively noisy environment, seismologically speaking, and this generates something called gravity gradient noise, which you have to learn to dispose of or mitigate. I won't discuss that in this talk. It's something that my colleagues are thinking about. Now, in addition to linear couplings of dark matter to regular matter, you might also have quadratic couplings. And this is an example of the sensitivity to quadratic couplings of various generations of Aeon and the Edge experiment. Now, I mentioned a while back that we had proposed Edge to the European Space Agency for their 2050 program. And if I paraphrase how they responded, they said, well, you know, this is all very interesting, but that's quite some way in the future, and you need to do various programs of technology development. In the meantime, why don't you consider possible medium-sized missions using cold atoms, possibly to probe quantum mechanics and general relativity? And so that's something which I've been thinking about recently. So towards the end of last year, we organized a workshop on the use of cold atoms in space. And that workshop came up with this rather complicated looking roadmap. It's complicated because it doesn't just talk about cold atoms for fundamental physics, astrophysics, and cosmology, but also other potential applications. So I mentioned earlier on that the sort of atomic species that we would like to use in our atom interferometers is strontium, which is illustrated here in blue. Strontium is also useful for atomic clocks, and that is what we'd eventually like to use for our Edge-like mission, space-based atom interferometer looking for gravitational waves. So there is another technological line here illustrated in green, which is to use rubidium. And this is favored by the Earth observation community, because they would like to use cold atoms to measure the gravitational field of the Earth, which could be sensitive, as I'll mention in a moment, to the effects of climate change. Rubidium is also one of the elements of choice for a mission called STE-Quest, which would probe the equivalence principle and the universality of free fall. And this is a gravity experiment that would fit in naturally ahead of the Edge-like long-term goal. So shortly after we had our workshop in December, the European Space Agency issued a call for medium and fast class science missions. And we submitted a proposal for this STE-QUEST mission. STE-QUEST stands for Space-Time Explorer and Quantum Equivalence Principle Space Test. So I should say that this is a concept that has been around for perhaps a decade now, but it's something which I think has acquired new life with the possible interest of the European Space Agency in cold atoms in space. The lead proponent is Peter Wolf from France, and he's assembled a core team, and I am one of the members of this core team from different European countries developing this proposal. So the primary objective of STE-QUEST has always been to test the equivalence principle. And it's thought that STE-QUEST, by comparing the free fall of potassium and rubidium isotopes, would be able to probe universality of free fall, or if you prefer, the Einstein equivalence principle at a level of 10 to minus 17 or so. But there are many other things that it could do as well. So I already showed you on the same plot the current tests of the universality of free fall and our ideas for future probes of ultralight dark matter. So here I compare the current limits on the universality of free fall coming from the microscope experiment with what you'd be able to do with STE-QUEST, at this time translated into a sensitivity to dark matter couplings. And you see that STE-QUEST would give you sort of an almost uniform sensitivity to these dark matter couplings over a large range of frequencies. This is to be compared with the prospective sensitivity of AL100, where here I've incorporated seismological noise. And here is AL 1 kilometer with that seismological noise. So AL100 and AL 1 kilometer hopefully would come into operation before STE-QUEST, but STE-QUEST would, as you can see, give you a much broader sensitivity over a larger range of frequencies and hence dark matter field masses. Another topic of interest is quantum mechanics. So of course, there's been a lot of debate about the transition from quantum to classical behavior. I'm not going to go through this in great detail, but one of the possibilities is that there might be some fundamental process which causes wave function collapse. And I have to declare personal interest. This is something that I worked on in the early 1980s. It's also been pushed very much by Ghirardi, Rimini, and Weber, whom I quote here. So they give a general parameterization of the possible collapse of the wave function in terms of the time dependence and the scale dependence. So it seems that STE-QUEST would have a unique sensitivity to such models of wave function collapse. So here on the vertical axis, we've got the time parameter lambda. On the horizontal axis, we've got the range R. And as you can see, STE-QUEST would reach right into this region, which has not yet been excluded. And it would come very close to the parameters that were proposed by Ghirardi, Rimini, and Weber. So on that roadmap for cold atoms in space, I had other topics besides fundamental physics. And one of them concerns timekeeping and geodesy. And for that, you need to have the latest next generations of atomic clocks in space so that they can measure the gravitational potential of the Earth. And you link them together and you would get a new universal time standard, which would be much more accurate, much more sensitive than what we're currently using. And this picture just illustrates that cold atom clocks can now reach fractional uncertainty at the level of 10 to the minus 18 or so. So there is an ambition in our cold atoms in space community of translating that sensitivity from the laboratory up into space and eventually into a world time standard, which would also have applications in geodesy. Another application of cold atoms in space is to measure the changes in the Earth's gravitational field, which could be induced by the fact that the mass distribution on Earth is changing. In particular, it's changing because of changes in the equivalent water height. And there's been a series of Earth observation missions observing these effects. And the Earth observation community would like, as a next step, to put a quantum device, cold atom device, into space. Now, the big advantage of a quantum device is that since it is depending on fundamental properties of atoms, it will not drift like the current classical accelerometers. So here there's a comparison between the sensitivity to equivalent water height for a quantum detector and a current classical accelerometer. These different colors show you that your sensitivity to the water height is just much greater with the atom device. And this is particularly interesting from the point of view of monitoring climate change. You can, in principle, measure much more accurately the changes in the ice caps in Antarctica and Greenland. You could measure sea level change. You could, in principle, get higher spatial resolution than current detectors, which would enable you to monitor what's going on in individual mountain ranges and river basins. So this is, I think, another potentially very interesting application of cold atoms in space. Okay, so I'm going to the end of what I want to say. As I've emphasized, experience with electromagnetic waves shows the advantages of making astronomical observations in a range of different frequencies, and surely the same will be true in the era of gravitational astronomy. Different frequency ranges are sensitive to different processes or different stages of the same process, like different stages of the mergers of black holes. So I outlined the atom interferometry program offered by AEON and eventually its space extension EDGE, which includes observations of intermediate mass black holes, first order phase transitions. And I've emphasized that both AEON and EDGE complement and have synergies with other future gravitational wave experiments. There are also opportunities to search for new fundamental physics, such as ultralight dark matter. So cold atoms in space also have interesting capabilities for probing the principle of equivalence and perhaps also quantum wave function collapse. So these are all applications to fundamental physics, astrophysics, and cosmology. But as I've emphasized at the end, there's a broader interest in other applications of cold atoms in space, which I think you will agree offer unique interdisciplinary science. Thank you.
Well, thank you very much, Professor Ellis. So we have good time to have the questions and then discuss. Actually, in the chat lines, okay, we have some questions coming from the participants. So I can give opportunity to Ibrahim Semis to ask questions, or may I read from the chat lines? Which yes, Ibrahim Semis, we are listening to you.
Yeah, actually, I've written 3 questions. One is, the first is there a simple argument that illustrates the superiority or the difference of atomic interferometry versus light interferometry in the context of gravitational wave detection? So you are saying that it's sensitive to a different frequency range. So why is that? Because for the same energy, the momentum is larger. Is that?
Yeah. So the fact that you're using atoms, massive objects, gives you sensitivity to a very different range of frequencies.
But I mean, is there a simple mathematical argument to show that it's like 3 orders of magnitude larger or whatever?
Well, if we go back to my plot, I think you'll see that it's not 3 orders of magnitude difference. There's not a big difference in point of fact. And there have been concepts for light interferometers which should also reach into the, well, this,
okay.
This plot here, I think, illustrates the point. So LIGO is optimal somewhere around, let's say, 100, a frequency of 100 hertz. You lose sensitivity around 10. The Einstein telescope would have a slightly larger range, but still, once you get below 1 hertz, the existing laser interferometer projects don't have any sensitivity. Likewise, LISA has an optimal sensitivity around 10 to the minus 2, 10 to the minus 3 hertz. And again, it loses sensitivity in this low frequency, in this higher frequency range. So this is, if you like, the physics opportunity or the science opportunity. So this is why atom interferometer devices are tailored for this frequency range. So there's a range of, I would say, about 2, maybe 3 orders of magnitude in frequency.
So, but is it like similar to the reason why an electron microscope is better than a light microscope? I mean, the wavelength is shorter at the same energy.
No, I think that's a good analogy.
Yeah, okay. All right. If there is no other question, I have 2 more.
Please go ahead.
Okay. The second is in your figures, you have shown the installations or the plans for the installations for the Ion 10 and Ion 100 to be vertical. So first of all, why are they supposed to be vertical? And secondly, vertical means you are if you are distinguishing vertical and horizontal, that means you are referring to gravity. So what about for age or whatever, if you go to space where it is weightless environment? So the question has 2 parts.
Okay, so thank you for that. So the reason why in a terrestrial experiment you use a vertical shaft is that you would like to basically interrogate your atoms many times with your laser system. I remind you that the more times you hit an atom with a laser, the larger the momentum transfer, the more you open up the sort of hysteresis loop, and the greater the sensitivity to new physics. So that's why in a terrestrial experiment, you like to do it vertically so that you can have a single laser system which interrogates the atoms many times. And as I reminded you, it's actually a differential interferometer in that you measure the difference in the interference patterns for 2 or more clouds. And that's illustrated here. We've got an atom source halfway up, an atom source at the bottom, and you compare the 2. That way you get rid of the laser noise. You've got a common laser. You've got a common laser because you've got a vertical shaft. Was that clear? I think I said.
And why can't you do this horizontally?
Well, because then the atoms will fall out of the laser beam.
Ah, okay. So you want the atoms to not drift sideways. That's the answer.
Correct. Correct.
Okay.
Now, I did mention that there is another experiment that's being proposed, actually under construction in France. And in fact, in their case, they actually do have a horizontal structure. Mm-hmm. But there they have many atom sources, but each one they interrogate only a very limited number of times. And so basically they hope to make up for the smaller number of momentum transfers by having a larger number of sources. Okay. Obviously, we're rather skeptical about that design, but they're quite optimistic about it.
Okay. Again, anyone else?
Yeah, I think there is no other questions, but
all right, then my third question.
Yes, okay.
Okay. If I saw correctly, the maximum sensitivity of ion 10 was about 10 to the minus 16 or 17, right?
Yes.
For the strain. So again, if I'm correct, there are no gravitational waves expected to be that strong at Earth. So when you construct ion 10, how will you know that it works?
So ion 10, you're absolutely correct. It is not going to be sensitive to gravitational waves. So in the sequence, the first detector, which would be sensitive to gravitational waves, would be ion 100. Now, what we will be doing is operating ion 10 in a network with the MAGIS detector in the US. And I think one of the ways in which you know whether any result that you see or you don't see is real or not is by comparing the signals in the two detectors.
What kind of signals? I mean, it won't detect gravitational waves, so what will it detect?
No, but it will detect
seismological things.
It will detect changes in the atomic interference pattern, which are induced by the coupling of the ultralight bosonic dark matter field to the particles in the atom.
If such a matter field exists.
If such a matter field exists, exactly.
Okay.
So if it doesn't detect anything, will that rule out ultralight dark matter?
Well, then you would exclude ultralight dark matter.
Up to whatever, yeah.
So I should say that although this looks like a modest improvement on the microscope experiment, it's actually, not sure whether I have no, I don't have the plot here. It's actually, something like an order of magnitude improvement, of course, over a limited range in frequencies. Okay, but I should say that Aeon 10, it's a sort of a pioneer experiment to demonstrate that one can actually do these manipulations with atoms and lasers, and it's the first stepping stone in the program.
Proof of concept. Yeah. Okay, thank you very much.
Well, thank you for your questions.
Okay. Yeah, as far as I see, there are no other questions. So let me ask. Okay, the Birmingham group, okay, has applications of the cold atoms for very modest, okay, purposes. Perhaps for the civil engineering and the archaeological purpose. So they detect the underground, okay?
Right.
Yeah, okay. another application of the fundamental physics. Okay, so similar to the muon detection to search for the voids in the Egyptian pyramids. Okay, so the fundamental physics have too many applications for very simple purposes also.
Right.
Yeah.
Yeah. So indeed, that Birmingham group is a member of the Aeon team, and I think you can regard the sorts of applications that you're talking about as being a sort of entry-level applications of cold atoms for Earth observation.
Yeah.
And they illustrate the capabilities of cold atoms for measuring very small changes in the gravitational field due to subterranean effects.
Yeah, yeah.
So yes, that's
okay.
Fully integrated in our collaboration.
Okay, yeah. So I think the time is over also. So we thank very much to Professor Ellis for his wonderful talk. So okay, we were very glad to hear his talk. So thanks. So bye-bye. And we continue with the next speaker, Sabine Hossenfelder. So okay, she is already present, but let me first present a few words, okay, say a few words. She is currently a theoretical physicist at the Frankfurt Institute for Advanced Studies. She is very well known for her outstanding works on quantum gravity and on quantum foundations. And as you know, she is author of the popular science book on the laws in math. Okay. So her scientific explanations on YouTube channel are very famous. She has also public engagement via giving talks, lectures, writing popular articles, etc. So title of her talk is the Superdeterminism, the Forgotten Solutions. So welcome, Sabine Hossenfelder. So it's your time. Thank you.
Thank you for the introduction. Can you all hear me okay and see my slides?
It's very okay. So also,
okay.
Yeah, okay.
Wonderful. Okay, so I'm going to talk about superdeterminism, and if you know the word at all, you've probably heard that it's an interpretation of quantum mechanics. And I want to start out by objecting to this description. In my mind, an interpretation is a different way to look at the same theory by using different mathematics, but ultimately gives rise to the same predictions. There is a value in having different interpretations of this theory. I don't want to deny this. There's certainly interesting things that have come out of rewriting quantum mechanics, for example, in terms of Bogian mechanics or many worlds interpretation brings different aspects into your attention. But superdeterminism is not an interpretation, it's actually a modification, or some people might call it a completion of quantum mechanics. It actually gives rise to new phenomenology. And people tend to be a little bit confused about why I would want to do that, because what's wrong with quantum mechanics? I'll get to this in the next slide. They've come up with all kinds of weird reasons for why I'm interested in superdeterminism. Is it maybe because I just really, really like determinism and I want to get rid of the indeterminacy of quantum mechanics? Or do I want to go back to a classical theory? Or do I want a realist description of nature? Or somewhat confusingly, sometimes people think I want to disprove Bell. That normally comes to those people who think that Bell's theorem or the observed violations of Bell's inequality have actually ruled out all local hidden variables theory, or maybe I just do it to be controversial. So none of those are the actual reasons. The actual reasons are far, far simpler. Quantum mechanics has some real shortcomings that we've all heard of as when we were students, but we have so gotten used to them that we've pretty much forgotten about them. The most obvious problem is what's known as the Heisenberg Cut. which is the question: at which size does a thing become a detector? What is it that makes some devices detectors and others not? And exactly how do you distinguish between them? This just isn't anywhere to be found in quantum mechanics. In quantum mechanics, we have the Schrödinger evolution, then we have the measurement postulate. But basically, a detector, well, we know what it is when we see it, right? If quantum mechanics was a fundamental theory, then we should be able to explain what a detector is based on it, but we can't do this in quantum mechanics, even though most people think that it's actually fundamental theory. Then there is the collapse problem, and I didn't call it the measurement problem, though this is a phrase you're probably more used to, because I think the measurement problem really combines several problems. The Heisenberg Cut is one of them. So the collapse problem is if we just take the update postulate and interpret it as a physical process, it's not local. So this doesn't fit together with special relativity, and more importantly, it doesn't fit together with general relativity. But if it's not a physical process, then what's the process? Just saying there, you know, you're not supposed to ask the question doesn't really explain it. The problem becomes particularly pressing if you want to understand how gravity interacts with quantum mechanics. If you think about the semi-classical limit of general relativity, then you have an expectation value of the stress energy tensor as a source term, and that expectation value would have to be updated upon measurement, and that update is normally non-local. Unfortunately, such non-local processes are not allowed on the left side of the equation. So in the Einstein's field equations, where you describe the curvature, those terms are locally conserved. So something clearly doesn't add up. And just saying, well, the collapse is not a physical process doesn't tell me what happens. And then there's the classical limit. This has been known for a long time, for 50 years or something, but the classical limit works well really only for integrable systems, and chaotic systems have been a problem for a long time. This isn't really all that surprising because quantum mechanics is, after all, a linear theory. Okay, so those are, in my mind, all problems which we have with quantum mechanics that I want to have an answer to. But how do we do this? Well, the most obvious thing to do, this is an old idea, but that's never gone out of fashion, is that you postulate quantum mechanics is not a fundamental theory, it's emergent from some underlying hidden variables theory. So the outcome of a measurement is determined by some hidden variables. Those are normally denoted lambda, and the seemingly random outcome is due to our lack of knowledge of the precise state. So the randomness comes from the same source that it does in classical mechanics. And in that case, the wave function is an ensemble. So it's a psi epistemic theory, but not because there are questions you're not allowed to ask, like in the Copenhagen interpretation, but because there actually is an underlying ontic state about which we're lacking information. And so those things have become called hidden variables for historical reasons. You know how it goes with terminology in literature. It doesn't always make a terrible lot of sense. That those variables are hidden just means they do not appear in the standard formulation of quantum mechanics. It does not mean they are unmeasurable. The philosopher Tim Morden has proposed to call them additional variables, and I much like this term, but most often people then don't actually know what I'm talking about. Okay, so what does it mean? Well, it means that quantum mechanics is not a fundamental theory. It is emergent, and you get it out, you get it back if you average over the hidden variables. The measurement postulate is then just an effective description for a process in this underlying more fundamental theory. This idea is supported by the obvious similarity between the classical Liouville equation and the von Neumann-Dirac equation, which basically screams in your face. You're actually dealing with a statistical theory. This argument has been made in somewhat different form by Klein in an interesting paper from about a decade ago, where he points out that if you take the h-bar to zero limit, you actually do not get classical mechanics for a single particle, but you get a statistical theory. That's kind of again, it's one of those things that's so obvious we never really think about it. If you want to get out a theory for a single particle, you also have to take certain limits for the wave function. Okay, so why superdeterminism? I'll try to explain this with a very simple argument based on a Mach-Zehnder interferometer. So suppose you have a laser beam that's supposed to be the red line, and you just send it into a detector, and the detector goes big. Now you can put a mirror there, and it'll go into the other detector. So far, so good. And now we replace the mirror with a beam splitter. So now if you don't have a beam, but you have an individual photon, quantum mechanics tells you what happens if the photon hits the beam splitter is that you produce a superposition of both paths. Now, the problem is that if you measure the particle, it does not give you a superposition of both detectors. It gives you either one or the other. So how do you make sense of this? How do you get the particle to go into only one of the detectors, which is what we actually observe? Well, it's simply enough. You introduce some hidden variable, and then depending on what the value of the variable is, the particle either goes to the right side or it goes to the left side. Sorry. So, all right, so far so good. But of course, that's not the only thing you can do. You can also recombine those superpositions with mirrors and the second beam splitter. And we know that in this case, the photon always goes to the same detector. You can also test by putting some phase shifter on the both paths of the interferometer that there's actually something happening on both paths. So it's not like the particle actually takes only one path. So how do we make sense of this if we want to describe what happens in terms of a hidden variables theory? So that's kind of a big problem for all local deterministic hidden variables theory. Well, in my mind, the answer is fairly simple. It's that what the particle does depends on the measurement settings. So this A and B is the notation for some kind of measurement settings. It could be one detector, it could be 2 or 5, what have you. People who like to talk about Bell's theorem normally have 2 settings because they're 2 detectors, but it doesn't really matter. The point is that this distribution, which is the row of the hidden variables, has to differ depending on what the measurement settings are. So if you measure the path on which the photon goes, then that's one distribution of the hidden variables. If you recombine them and you measure them after you've recombined them, you measure the interference, and that's a different detector setting. So you have different distribution of hidden variables. And that's explains the Mach-Zehnder. You can do the same thing with your favorite experiment, double slit experiment, where you measure interference or which path measurement, or Bell experiment in any kind of combination, whatever you want. But I choose this just because my PowerPoint skills only go so far. Okay, so what does this mean? So this relation, if it's fulfilled, it's called statistical independence. So those theories all violate statistical independence. And what this previous argument just showed you is that any local deterministic solution of the measurement problem requires that the distribution of the hidden variables depends on the measurement setting. So this assumption is violated. It's also known as measurement independence, free will, or free choice. And oh yeah, I put a note here so I don't forget to say this. These theories don't have to be classical in any sense. You could already see this from the previous argument with the Mach-Zehnder interferometer, because there are cases in which the particle actually goes over both paths and then they are recombined. So that's not a classical point particle or something like that. Okay, so Bell's theorem, in a nutshell, the way that I look at it is that if you combine local causality and statistical independence, you get a conflict with observations, because all theories which fulfill these 2 assumptions have to obey the inequality, but it's experimentally violated. But we already know that to solve the measurement problem, statistical independence must be violated. So all the interesting hidden variables theory violate the assumptions of Bell's theorem anyway. So for this reason, there isn't actually a reason why you would have to violate local causality. So what then do we mean by a superdeterministic theory? Well, it's a hidden variables theory, a local hidden variables theory, I should have put this here, which violates statistical independence. Now I have to warn you that I just came back from a workshop where we spent 1 week arguing over what exactly we mean by superdeterminism. So if you look at 2 different papers on the topics, you get 3 different definitions, I'm afraid. For example, some people don't actually assume that a superdeterministic theory is also deterministic. Now, leaving aside that an indeterministic superdeterministic theory is about as stupid as nomenclature can get, I also think it's superfluous to do this kind of mind bend, because whenever you have a time evolution that's indeterministic, you can just take this indeterministic element and quantify it with some kind of hidden variable, and then you chalk it up to the hidden variable. So then you have an evolution that's deterministic given the hidden variables. So I think that the deterministic theories actually encompass both cases. This name is extremely misleading, which is why everyone who works at it is really unhappy with it. It suggests a theory that's more deterministic than deterministic, and what's that supposed to be? Personally, I would prefer to use Bohm's term implicate order for the following reason. So I'm not sure what Bohm would think about this, but I think this term describes it very well. If you think of your typical Bell type experiment where you have a source where Bell put the hidden variables at the source, but I have a little bit to say about this later. And then you send your entangled particles, one to the left and one to the right, to the detectors that I've labeled with A and B. Then superdeterminism says that this distribution of the hidden variables depends on those settings. But now, of course, this is a deterministic theory, so you can always take the detector setting and roll it back in time with the evolution law to some initial state. And that initial state will, in general, be spread out over a big part of a space like hypersurface. It will be ridiculously complicated. This is why people think of superdeterminism as a kind of a conspiracy, because you get this idea that, well, gee, all the different ways these measurement settings could have come about must have been covered by this theory. Now, this is extremely misleading, because the only thing you really need in the end is the measurement setting itself. And already in quantum mechanics, if you think about it, we could do the same thing. We could take the measurement setting at the time of detection and roll it back to some hideously complicated initial state, and then we could say, oh gee, my God, all those details in the initial state, how do we ever get them? Well, we just never need them. So I don't know why people sweat about this point so much. But in a superdeterministic theory, this correlation, which comes which in the way that I've drawn it comes from the preparation with the detector settings at the time of preparation, can always be re-expressed as some spread out correlation on this initial hypersurface, which then unravels into this very clean correlation between the setting at the time of measurement and the hidden variables. So you have this implicate order on the early slice that unravels into this explicate order. And so this is why I think that the term is quite inappropriate, quite appropriate. Okay, so historically, superdeterminism has been lumped together with the question of free will. As I said earlier, the assumption of statistical independence in Bell's theorem is in fact often referred to as the free choice assumption or the free will assumption, because it seems to have something to do with the experimental's choice of the detector setting. I find this association to be very unfortunate and misleading. Well, for one thing, there's the obvious. Choosing a detector setting does not necessarily require human actors. You could just do it with some kind of machine. And in fact, this is often the case. But maybe more importantly, free will is generally hard to make sense of in any theory that is deterministic. And there's like a debate going back in the history of philosophy for as long as there have been philosophers. And this tension has nothing to do with superdeterminism in particular. And then there's also the fact that the laws of nature always constrain what we can do. Just think about, for example, you would like to put two fermions into the same state. Well, the current laws of physics, to the extent that we know them, just say you can't do this. That's the Pauli exclusion principle. But no one in their right mind would say that this constrains our free will. It's just the way that nature is. And it's the same with superdeterminism. So statistical independence is violated, hidden variables are correlated with the detector setting. That's just the way it is. It doesn't have anything to do with free will. Okay, so this brings me back to the question, like, where are the hidden variables? As I said, I believe the way that Bell thought about them is that they are some kind of property of the prepared state. So if you have your Bell type experiment and you have your initial spin zero state that decays into this entangled pair, then a lot of people, especially particle physicists, like to picture those hidden variables as an intrinsic property of those particles. But this is not how they actually appear in the theorem. The theorem doesn't say anything about where the hidden variables are or when they are. The only thing that we know about the hidden variables are that they are what determines the outcome of the measurement. This is actually the definition that Bell wrote down, and this is in fact how it enters the proof. But now think about it. If the hidden variables were some kind of initial state of the particle at the time of preparation, then this would not determine the outcome, because you also need to know the time evolution of those hidden variables. So what determines the outcome is really a combination of the initial state plus the evolution law. And what's the combination of an initial state and an evolution law? Well, it's a trajectory. So the hidden variables are not initial values, they're actually labels for trajectory. Now this little graph which I have here, it's supposed to show the initial state of the hidden variables, and this ensemble of states falls apart into two different clusters. You could say in each of those clusters corresponds to one detector eigenstate. So it splits apart. And really the only thing you need to know to make the predictions coming out of Bell's theorem or whatever else you want to predict is you need to know which of those clusters does the initial state go to. But for this reason, asking where the hidden variables are located makes no sense. The trajectory, the position changes. Okay, so this is a somewhat funny objection that I have to address, because if you dig into the literature about superdeterminism, it's one of the things that you undoubtedly come across. Does it destroy science if we give up the notion of statistical independence? And I believe where this idea comes from is that this assumption of statistical independence is really important in other areas of science. If you think about random controlled trials, you always have an assumption that the way that you choose your control group has nothing to do with what you're later going to measure. So, and of course, it works very well. So this assumption of statistical independence has certainly helped us to understand a lot about how the world works. So I can understand that throwing it out might seem like a threat. But of course, we know experimentally that the properties that we understand as typical quantum properties, like entanglement, for example, or the uncertainty principle, and superpositions of two places, like things being in two places at the same time and so on. We don't normally observe them for large macroscopic objects. So there's no reason to think that those violations of statistical independence, which we see in quantum foundations, would carry over to macroscopic objects. In fact, if you think of my earlier argument, the only reason you need those violations of statistical independence to begin with is to get the state to go into a detector eigenstate, which is what we actually observe. So they are violated if and only if the Schrödinger evolution would lead to a superposition of detector eigenstates and kind of Schrödinger cat states. And since this is not what we observe, we wouldn't expect to see any such violations in macroscopic objects that we do observe. In fact, you need this violation of statistical independence just to explain why we observe such macroscopic objects in the first place. But what does it mean? What does it mean to violate this assumption of statistical independence? Well, you can just express this equation in words. I told you earlier that the hidden variables label the trajectories. They describe what the prepared state does. And if this condition is not fulfilled, it means that what the prepared state does depends on the measurement settings. Now, an objection that might come to your mind is that this is completely useless because we don't know the setting. If before we have done the measurement, we don't know what the setting will be, because there could be some random number generator or experiments that they have actually done where they've used photons coming from distant quasars and that kind of stuff. And that's all well and fine, but think about it. We never know this. We also don't know it in quantum mechanics. What we do instead is we make predictions for all possible settings, and then we compare the predictions with the result that we actually measure in the laboratory. Ken Wharton has proposed to better refer to this as a future input dependence. So the input here is the measurement setting at the time of preparation. And when he speaks of future input, I believe what he means is he means this in a purely operational way. You have a model, and you put in some parameter, and then you make your calculation the same way that you always do, just that in this case, the input is actually a variable that you will only learn in the future. Doesn't stop you from doing the calculation with it, though. Okay, but what the most important feature of all those superdeterministic theories is that they have to be non-linear. This is just because the measurement process is not linear. If you think back of the example that I told you earlier with the photon going to some kind of detector, you can send the photon to the left, and the left detector will pling, or you can send it to the right, and the right detector will pling. But if you send it through the beam splitter and you create a superposition, you do not get a superposition of the detector outcomes. So whatever the underlying process looks like, it has to be non-linear. And this means these underlying theories are quite possibly also chaotic, which in my mind explains why the hidden variables are hard to measure. Otherwise, we already have found them. So where are we in terms of theory development? Well, there are a variety of toy models that have been around since the 1980s or so. Those demonstrate that you can reproduce quantum mechanics in certain systems, like typically those papers focus on bell-type tests. You can reproduce those if you violate statistical independence. It doesn't take much. It's not particularly complicated. There are very few full theory approaches to superdeterminism. I'll tell you a little bit more about the existing ones in a moment. But first, I want to tell you a little bit about a toy model that I've been working on with Sandro Donati, and you find this on the archive. This is looks a little bit intimidating, but I swear it's actually quite simple. So this works for any finite dimensional Hilbert space. So n is the dimension of the Hilbert space, and we define n complex hidden variables. Those are the sigma n, and they are just uniformly distributed in the unit disk. And from those, we derive a related random variable, which is the lambda. We really just do this for convenience. And in this distribution, there enters the projection of the wave function, which is the psi at the time of detection, TD, on the detector eigenstate, which is the I. So those coefficients AI, they are just the measurement outcomes that you expect in standard quantum mechanics. So now we have those random variables, and from those we define a set of Lindblad operators, and then we just add those in the standard form to the master equation. And I guess you've probably all seen this kind of formulation. So you get first order differential equation for the density matrix. And yeah, I should probably add, so this density matrix, since it depends on the hidden variables, is not actually the density matrix of quantum mechanics. You get the density matrix of quantum mechanics if you average over the hidden variables. So what happens in this model is the following. The evolution of any initial prepared state, no matter what the value of the hidden variables, is a detector eigenstate. Exactly which eigenstate it is determined by the hidden variables. And when you average over the hidden variables, the probabilities agree with those predicted by quantum mechanics. The reason for this is that we put in the probabilities from quantum mechanics into the notion of the hidden variables. So what this gives us is a deterministic local collapse process that reproduces quantum mechanics exactly. It doesn't require any fine-tuning. So this was the reason we put out this toy model to begin with, because there are a lot of papers that have argued that superdeterministic models necessarily need to be fine-tuned because of this conspiracy argument. There's nothing to fine-tune in this model. As I said, the hidden variables are uniformly distributed in the unit disk. There aren't even any free parameters. There's this one parameter in the master equation, which is the kappa, but you don't actually need to know exactly what the kappa is. It just has to be small enough to not be in conflict with observations that we have done so far. Ultimately, the reason you don't need any fine-tuning is that to get Bond's rule, you don't need any more assumptions than Bond's rule. We've put in Bond's rule, and now there's nothing left to fine-tune. Now you could argue, of course, well, that's a little bit pointless, and I would agree. If deriving Bond's rule is what you wanted to do, then that's entirely pointless. But this is a reformulation, you could say, of quantum mechanics that gives you exactly the same result, but it's local. And for me, this is the important point. Now, I called this a toy model rather than a theory, because ultimately just saying, well, I have those variables and they're just there, and they have this distribution, doesn't really explain very much. Also, as I just said, if you average over the variables, you get back quantum mechanics exactly, which is not what you want. You actually want to know what the hidden variables are, so you can make a prediction for the distribution and possibly see deviations from quantum mechanics. So this is not the case in our model. It was really just there to explain why this argument that superdeterministic theories need to be fine-tuned is obviously wrong. Well, I would say it's obvious, but maybe it wasn't so obvious to other people. Okay, so, but what about real theories? As I said, there aren't many, but we have at least two approaches. In all fairness, I would say none of the existing approaches is really satisfactory. The probably best known one is Truft's cellular automata approach. So this is a deterministic local quantum mechanical model which builds on a discrete space and time. And it's based on this idea that cellular automata can give rise to a lot of complexity, as you probably know. It defeats Bell's theorem by postulating that only some of the initial states are allowed, and those are the ones that lead to results which agree with quantum mechanics. So this is a kind of super selection rule for the ontological states. And it's this super selection rule that's nonlinear. So this is where the nonlinearity comes in. The problem with this approach, well, besides from the problem that you discretize space and time, which comes with a whole string of problems coming after it, is that you don't really know how to choose the initial state. If you just choose it by the assumption that it reproduces observations, then the theory has no predictive power. So you need some kind of measure on the initial states. And the last time I looked, it wasn't really clear what the measure would have to be. But in any case, so this idea has been around for some time. There's another idea which is actually even older, which is Tim Palmer's invariant set. So in this approach, state space, so that's the state space for everything, basically, is a fractal. So it's not a continuum the way that we're used to it, but it's a fractal, and it has gaps, which are states that do not exist in physical reality. So if you have a state like our universe, which exists, then right next to this, if you make an arbitrarily small perturbations, there are many states that do not exist. And the problem with this kind of structure is that making a generic perturbation just kicks you out of the theory. As a result of this, not all combinations of prepared states and detector settings exist, which effectively leads to a correlation that violates statistical independence. So this is kind of an idea for a more fundamental underlying structure in state space that explains why statistical independence is violated. And Tim Palmer has put forward some ideas for how to experimentally test this. Okay, now I want to tell you a little bit about my own attempts to develop a more complete theory for superdeterminism. I think there are two key questions. One is, what are the hidden variables? And when do deviations from standard quantum mechanics become relevant? So the second question is the important one for phenomenology. Now, in Tuft's model, the hidden variables are higher energy degrees of freedom, which he integrates out. In Tim Palmer's model, he has a p-adic number that quantifies which cluster the state develops into. Now, personally, since I have a background in particle physics, I don't like the idea of introducing new variables. It's just really hard to make compatible with the standard model. You can try to hide them at higher energies, the way that Tuft does, or you could try to make them very weakly coupling. The problem with that kind of thing is that then you have to explain why we seem to see their relics in low energy experiments that we typically do in quantum mechanics. And also, we already know that the detector settings determine the average of the distribution. But a detector isn't just a setting. A detector is a big thing with a lot of individual particles that may slightly wiggle around. And to me, this brings up the obvious question. Couldn't it just be that the other details of the detector, which is not this 1 degree of freedom that is the setting, are the hidden variables that determine the outcome? And I should probably add here that when I say detector, I don't. And so basically everything except for the prepared state. And for what the other question is concerned, when do the deviations from standard quantum mechanics become relevant? I really, really wish I had an answer, but I don't. I've been thinking about this for many years, and eventually I just came to the conclusion that you can't derive a more fundamental theory from a less fundamental one. If I could, then it wouldn't be more fundamental. So we need some new parameter that sets a scale that may be the number of particles or the total energy, or if you believe Penrose, then maybe it's the got something to do with the gravitational energy, could have something to do with the action or the amount of entanglement or the masses of the objects, or a combination thereof. Actually, you also see this in collapse models, since this came up in the previous talk. You also have, so you need some new parameter to tell you when this process is going to become important. Now, to make a long story short, I don't know what the right parameter is or what the combination is. Whatever you want it to be, give it to me and I'll write down a model for you. And so for me, this is, if I were to actually write down this model, I'd be pretty convinced that it's wrong, because I can make it work for anything, which is why I've refused to write down a model. There's somewhat of a lose-lose situation. If I don't have a model, then people complain to me, oh, you don't have a model. But if I were to actually write down a model, then in the best case, someone would go and actually test it, and then they'd rule it out, and then they'd say, well, we've ruled it out, even though it was only a prediction that I didn't actually believe in. Okay, but here's generally the attempt that I've made to answer those questions. I've assumed, as I just said, that the hidden variables are really the degrees of freedom of the detector besides the actual setting. The setting determines the average, so this is where Born's rule comes from, and the rest of those degrees of freedom determine which outcome is realized. I assume that the actual time evolution for both prepared states in this underlying more fundamental theory optimizes some quantity if you vary over the final state. So basically, you're looking for the final state that makes the outcome optimal in some sense. And that's why it's super deterministic, because it depends on this final state. So what it comes down to is that you want to construct a quantity so that if the final state includes an interaction with the detector, then it may be better for the prepared state to go off the Schrödinger evolution. So it will have to reach a balance. On the one hand, it wants to remain on the Schrödinger evolution. On the other hand, this wouldn't lead to an optimal outcome. So in some circumstances, if you have a big detecting device, then the Schrödinger evolution will not longer be fulfilled. How do you get Born's rule? Well, people often throw two different things together in Born's rule. One question is, why are the probabilities given by the absolute square of the wave function? Now, that's an interesting question, but I believe that under fairly mild assumptions, the answer is that this is pretty much the only way you can put a probability distribution on a vector space. The more important question is, why are those probabilities given by the absolute squares that you get from the projection on the detector eigenstates? So remember, you ultimately want to describe where the Heisenberg Cut comes from. So why the detector eigenstates? What's so special about the detector eigenstates? How does this end up in the evolution law? So this is the thing that you want to explain. And the idea is roughly that the detector eigenstates are all very optimal end states compared to superpositions of those states. It would be a typical Schrödinger cat state, where a detector clicks and doesn't click at the same time. But just exactly how optimal it is, like the fine details, that depends on the exact initial state of the detector and the environment. And this is where the apparent randomness comes in, because we can't exactly know what this initial state was. And as I said, it isn't all that difficult to get done. The key question that remains is, what's the scale where it becomes important? And the reason I say it isn't all that difficult to be done is that we don't actually have any data between the preparation and the measurement, because no one's ever done a measurement before a measurement. That just doesn't exist. So there's a lot of freedom for how to write down the dynamical law. It just basically anything that gets you from the prepared state into the detector eigenstate will do. So this is what I've been working on together with Sandro, and we have a paper on the archive that explains at least part of this. So we're working with a path integral where the idea is that the outcome, which is actually realized in nature, should optimize the absolute square of this Z. So I know this looks a little bit like the normal Feynman path integral, but what you calculate in the end is not a distribution of outcomes for which the square of the amplitude gives you the probability, but really what you want to calculate is just what is the most optimal outcome. And this, by postulate, is the one that's actually realized in nature. And so what you integrate over in this path integral are not classical paths in space-time, but they're paths in Hilbert space. So you have a state that's quantified by those coefficients, and then you integrate pretty much like in the normal path integral over all possible combinations of those coefficients. And if you just look at this exponential, you'll see that the first term, which you have here, is basically kind of like an expectation value around the Schrödinger equation. And if you squint your eyes a little, you can probably guess that this first term is going to be optimal if this is just 0, which is exactly when the Schrödinger equation is fulfilled. And indeed, what we show in our paper is that this is exactly correct. If the second term, which I just called vaguely quantumness here, if this term is not there, then the first term alone will give you back quantum mechanics exactly. And when I say exactly, I actually mean exactly. There are no correction terms, because as I said, the only path that's actually realized is the one optimal path. And once you have this, there are by definition no more correction terms. Of course, reproducing quantum mechanics is not what we wanted to do. We wanted a dynamical process that would actually switch over from the Schrödinger evolution into a collapse-like process locally. And this is what this quantumness term here is. Basically, what it should do is that it should introduce a damping for all final states that are very non-classical, like, for example, a superposition of two detector outcomes. So whenever the normal Schrödinger evolution would go into such a state, then the outcome should be very non-preferred. And this creates a situation in which you have to weigh the disadvantage from going off the Schrödinger evolution into a state with lower quantumness against staying on the Schrödinger evolution, but then with the punishment of going into a state that's very non-classical. And then the question comes down to, well, what's this thing that we call the quantumness? And that's the same question again, like how do you quantify the deviation from quantum mechanics, to which I don't really have an answer. We've tried many different things. One obvious thing that might come to your mind are certain measures of entanglement. The problem with all those measures is that they're computationally extremely difficult, and if you put them into a path integral, you can't calculate anything, and that's pretty much the end of the story. Yeah, so that's pretty much where we are now. I'm coming close to the end, but I want to spend a few final words on the possibility of experimental test. So you can't test superdeterminism with Bell type experiments, because the only thing that measuring violations of Bell's inequality tells us is that at least one of the assumptions of the theorem must be violated, but they can't tell us which one. So in my mind, really the only thing that all those measured violations of Bell's inequality have told us is that statistical independence is actually violated. So what can you do instead? Well, keep in mind what I told you earlier, that all those theories have to be nonlinear and they are quite possibly chaotic, just because it's evidently difficult to see anything beyond quantum mechanics. So quantum mechanics is the long-term average, and in the limit where the theory is chaotic, that's the best we can do. So this little GIF, which I have there in the corner, it shows double pendulum, and what you should see is that for the first couple of seconds, those two pendula look almost exactly the same. So they start out with initial conditions that are so similar you can't tell the difference, but they were not exactly the same. And so after some while, they diverge from each other and they become entirely uncorrelated. And what we observe in quantum experiments at the moment is always this regime where two pretty much identically prepared initial states have already become entirely uncorrelated. And what you want to do is you want to reach a regime where two identically prepared states, identical to the extent that you can manage, are still correlated. So to find evidence for this deterministic part of the evolution, you have to closely control the initial conditions. And that, importantly, includes the detector. And also, to say the obvious, it would be a benefit if you measure really quickly before too much noise happens and too many things wiggle, and that basically washes out all the correlations. The detailed predictions depend on the model. I made some fairly vague, admittedly, estimates 10 years ago, in which I derived some constraints on the size of the system, the number of atoms, and how quickly you have to measure at which temperature, and so on and so forth. For all I know, no one's done the experiment or any related experiment. But I think it's technologically, it's probably feasible to push into a regime where you could plausibly see these deviations. The reason I find this very promising is that this is a parameter space which you can test from both sides. You can, on the one hand, you can make your detector and transformation devices and so on, you can make them smaller and smaller and smaller. So this is the Heisenberg cut from the one side. And on the other side, you can make your prepared state, the thing that you're trying to measure, larger and larger and larger. And at some point, they'll meet in the middle. And so you can just scan through the parameter range ideally. Of course, we're not there yet, but the technological trends are coming in from both sides, making detectors smaller and making quantum objects larger and larger. So you can make a fairly model-independent prediction for all superdeterministic theories, which is that, well, after all, the deterministic and identical measurement setups will lead to identical measurement outcomes. This is not the case in quantum mechanics. So what you do is, concretely, you look for an autocorrelation in a time series of measurement outcomes that, according to quantum mechanics, should be uncorrelated. And generally, this will require small cold systems in which measurements can be repeated in a rapid sequence. So before I come to an end, let me maybe just say a few words of what's it good for? Well, if quantum mechanics is not fundamental, then all the bounds and inequalities that we derive from it also aren't fundamental. And this means that the limitations that are posed by the uncertainty principle can be overcome if we figure out how this underlying theory works. And this brings me to my end. In my opinion, superdeterminism is our best chance to make progress in the foundations of physics. Thank you for your attention.
Thank you very much, Sabine Hossenfelder. So this was a wonderful talk. Actually, we have time to ask questions in the chat line. So one question, your Onur Pusuluk, you can state your question or I can read, okay? So he asked, can we say superdeterminism is a theory which is local in space but non-local in time? This is the question posed by one participant. So another question, is there a relation between superdeterminism and the two-state vector formalism of quantum mechanics?
So is it non-local in time? I don't think so. I'm not sure why you would think that. Of course, it kind of depends exactly how you formulate your space-time picture to begin with. Like, as I said, 2 likes the idea that both space and time are discrete. And you could say, well, if you have discrete time steps, then that's kind of non-local in a sense. But yes, so I guess I would say it depends on what you start from. Oh, and the other question about the two-state vector formalism, that's an interesting question. As I said, I was at a conference last week where we talked about different ways that people have used the word superdeterminism, and one of the talks was about the two-state formalism. My brief answer is, I suspect the answer is yes, but I don't know exactly, but I'm hoping to look into it closer in the future.
Okay. Thank you very much. Also, I wish to ask a question. So in your toy model, you include the Planck's constant. Planck's constant, okay, we know it comes from the quantum mechanics. So in a way, quantum mechanics helps us to shape the superdeterminist model. So at the end, the quantum mechanics turns out to be an emergent phenomena, and then the Planck's constant comes from your first equations from the theory.
So of course, it would be great if there was a way to derive Planck's constant. I guess I'm not that ambitious. I quite like quantum mechanics, honestly, and I think my strategy is that I start with the quantum mechanics that we all know and like, and then I try to go beyond this by adding something to it. As I've said before, I have a background in particle physics, and that's what they do in particle physics, is they talk about phenomenology, physics beyond the standard model. You take the standard model, you add something to it, and basically I'm doing the same to quantum mechanics. So I would call this phenomenology beyond quantum mechanics. So H bar is still there, but then, as I said, you need some new parameter that quantifies the deviations from that, and I don't know what this parameter is. But yeah, I mean, you know, other people have other opinions about this, and maybe there are some people who are more clever than I am, who can figure out how to actually derive it.
Okay, thank you very much. So let me check. Is there any other question? It seems to be no other questions. Okay.
I see someone's raising their hand.
Their hands, yes. Okay, I cannot see. So please. Okay.
Yes.
Yes, Ivan.
Yes. Well, I want to ask something. I sometimes don't see why the Epr paradox is supposed to be a paradox, because it is formulated in terms of non-relativistic quantum mechanics. And then we say, oh, superluminal communication. But if you are non-relativistic, then why? I mean, theoretically that doesn't seem to be a contradiction. I mean, the problem is the theory is non-relativistic, it seems to me. What am I missing? That's the first question. And the second question is, since you are changing or let's say expanding, whatever, quantum mechanics, what does this change about the ideas related to quantum gravity?
Yeah, so about the Epr paradox, I guess you're referring to the original version that's in the paper. Right,
yeah,
so like, yeah, historically, yeah, of course, I guess this is a criticism which you could level at this approach, but of course we know today that just going to relativistic propagation of particle doesn't solve the problem. I mean, this has been checked forwards and backwards. so actually, it's quite interesting historically, the way that this paper seems to have come about is that Einstein was talking about the collapse of the wave function in a single particle experiment. He was just saying, well, let's suppose you have a photon and the photon, the wave function of the photon expands spherically. And then you measure it at one particular location. So suddenly the wave function collapses, and that collapse has to be non-local, because now you know if the photon is suddenly in this one on this one side, then it's not on the other side. And just in quantum mechanics, that happens instantaneously. So of course Einstein would worry about it. You actually don't need the second entangled particle. I think the reason this came in later in the paper he wrote with Podolsky and Rose, but I'm really just guessing there, you know, I'm not a historian, is that in the single particle example, it's kind of a little philosophical, what actually is the thing on the other side if there was no particle there. So I think this is how it came about. So if you think that the collapse is actually a physical process, then it has to be superluminal. And then there was this whole Einstein-Bohr debate where they argued back and forth.
But I mean, if you are not arguing relativistically, then superluminality should not be a problem, it seems to me.
That's right. But what I'm saying is that even if you're arguing relativistically, it's still a problem.
Okay.
Okay, and about quantum gravity, yeah, that's a very interesting point. I've worked on quantum gravity for some while, and to me, this is one of the motivations, is the problem of combining quantum theory with general relativity. I think that having a local description is certainly going to help. If you look at any of the current approaches to quantum gravity, at least the ones that I know of, they just say nothing about the measurement process. If they say something about it at all, they're at least to the extent that I know all many worlds people and believe that this doesn't happen to begin with.
Thank you.
Okay, thank you very much. So I think the time is over also. So we thank Professor Sabine Hossenfelder very much. It was a wonderful talk. So she forced us to rethink about the quantum mechanics, okay, from the very beginning. Thank you very much. So bye-bye, see you. The third speaker of the first session is the Vyacheslam Kanov. Okay, so I think he is present.
Yes, I'm present,
okay,
but
wonderful. Yeah,
I have to share the screen. So.
Yes, okay, but let me say a few words about your CV. So, Mukhanov is a theoretical physicist at the University of Munich. He is well known for his outstanding contributions to theory of quantum origin of the universe. He predicted that the spectrum of the inhomogeneities in the universe originated from the initial quantum fluctuations. So today it is well understood experimentally by measuring the cosmic microwave background temperature fluctuations, of course. And later he has developed the general consistent quantum cosmological perturbation theory. For his eminent works, he was awarded by many prizes. Let me list them: Tomala Prize, Blaise Pascal Chair, Amaldi Prize, Gruber Prize in Cosmology, Max Planck Medal, Dirac Medal. So it is a great pleasure and honor for me to invite Professor Mukhanov to give his talk on discrete geometry. Yes, please, it's your time.
Wait a minute, I have to share my screen.
Yes.
Okay.
Not yet.
Okay, so okay.
Yes, it is great. Yes, wonderful. Yeah, BC.
Okay, very good. So the title of the talk, in fact, should be discrete geometry, and okay, because more mathematical than about physics, but because, as we know, gravity is geometry, therefore I could use also discrete gravity, and this is the paper which the work which I did with Ali Shamsidin. And before I will start, okay, let me blah, blah, blah a little bit, because everything else will be just mathematical formulas. I recall that when in 2003 I was visiting Bryce David, he told me an interesting story. He says that he made poll among mathematicians, asking them, differential calculus is the invention of people or it's there, given us by God. And he said that the result of this poll was 50%, 50%. I told him perhaps good mathematicians said that it was given us by God, and bad mathematicians said that it's invented by us to solve, instead of equation finite differences, okay, differential equation, which is much more easy. But now I'm not very sure at the fundamental level that it's the case, because as you understand, when we speak about Planckian scale, then it's hard to imagine that they have substructure in the Planckian scale, or we have some substructure. I will go to this a little bit later. First, let me, with first transparency, remind you a little bit things which perhaps you know about lattice gauge theory, which was suggested by Wilson, who just took, discretized the space, normal flat space by these rectangulars, and then associated with each mid of this placket, okay, if I will take this particular placket, what is called gauge field, which is the element of the algebra, and then he introduced, okay, unitary matrix. A is the scale of the placket, the size of the placket, and then you could easily construct the object which would be gauge invariant, or better to say, which would respect explicitly gauge redundancy, because it's not invariance, it's redundancy in some sense for those people who distinguish it. Because then you take 4 unitary matrices, okay, multiply them, then after that make gauge transformation, multiplying at each corner by unitary matrix, okay, which depends on the corner, and it's clear that this kind of object is gauge invariant. After that, you integrate over all these plackets, you make path integral, but it's some kind of theory which has this local gauge UN invariance on one hand. On the other hand, in the limit when the size of the lattice, I mean, here the size of the placket goes to 0, in the leading order you reproduce normal Lagrangian for the Young-Mills fields, SUN Young-Mills field. You see, but nevertheless, I have to stress it's not just discretization for computer simulation of the normal gauge theory. It's actually something more, because in this theory you can prove things which impossible to see directly in the continuous theory. But here you could think about it as about some kind of tool of studying the gauge fields, okay? Also, you understand that introducing this construction, you violate somehow invariances which were present in the original theory, like rotational invariance theory. So for the gauge theories, I do not see actually, besides of practical need to do this kind of procedure, but when we go to the gravity, then the situation becomes a little bit different, okay? And why I think actually this lattice gauge theory has more justification in some sense, because in physics, what makes sense, only what you can check experimented, right? And when we speak, for instance, about normal quantum field series in Minkowski background, sometimes we are integrating overall momenta up to infinity, without taking care that in the Planckian scales, everything is violated. Because if, for instance, if you believe really in the quantization of the gravitational field, that was experimentally proved in cosmology that it's really the case, and if you would consider small perturbation of the metric around Minkowski background, put head here on this small perturbation, then you will find that because of quantum fluctuations, okay, this H in the scales smaller than the Planckian scales becomes larger than unity. And therefore, to speak about smooth Minkowski space at the moment larger than, for instance, larger than the Planckian scale, doesn't make too much sense. By the way, actually also with this subject or with this kind of things is related so-called super Planckian problem in cosmology, which now people use for this swampland or God knows what, because if you do technical consideration, for instance, of these quantum fluctuations in expanding universe, then it looks like the scales which had scales which are smaller than the Planckian scales are stretched to the larger scales. This is the reason for writing a lot of papers, what will happen if you will change, for instance, dispersion relation and all these linearized equations as the scales larger than the Planckian scale. But all these kind of talks, actually, they do not make too much sense, as you understand, because as we see from here, there in sub-Planckian scales, you cannot make even linear perturbation theory because everything that comes in so-called strongly coupled regime. Therefore, there is other things. You could ask question. In principle, how could we check in experiment what happens in these sub-Planckian scales? Of course, natural thing is to take two particles with the energy or with the frequency larger than the frequency which correspond to Planck scale and collide them. But you know, in such a case, you will form immediately, if it's not, for instance, if it's collinear collision like this one, okay, face to face, you will form black hole with the size, with the radius, which is larger than the Planckian scale. If you want to check what is happening there, you have to fly there. You know that you cannot fly there in principle, and also inside black hole, you will face again the same problem. Okay, what happens with this kind of super Planckian collisions? As we know very well, in quantum field series, there is infinite number degrees of freedom in sub-Planckian scales. And okay, momenta can go to infinity, and it saves us from a lot of problems. For instance, when you have inflationary expansion, okay, you can always take the number degrees of freedom from this infinite reservoir, stretch them to the larger scale, and there is no problem with multiplication of the number degrees of freedom. Because, for instance, in inflationary cosmology, you can start with the universe of the Planckian scale, and then during very short time, you can produce universe with huge number degrees of freedom. You see, but of course, there is no problem, for instance, to increase the number degrees of freedom. If I will take this pencil, will break it, I will not do it in real time, yes, and you understand that the number degrees of freedom will increase immediately. Therefore, the increasing of number degrees of freedom is not a big problem, and I think actually, in spite of the fact that quantum field series, there is infinite number degrees of freedom in sub-Planckian scale, it would be much more logical and much more reasonable to have finite number degrees of freedom per each Planckian volume. You see, because you cannot do anything. Or you could think about each Planckian volume, if you prefer, as about piece of Minkowski space, if it helps you. But it's really irrelevant. The main thing that you have to associate with which elementary cell just finite number of numbers. In this case, by the way, if you consider finite volume, your quantum field theory will become quantum mechanics, just with a lot of degrees of freedom, and all distributions you have to replace, all delta function you have to replace, or you can replace by Kronecker symbols. So therefore, okay, I think that it's natural to assume that manifold is discrete and consists of elementary cell where points are indistinguishable. But immediately there appears some obstacles, like how you divide the space into the cells. Okay, you do it like this one, or you could use some curved coordinate system, even assuming that the elementary volume of each cell is not more than the Planckian volume. In this, but I think actually it should not be a big problem. Why? Because you know that, for instance, if you would consider cells in quantum mechanics, but cells in quantum mechanics which are due to the in-phase space by uncertainty relation, right? Then you can always make canonical transformation and go from one P and Q to the other P and Q, where old P and Q could be curved like this one. Therefore, we should not pay too much attention to the shape of these cells. The other things, but then next question which you could ask me, why we wouldn't take just each of these cells and replace it by point. And by the way, also actually there is also discretization of space, like Regge calculus, where you assume some intermediate structure in between and put all the curvature in the corners of these tetrahedrons. So I don't know how to call them forward. Yeah. So, but in Regge calculus, it's even big problem actually to restore after that the continuous theory, the theory of continuous manifold. And the first question, which would arise in this case, if the manifold is not continuous, how you define the dimension of this manifold? Because we know how dimensions is defined in case of continuous manifold, because in continuous manifold, d-dimensional manifold is defined as topological space for which each point has a neighborhood homeomorphic to the normal ID space, Euclidean d-dimensional space. In this case, in principle, if you would not assume that each cell has some kind of substructure, and there are only points, then for points, as we know, dimension is always equal 0 for the finite, for the manifold which consists of the discrete points. Therefore, we still should not give up with the cells, because in this case, even if I would associate with each cell some finite number degrees of freedom, nevertheless, it has neighbors and it has boundaries. And in discrete case, okay, we can define the dimension assuming that each cell has 2D neighboring cells that share a common boundary with each individual cell. Okay, this point is not a common boundary, but this is common boundary, you see, in some sense. I don't know up to what extent this thing actually can be made mathematically rigorous, and honestly speaking, I don't care. Mathematicians should care about it. Let me give example. What does that mean? But if, okay, I have discrete cells, then of course I can numerate them by set of integer. And how to do this thing? Let me consider just, for example, two-dimensional space. Let's assume that I have this cell. Everything is two-dimensional. And this particular cell, for instance, I will numerate by n integer number, by d integer numbers, assuming that my space is d-dimensional. Also, for simplicity, I always will assume that I am working with the Euclidean version of the space, but then actually how to generalize it to Lorentzian space is a different problem, okay, which has much more tricky details, which I'm not going to discuss. First, so in d-dimensional space, I have d integer numbers to numerate in each cell. Now, in particular case of two-dimensional space, you see each cell has 1, 2, 3, 4 nearby cells. And if this cell is numerated by two integer numbers n1 and n2, then it's logically to numerate the nearby cells, just increasing this integer number. For instance, this cell, when I go in this direction, will be numerated by n1 plus 1 and n2. If I go, for instance, in this direction, then I change this argument by 1. Correspondingly, for these low cells, I have minus 1. Okay, so it's more or less clear what kind of principle we use now to cover the whole discrete manifold, or to numerate all the elements of this discrete manifold by the integer numbers. So first step we did, compared to differential geometry, where you start with defining so-called continuous manifold, then the next construction, or the next element which we have to introduce in this manifold, the most elementary thing, okay, to make it more non-trivial, to define in each cell some, for instance, scalar function, or some scalar, not scalar function. It will be scalar function in continuous manifold, but in this case, it's just one number, or for the n degrees of freedom, or L degrees of freedom, it's L numbers, but let's consider for simplicity just scalar fields, and with each cell we associate one number, finite number of numbers when we have many degrees of freedom. For instance, here I can write that f can be just a scalar function. I think about it as about scalar function. Then what would be the next natural construction? For instance, in the theory of continuous manifold, you introduce some parameterized curve. And then at each point, you associate with it some operator which is called vector, tangential vector to this curve. In our case, of course, we could define some kind of curves which are connecting different cells, but nevertheless, it's because it should be local stuff, yeah, it's not so easy to introduce some replacement immediately for this tangential operator. But what we can do, we can introduce so-called shift operator, defining them like this one. When this shift operator acts on the scalar function in some cell n alpha in the direction beta, then it produces me the number in one of the nearby cells according to this rule. You see, so it increases integer in direction beta, exactly. Because if it would be beta equal 1, then it would be n1 plus 1. If beta would be equal 3, then it would be n1, n2, but n3 would increase by one quantity. So these shift operators would be considered as a basis in a linear space, d-dimensional space in each cell. They form linear space in each cell, particular cell, because you could define multiplication of each of these operators and sum of them according to this rule. You see, you are just taking this combination, act on an arbitrary scalar function, and then you produce with corresponding coefficient, okay, the number, which would be the linear combination of the numbers in nearby cells. You could also define inverse operator, just moving from cell n plus 1 to cell n minus 1, okay? You see in the direction alpha. So it means that, for instance, if this alpha would be 2, it would mean that this n, which is n1, n2, n3, n5, etc., only one number, n2 would be, from n2 you subtract 1. And for after the getting so-called limit of continuous manifold, it would be convenient for us to introduce so-called tangent operators at each point n, okay? Also, D operators in linear space, which is just sum of shift operator minus inverse shift operator, okay, divided by 2. And in 4-dimensional space, for instance, this tangent operator allows you to compare the value of functions in the cells which are both nearby to cell n. So in the cell n plus 1 and n2 minus 1. You see? So we define now analog of what is called vector operators in the differentiable manifold case, but we defined it in the case of the discrete manifold. The next construction, which is coming in the game, of course, and which we go step by step, yeah, and which has more complicated structure, is to define the scalar product. When you take two operators, you can define the scalar product which produce just some number. And among all these E operators, okay, or shift operators, you can find linear combination which are all orthogonal, okay? D vectors, D Vierbeins, which are orthogonal to each other according to this definition of the scalar product. Then after I did this thing, I can define what would be the local gauge group of my gravitational theory, which after that I want to make discrete gravity, and which is replacing this unitary group of the transformation for the gauge series. Then, of course, the natural candidate for this local symmetry group is the group of rotation in each particular case. It's like, okay, if I would consider Lorentzian group, it would be the group of Lorentz transformation, local Lorentz transformation. It means that if I go from some vector which consists of, let me call it, instead of D, Vierbeins, okay, I will call it Vierbeins, keeping in mind 4-dimensional case, or not keeping in mind D-dimensional case, but Vierbeins, okay, sounds nice, as you understand. Then, if I will take and rotate all these Vierbeins with some matrix, which is nothing more than just group of rotations, then, okay, nothing should change because it's analog of the gauge transformation. Then, if I will take these orthogonal vectors, then any tangent operator I can expand, okay, there is summation of this index, as a linear combination of these Vierbeins. And the coefficient in this kind of expansion normally are called Soldering form. For instance, you have this 16 Soldering forms, it's 4x4 matrix just in 4-dimensional case, and 3x3 matrix in 3-dimensional case. Then next concept, of course, now what I did, I define at each cell what is called shift operators and tangent operators. I define the scalar product. Then the next step, which I have to do, I have to compare this object in nearby cells. For that, I need parallel transport, as you know, in general relativity, where, okay, in such a way, there come Christoffel symbols. You just take the tangent vectors, which are tangential to coordinate lines, bring into the nearby point, and then you know that the component in the new point should be expressed in terms of Christoffel symbol. But here, situation is a little bit more complicated because I cannot make infinitesimally small shift. Here, I have to have finite shift, you see, and I have to use for this finite shift some elements of the group, but not algebra. So some kind of things which are exponentiated algebra element, and this thing I could do very easily only for these sphere binds, which are 4 orthogonal vectors in 4-dimensional space, or they can form also, I can say that it's some kind of particular subkind of non-holonomic basis. Non-holonomic means that it's not necessarily vectors tangential to the coordinate lines. In fact, actually, they cannot be tangential to coordinate lines in the curved manifold. And then what I have to do, I have to define my parallel transport. Let's assume that I want to consider here some vector, okay, from these sphere binds, which also pre-exist, with the vector operator, which is in the point, in the cell, which is nearby cell, n plus 1b. Beta is direction. Then what I do, I bring my vector before I comparing it with something what was existing here to this point. Okay, and this tells me that I define in such a way parallel transport. And then the parallel transport, in this case for finite things, is given not by so-called spin connection, like in the case when I have differentiable manifold. This is what is called spin connection, yeah? But it's given by exponentiated spin connection. You see, so it's given by this matrix omega, which is analog of the unitary matrix, and these are the group of the omega is the element of the algebra, but omega itself is the group elements. You see, and because I am considering SON group as a local group of the gauge redundancy, then of course there should come GCD, which are generators of the rotation group in the vector representation. They satisfy appropriate commutation relation. Then, of course, I could also take from this cell and bring here the tangential operator. You see, not these sphere binds. Sphere binds, I know that they are transformed by this group. But when I bring tangential vector, then I write some object which happens to be some kind of generalization of the Christoffel symbol for these tangential operators. But you do not consider, nevertheless, that this is the things which are tangential to some lines. Then I know that E multiplied by V is a scalar, and therefore when I bring scalar from one cell to the other, nothing changes with the scalar, okay, it's just invariant, it's the same number. And using this condition, I can immediately express Christoffel symbols in terms of the elements of the group of spin connections and these sphere binds. This is rather complicated equation in terms of the finite differences, because you understand that this omega is exponent of some matrices. But from here, I can see that symmetrical part of gamma at least can be entirely expressed in terms of the spin connections omega, which I introduced here, and also soldering form in the cell N and nearby cell. If I will assume for simplicity that I have no torsion in the space, so I will assume that these Christoffel symbols are symmetrical in the low indices, then I will get from here this kind of relation, again, very complicated relation. I will show you in one particular case, okay, finite different relation, because here you have exponent of the matrices, which would allow me to express omega entirely in terms of the soldering forms in the cell N and nearby cell. Under local gauge transformation, if I will take, for instance, in cell N, my Vierbein and then multiply it by rotation matrix, then, okay, after some calculations, you will find that the element of the group of the spin connection is transforming like this one. And you understand that here it involves also inverse matrix of the rotation, not only in cell N, but also in cell N plus 1 beta. So it's transforming not covariantly. You see, it's analog of the transformation law for the strength of the gauge fields, where you have UA, unitary matrix A, unitary matrix minus 1, plus unitary matrix multiplied by the derivative of this unitary matrix. So the fact that here I have nearby cell is explicitly expressing this fact that you have this mono-trivial transformation law for the spin connections. If I would consider continuous limit, then this transformation law for the spin connection would look exactly like transformation for the gauge field, but with replacement of the, how it's called this, gauge unitary matrices by Lorentz matrices or rotation matrices when I work in Euclidean version. But then if I will take not just this operator omega, but combine it like this one within one cell with the shift operator, then I will find immediately that this combination transforms covariantly. Namely, in each cell, okay, the transformation law for this operator, which is here exponent, okay, which involves also generators of the rotation matrix, multiplied by this En, okay, when I make rotation in one particular cell, then the result which I am getting for this object is like rotation matrix for in cell N, here this matrix, multiplied by inverse matrix in the same cell N. This makes me very easily actually to build some kind of scalar spin connection curvature, which doesn't depend, doesn't change with respect to this group of the local, I stress, rotations, because rotation from cell to cell can be different. Because what I do, I will just take the placket like this one, which is connecting, for instance, 4 different cells. And then I will write the product of these elements, okay, which involve also matrix or group element for spin connection, okay, inverse things, and then I have to get the tensor which will be antisymmetric in these 2 indices, therefore I will subtract similar combination with antisymmetrized indices. And I can go back and can express everything in terms of these omega matrices, which is exponent omega yod, or G, I don't remember, G, right? So G is a generator of the rotation group, then matrices in the nearby cells and inverse matrices. You see? Therefore, this object obviously is invariant with respect to local SOD transformations. And for the case of 3 groups SO2, SO3, and SO4, you could show that, okay, these horrible matrices could be reduced just to these numbers multiplied by the generators of the rotation group. So, but only in these 4 cases. In other cases, it's much more complicated. Then what can I do? Okay, there appears 2 extra indices. One index actually refers to the tangent group. The other is referring to the manifold or to the directions which are characterizing the shift from one cell to the other. Then I contract these indices, alpha, beta here is the appropriate Fairbairns, and then I am getting the scalar curvature associated with each particular cell of the manifold. You see, after that, you could tell me how could I write action for the gravity. Instead of writing integral, I just write sum over all cells from the scalar curvature in each cell, but I have actually here some kind of weighting factor which still has to be determined. And actually at the beginning I did everything in the spinor representation, then we switch to the vector representation and all these kind of calculations. And the only thing which actually I was not able to reproduce in the vector representation, this kind of weighting factor, because this factor, we found that it has to satisfy this kind of equation, again in finite differences. It looks very simple, but if you write it explicitly, you will see that it will look not so simple. From the hermicity of Dirac operator. So the hermicity of Dirac operator, when you write appropriate sum for the Dirac operator with the weighting factor, yeah, and require that Dirac operator should be Hermitian, then you will find immediately that with each cell you have to associate this weighting factor which satisfies this equation which has to be solved. Now, to show you that these formulas, okay, are not as simple as they look like, it was quite a lot of work to reduce them to simple formula. Let me demonstrate how this formula looks explicitly in two-dimensional case. So I will consider two-dimensional case where all cells can be numerated by 2 integers. In this case also matrix, okay, two-dimensional rotation, very simple matrix, and matrix, I mean, which is exponent. Exponent could be taken explicitly, so it could be this, I mean, this matrix could be exponentiated, and then you are getting that this exponent of omega multiplied by the generator of rotation group, in this case, which is very simple, is just cosine of omega alpha, one number, okay, because this spin connection has only 2 indices, and they are antisymmetric. In the upper indices, therefore, you have, okay, alpha, which takes 2 values only, but here you have only one combination, 1, 2, because 2, 2 and 1, 1 are 0. Therefore, what can you do? And here, of course, it's multiplied by unit matrix and plus sign of the same thing multiplied by this tau matrix, which I think 0, 0, 1, minus 1, something like this. But nevertheless, now equation becomes digestible, but not complete. After that, I still can use my freedom in the choice of the gauge, I mean, making appropriate rotation and in partition of the manifold in the cell to reduce all spin connections. There are 4 spin connections in this case. You see 1, 2, 2, 1, they don't need to be the same. 1, 1 and 1, 2, 2, 2 also need to be the same. But then I could use the freedom which I have to set this component to be equal to 0 and, okay, to equate these 2 Fairbairns, 2 binds in this particular case. It's the same thing as, for instance, in two-dimensional case, you know that all metrics are conformally flat or Y flat, if you prefer. So now, after that, after I wrote this thing, actually, as 2 by 2 matrix, I can solve everything. For instance, this torsion-free condition, which I was mentioning, which should allow me to express spin connection in terms of Fairbairn, look like this one. And they have these explicit solutions, you see, for omega 1 and omega 2 independent spin connections, and they are expressed only in terms of one Fairbairn, which I took like E using the freedom in the choice of partition of the two-dimensional manifold and also using rotations. Now I can take this omega and can get explicit expression for this only non-vanishing in two-dimensional case component of the curvature. And then I see immediately that it's equal to psi. It means that it cannot be arbitrarily large. So in this case, I am getting somehow automatically that the largest possible curvature cannot exceed the curvature associated with the cell. If I would take cells of the order of Planckian scales, then curvature could not exceed Planckian curvature in this case. So automatically, somehow, I do not allow in this discretized theory unlimited growth of the curvature. Now, but you could ask natural question, can I reproduce from this theory the result for the differentiable continuous manifold? And the answer, which is also non-trivial, is yes, because instead of numerating cells by n, alpha, you could multiply, for instance, this elementary cell, or the elementary distance, if you want, yeah, between two cells, by epsilon, and then can take a limit when epsilon goes to 0. But if you would keep just epsilon goes to 0, then any cell with finite n here would shrink to 0, as you understand. Therefore, limits should be taken very carefully. You have to keep x to be constant, take epsilon goes to 0, but n goes to infinity. And this is what will produce you in the limit continuous manifold. Is, by the way, not so much surprising, because take just straight line, numerate it or divide by cells, and then now make, it's unfortunately I didn't put this picture, yeah? The size of this cell going to 0, then you will see that given point of the manifold, okay, it changes when epsilon goes to 0, it goes to a different cell with different number n in discrete case. Then in this case, of course, I could again to define my shift operators according to this formula, but instead of 1, epsilon comes in the game, so it's 1 multiplied by this epsilon, small parameter. For the nearby cell, x gets continuous, and then if I will consider the limit when epsilon goes to 0, and I will take my so-called shift operator, okay, act on these functions, then I will get this kind of difference, which in the limit epsilon goes to 0 gives us the standard expression for the tangential operator to coordinate lines x. Moreover, now when I consider parallel transport, I have also to keep in mind that the size of the cell goes to 0. Therefore, I have to insert here no summation over beta, by the way, they are both in like low position. I have to insert this small parameter epsilon, and then when I exponentiate epsilon, when epsilon goes to 0, then of course it becomes 1 plus epsilon, etc. So the element of the group, okay, is in the leading order approximated by the element of the algebra. And if I would take this thing into account and go to the definition of the curvature, which I gave before, right, with all these omegas, when epsilon goes to 0, then I am getting this expression where R alpha beta A B is just normal expression which should be very well known to the people, especially those who work in supersymmetry, for the spin connection curvature. You see? And then from spin connection curvature with Vierbein, you make normal curvature just contracting with appropriate Vierbeins. Now, if I take this action, then curvature, okay, scalar curvature contracted with the appropriate Vierbeins, but then what about this factor, Vn? I have to solve this complicated equation, where it was, okay, doesn't matter, you perhaps cannot appreciate how complicated it is anyway, but this equation. And I can show you that in this limit, modified form of this equation, in this limit, is reduced to the trace of this equation, from where it follows that this function V becomes just square root determinant of Vierbein, or its square root of the metric. And therefore, in such a way, in this limit, I am reproducing Einstein action in d dimensions. So it has correct limit on one hand, on the other hand, everything is discretized. There are some kind of physical consequences, okay, of it. Equations are complicated, of course, and we still do not considering application of this thing, yeah, to the particular model. But I believe that the model is not so bad, in spite of the main question here is not technicalities, as you understand, but the principal questions like existence of some limiting curvature, etc., and it could be applied to discretized space, and we can get completely different picture, not like, for instance, perturbation are stretched from the Planckian scale, but different picture, like you start with 1 degree of freedom, and then the number of degrees of freedom are growing, growing, and growing, for instance, in expanded universe or in inflation. But per each degree of freedom, you have one Planckian element. Okay, so thank you very much. It's finished. I don't have conclusions.
Okay,
Conclusions, everybody can draw himself. Yeah.
Thank you very much, Professor Mukhanov. So it was a brilliant presentation, very hard topic. Let me check the chat lines. So there is a question from a participant, from Utku Bulut. The question is the following: could there be a benefit of the choosing triangular or hexagonal lattice instead of square lattice? Or square lattice is simply easier to use?
Yes, square lattice is more easy to use. Moreover, the lattice should be like square lattice, but you should not actually, for instance, keep the angle. It should be not like square, really. Okay, but it has to have the same number of boundaries as square lattice, because if I will make triangulations, that I will not be in agreement with my definition of the dimensionality.
Okay, thank you very much. So, are there any questions? Any hands? Raising hands? No, perhaps. So, what would you say about how can we see the effects of this discrete nature of the space-time, for example?
You can see in principle in experiments the discrete nature of space-time, because one of the ideas which I am promoting for a long time, and together with Bekenstein, that, for instance, the area of the black hole is quantized in terms of the integers of the Planckian areas. And this kind of little thing has drastic consequences for Hawking evaporation. Because even for big black hole, this assumption somehow completely deform this thermal curve for Hawking evaporation. You see, because instead of consisting of, continuous spectra, this thing, what you are getting instead of it, you are getting lines. The envelope of these lines is like Planckian curve, but nevertheless, okay, instead of Hawking spectra, you have the spectra which consist of discrete lines. We even estimated what should be the width of the lines, and width of the line should be about 3% compared to the distance between lines. And this does not depend how large is the black hole. Even for huge black hole, you have the same result. You have line structure. And if, for instance, tomorrow people would find evaporating black holes which emit according to Hawking radiation, if they would find spectra which would be continuous, Planckian spectra, it means that, okay, our idea about discrete cells of the surface area is not valid. But if they would find that, okay, this kind of thermal curve, don't forget that it's thermal curve, envelope is thermal curve, statistic is thermal. Okay, now entropy is maximum, information is zero in this case, yeah? Then it would be experimental proof of the quantization of space-time in terms of the Planckian values. And you should not be surprised that it's valid even for large black hole, because I could ask you a question. If, for instance, you would take hydrogen atom, how do you think, where you see more quantum nature, at the low levels or at the higher levels, if atom is isolated? Yeah. You know that you will see that structure becomes more quantum for the isolated hydrogen atom when you go to higher and higher levels. Why? Because distance between levels drops down as 1 divided by number of levels in power cube, but the width of each level drops down like 1 divided by n in power 5. And moreover, in astrophysics, people observed actually sharp line for the transition in the neutral hydrogen between level 140, 139, something like this one. And they see really very sharp lines. They are sharper than lines for the transition from third to second level.
Thank you very much. So, is there any other questions, or let me check the... So, okay, thank you for your wonderful talk, Professor Mukhanov. So, actually, the time is almost over. So, okay, this is the end of the first session. So, the next session will begin at the 7 o'clock in the evening. So, Ekrem Aydıner, so what would you say? Okay.
Yeah, I would like to thank speakers. All talks was very nice. Program will start after 1 hour.
Of break, yes. Okay.
Yes, yes.
So this is the break time. So thanks a lot, everybody. Thanks for the speakers. Okay. Bye-bye.
We can see, we can meet after 1 hour.
Yeah.
Okay. System will open. You can join if you want, whenever.
Okay. Thank you. Thank you very much. Bye-bye.
Bye-bye.
I guess we can start the talk after that.
Can we check if I can share my files?
You should be able to. Let's see. Okay, you should be able to. You are co-host. If you'd like, you can try sharing your screen. Yeah, it should work. Good, great. We can see. Yeah, we can see that.
How's it now?
Yeah, we can see your screen.
Okay.
Perfect.
Yeah, it's perfect.
Let's just wait a few more minutes. Then I guess we can start the session.
Merhaba herkese.
Ali, ben birinci konuşmacıyı aldım, sen ikinci konuşmacıyla, tamam? Böyle paylaşalım istersen. Tamam.
Tamamdır hocam.
Tamam.
YouTube'a baksana.
Yeah, I guess we can slowly start the session. Okay, everyone, welcome to the afternoon session of the Frontiers of Fundamental Physics. This 2022 International Symposium. Now, as before, same as before, please remain muted throughout the talk and direct all your questions in the chat. We can address them, at least some of them, at the end of the talks. So the chairs of this session will be Durmuş Aldemir and Ali Övgün. So the stage is yours. Thank you.
Thank you, Soner. Unfortunately, Claus is unable to participate in today's session due to some, inconvenience. And therefore, we would like to continue with Ali Mostafazadeh from Koç University. Let me give you a little bit information about Professor Mostafazadeh. He has received his BS degree in physics and mathematics from Boğaziçi University in 1989, and he has earned his PhD in Texas University of Texas at Austin. He has been working on quantum mechanics, supersymmetry and its generalizations, quantum cosmology, pseudo-Hermitian operators, mathematical optics, and scattering theory. And just a second. No, I would like to leave the stage to Professor Mostafazadeh. It is yours. Please go ahead.
Okay. So you see my screen, right?
We see screen, yes.
Okay. Well, I would like to begin thanking the organizers for giving me this opportunity to present this talk on geometric extensions of quantum mechanics. I'll give a basic introduction to axioms of quantum mechanics and this concept of pseudo-Hermitian operators. I describe difficulty with systems when the state space of quantum mechanical system becomes time dependent. Then I will try to show why one needs to work with Hermitian vector bundles, what the metric connections on these vector bundles are, how one can introduce the energy operator for these systems with time-dependent Hilbert spaces, and what is the geometric interpretation of it. And then I'll show that these questions lead to a global geometric extension of quantum mechanics, which is completely consistent and reproduce the ordinary quantum mechanics we know locally in the sense that I will describe, and I'll conclude with some general remarks. So axioms of quantum mechanics, throughout this talk, this curly H with index or without indices mean Hilbert spaces with some inner product, which I use the standard bracket notation for. Capital H will denote what we call the Hamiltonian. This is going to be a linear operator acting on this Hilbert space. And I'll only consider Hilbert spaces which are finite dimensional to avoid questions with regard to domain of operators, which is not really an important issue at this stage of the development of this theory. By definition, we say that this operator is Hermitian if and only if this equality holds, that you can replace H on the right slot of the inner product to the left for all state vectors, a pair of a Hilbert space with such a linear operator specifies in a quantum mechanical system because this Hilbert space determines the kinematical properties of the system. Pure states are non-zero vectors in this Hilbert space, and observables are Hermitian operators acting on this Hilbert space. There is a well-known theorem which says that if you want to have the expectation values of a linear operator to be real for all the states, then this linear operator must be Hermitian. This is the very basic reason why we choose Hermitian operators as observables of quantum mechanics. Usually we argue that that's because these operators have expectation values which are real, but the opposite is also true, and it's more important. You can't have an operator having all expectation values real and be non-Hermitian, but you can have a non-Hermitian operator with real spectrum. So reality of a spectrum is not sufficient by any means. The dynamics of the system is given by the operator H, which we call the Hamiltonian, through the time-dependent Schrödinger equation. I'll take H bar to be 1. And unitarity of evolution means that for a evolving state vector psi of t, the inner product or the norm square remains time independent. Is the derivative with respect to time of this quantity is always 0. And that implies that this Hamiltonian must be a Hermitian operator also. So one cannot avoid requiring hermiticity of observables in the Hamiltonian for this reason. Now, if we have a pair of Hilbert spaces H1 and H2, an operator mapping the first one to the second one, we say this is a unitary operator if this operator leaves the inner product invariant. That means if for any pair of state vectors from the first Hilbert space, you take U and map them to the second Hilbert space and take the inner product there, you get the same result. There is a simple theorem which says that two pairs of Hilbert space and Hamiltonian specify the same quantum system if there is such a unitary operator U, which maps the Hilbert spaces, that the Hamiltonian of the second pair is related to the Hamiltonian of the first pair by this equation. This is if and only. The reason for this is that if you take states from the first pair and map it to the second one, the observables are mapped by the similarity transformation. And if you calculate the expectation values, you get the same thing. Whether you use the first pair or the second pair, the outcome of expectation value calculation is the same. Therefore, the physical quantities that you want to compute are identical. So these two pairs of Hilbert space Hamiltonian operator are equivalent. Actually, you can identify quantum systems with the equivalence classes of all such pairs. So this would be a simple mathematical definition of a quantum system. But there's a problem here because you see, if you identify the Hamiltonian in the first representation with the green, H1, with the energy observable, then if you ask what is the energy observable in the second representation, there are two options. Either you have to say this is an observable, so the procedure for identifying observables is just by unitary transformations. Or you might say, well, why not the second Hamiltonian be identified with the energy observable? And there is a conflict because Hamiltonian doesn't transform by similarity transformation, but observables do. So how does one actually define energy observable and which one should choose? So one important observation is that in quantum mechanics, the axioms do not choose the particular Hilbert space you want to work with. And this leads to what I call pseudo-Hermitian representation of quantum mechanics. This is based on a series of theorems I proved in 2002 and Journal of Mathematical Physics papers. But the theorem summarizes those papers, which says that the following statements are equivalent. If you have an operator H which is diagonalizable and has a real spectrum, then that's equivalent to saying that this Hamiltonian is related to its adjoint by this similarity transformation, where this eta is a metric operator, which means it's a Hermitian positive definite operator. And that is also equivalent by saying that this the operator becomes Hermitian if you modify the inner product of your Hilbert space and replace the standard Hilbert space by this inner product, by this new inner product where you have eta inserted in the second slot. And that is also equivalent by saying that there is an antilinear symmetry operator, an antilinear operator which commutes with your Hamiltonian and it squares to 1. These 4 statements are equivalent statements. While this theorem has some impact, you can use it for constructing this metric operators and therefore new inner products. And this has applications in dealing with this famous Hilbert space problem in relativistic quantum mechanics and quantum cosmology. Another simple outcome of this investigation is that if you take the square root of this eta is a positive definite operator, so it has a positive, unique positive definite inner product. Well, it's Hermitian, so maps H to H, but because the identity of H and this modified Hilbert space is the same, you can view it as an operator mapping H eta, which means the same vector space with the new inner product back to H. And then you view it like that, you see that now rho becomes a unitary operator, simply because of this calculation. Pick 2 vectors in this new Hilbert space. By definition, this means that eta is rho squared because rho is the square root. And then you get one of the rows in the rho squared move to the left because this is a Hermitian operator with respect to this inner product. And you see you arrive at that. So if you map psi and phi by rho, the inner product doesn't change. So this gives you a unitary operator. And this says that you can actually map using this rho and find a new completely Hermitian representation of your quantum system. So if you have a quantum system with this inner product space, with this Hilbert space with new inner product, and the Hamiltonian operator you start with, you can define a new Hamiltonian which acts on the original Hilbert space, and these are unitary equivalent. Now, in 2007, I show a very simple result that if your inner product is time dependent, then your Hamiltonian either generates the time evolution, it either gives you a non-unitary time evolution, or you must accept that it's not an observable of your theory. So there's a conflict between unitarity and observability of the Hamiltonian operator. The reason is very simple. If you recall that the inner product of this Hilbert space is given by here, and you want this to be Hermitian, if it's observable, it is Hermitian with respect to new inner product, which is equivalent to this with the Hermiticity relation. Whereas if you want your evolution to be unitary, you want this, and this is equivalent to this relation. And you see there is a difference by the second term, which involves the derivative of eta. Eta is invertible, so these are equal only if eta is not time dependent. So people have come up with some way out of this dilemma. You can, for example, try to say that, well, I'm going to modify the Schrödinger equation. But then you can also ask, what is the energy observable? How do you get the observable, which is not the generator of time evolution? So let's just start with a time-dependent Hilbert space, which I call HT, and take an evolving state vector which moves in this time-dependent Hilbert space. Now, if you want to define the rate of change of this state vector by using the standard definition of the derivative with respect to time, you run into trouble because this psi of t plus epsilon does not belong to the same space as psi of t does. This belongs to ht plus 1. So can't subtract them. They don't belong to the same Hilbert space, a vector space. So what you can do is to replace this psi of t plus epsilon, which belongs here, by an associated vector which belongs to the correct Hilbert space. And therefore, you have an assignment of psi t plus epsilon, giving you this psi sub epsilon, which you don't know. And then once, if you can do that properly, then this makes sense. And then we can talk about the rate of change in time. And this is precisely what leads or takes you to the theory of Hermitian vector bundles. So very quick reminder of what a vector bundle is. A vector bundle is a manifold E, curly E. It comes with a base manifold M. There's a projection map which maps the bundle space to the base space. There is a vector space. I'm talking about complex n-dimensional vector bundles. So you take Cn, it's called the typical bundle, and you pick one copy of the Cn and associate to each point of the base manifold, and the totality of these so-called fibers give you this vector bundle. V sub r means the fiber over the point r. R is a point on the base manifold. I also identify with the coordinates of that point. Now you pick two coordinate patches. The bundle, being bundle, means that it's locally trivial. That means there are this, maps F alpha. These are homeomorphisms which take the part of the bundle over this O alpha to the cross product of O alpha with the typical fiber. And this is the homeomorphism, so they look alike. And if you pick one point in your bundle, V, and apply this F alpha, it gives you a point in the base manifold, this is the projected point, and some point in the typical fiber. There is a function which maps the fiber over R to the typical fiber, and this is supposed to be a linear map. It's actually an isomorphism, vector space isomorphism. And on the intersections of these local patches, you can compose, go from the typical fiber here to there by this composition map, which I call the transition functions of the bundle. And these have all the information about the topology of the vector bundle. Now let's look at a single patch and take a point in the patch O alpha. On the typical fiber, we have the standard basis of Cn, 0, 0 with 1, and the rest component 0. And remember, these phi alphas are isomorphisms from the typical from the fiber over R to typical fiber. You can use the inverse of this map to define a basis over the fiber over R, which I call psi n. Now we can expand a global section restricted to this part of the bundle. A global section means a function from the base manifold to the bundle space. And essentially, it assigns one vector in the bundle over the point. And because this little psi n's form a basis, I can expand it. And there will be some coordinates which I denote by this capital psi n's. They depend on the point at which this expansion has been done. And these are called local coordinates of this point. And we can arrange them into a column vector with n components and represent the global section over a local patch by these vectors. They are maps from O alpha, the open map, to the Cn, the ordinary n-dimensional complex vector space. Now imagine that you have a curve in the base manifold, which I call C, and at the value of t, which runs from some t1 and t2, that you get these points which are called r of t, or the values of the points that the curve gives you at the point at the time t, if you assume that this t stands for time. And also I write V sub RT as VT, so because at each time you have one fiber over that point. Now let's expand this psi. Suppose that there is a vector psi to one of these sections over T and expand it in this local basis that I defined using this capital psi. Well, if you go by an infinitesimal amount epsilon to the increase T by an epsilon amount, you again will have this kind of expansion. These are the basis vectors in this new fiber. And you remember I was interested in assigning psi epsilon to psi of T plus epsilon. So what I'll do, I take these coordinates and and bring it here, and now replace the basis vectors over T plus epsilon fiber to T. And then this becomes a vector in VT, the fiber over T, then I can subtract. And I do the subtraction, and I imagine that this thing is going to be infinitesimally, get a linear infinitesimal correction. And the general form is this. This is the time derivative of the coordinates of the curve in the base manifold. And there will be some matrices here because it's a linear operator. There should be some matrices because it's a column vector. And these psi a's are nothing but the components of a local connection one form. Capital A sub little a is an n by n matrix, which depends on R. And the connection on this bundle is a consistent assignment of local connection one forms to all points on the bundle. Now you can abbreviate this condition, which defines how you get psi T plus epsilon out of psi, by this notation where this d sub T is called the covariant time derivative. So if you use this condition that the covariant time derivative of psi should be 0, this gives you a way to move in the bundle space over the curve C and define a curve in the bundle space, which is called the horizontal lift of the curve C in the base manifold. So this is like a differential equation. If you have one point, initial point, you can integrate it, and that gives you this curve in the bundle space. And this assignment of this curve to the initial position here is called the parallel transportation. This is well-known concepts. Now, what is a Hermitian vector bundle? A Hermitian vector bundle is a vector bundle which comes with an inner product on each of its fibers. So you can take inner product of vectors on the same fiber. Remember, there is a isomorphism which takes fibers over points to the standard, the typical fiber. And you can always, this is just Euclidean n-dimensional complex space. You can also endow it with the Euclidean inner product to make it a Hilbert space. And this is going to be the Hilbert space H that I started with, standard Euclidean inner product on Cn. Now, a connection is said to be metric compatible if the inner product of a vector belonging to one of the fibers does not change if you do the parallel transportation. So you take psi and phi, you take the inner product, you parallel transport both, and you keep taking inner products, and the result is the same. Now, remember we had these basis vectors, psi n, psi m, and there is an inner product on the fiber. So you can calculate these inner products. They are labeled by m and n, which run from 1 to n. So this defines you an n by n matrix. Well, the n by n matrix defines you a linear operator from V to V by just matrix multiplication. And this eta, because it comes from this calculation, you can show it's positive definite. So it is an example of a metric operator, this eta that I introduced. Now, similarly to this connection one forms, you can identify this to this matrices, which give you the connection one form. You identify some linear operators. Matrices are linear operators, we know. And then I can use these linear operators to define a new linear operator, H sub A. This is just a linear combination of this psi A T's. Now, if you do that, you can write this condition for parallel transportation as a Schrodinger equation for this Hamiltonian operator. So time evolution is nothing but the parallel transportation. And if you want this connection to be metric compatible, then this HAs should satisfy this relation which we saw before. This is also if and only if statement. Now, let's take the typical fiber and put this new inner product with using this eta which I defined. It defines an inner product. So I'm changing the inner product over V, and then I get a new Hilbert space, which I call H sub eta. So again, there is a linear transformation from fiber, which is an inner product space, to this inner product space, which I define. Now, I just told you that this parallel transportation corresponds to some time evolution. And then you see that if you endow the typical fiber with this inner product, this evolution becomes a unitary evolution. So parallel transportation defines you a unitary time evolution. And the Hamiltonian is given by this connection, A sub A. Now, this evolution is completely geometrical in the sense that it's time reparametrization invariant. Why? Because you see, there is a time derivative here. So if you take this formula, plug it here, you'll get the time derivative here and time derivative here. So parametrizations of time don't change anything. So this defines you a geometric evolution that is independent of the rate of the change of time. Now we will view these points in the parameters, the base manifold as parameters, which determine how the Hilbert space depend on these parameters. And once you have a curve, then the Hilbert space become time dependent. And each choice of this connection defines you an evolution. And we will call this a horizontal evolution because it defines horizontal lifts. Okay. Now, suppose that I freeze the evolution. Just suppose that this R of the curve which I pick in the base manifold is just one point, doesn't depend on time. So you're sitting on the same point. On the same point R in the space, there is this Hilbert space I assign to it. And I can talk about evolutions in this Hilbert space using some Hamiltonians, which are called HE. Now, this Hamiltonian will define evolution operator, which is unitary on this Hilbert space, provided that it's pseudo-Hermitian, that this has this property. Okay. Now, so I've got some evolution here, but I can use the inverse of this map to pull it here, right? Now, because I have, the time has been frozen, there's no time evolution in the base manifold. What happens is that you get this vectors evolving in the single fiber over that point. And these are called vertical evolutions. So we have this horizontal evolutions which come from parallel transportation, and these vertical evolutions, which I can define by the choice of these Hamiltonian operators on the typical fiber and pull it back over the fibers over this point. So we propose that the general evolution in this bundle setting is done by a Hamiltonian, which is the sum of this geometric Hamiltonian, which comes from connection, and these Hamiltonians, which give you vertical evolutions. So it's a combination of horizontal and vertical evolutions. And because this H sub A, remember, because this connection is compatible, it satisfies this relation, and HE produces a unitary evolution, so it satisfies this. Therefore, if you use these two relations, you can show that this Hamiltonian, which is the sum, also satisfies this necessary condition for unitarity of evolution. So this actually defines a unitary evolution on this space H sub eta. Remember, H sub eta is the typical fiber, endowed with this inner product eta. Now, this H sub E, which generates vertical evolutions, I will identify with energy observable. So energy observable is the generator of vertical evolutions. You can quantify this metric compatible connections. Every metric compatible connection can be admit this kind of decomposition into A0, which is given by the metric, and this omega, which is some pseudo-Hermitian matrix valued one form. So eta pseudo-Hermitian means I use eta to satisfy that. And this A0, you can show it is almost like that with an extra minus sign, and these are called eta pseudo-anti-Hermitian operators. So the general Hamiltonian that I introduced consists of horizontal and vertical pieces. The horizontal piece comes from the connection. I can split it into this part, which comes from this omega, and this part, which comes from A0. And the sum of these two is pseudo-Hermitian. This one is pseudo-anti-Hermitian. And these are the definitions of what these operators are. It's not very important. So now we have the big picture. So remember, we have this curve here, and I used the inner products over this fiber bundle over M to introduce this space, which is a typical fiber with this inner product. And that is defined by this metric operator eta. I can use a square root of it to map to a completely Hermitian representation of the system, as I discussed before. Now, if you go to the to this representation where the Hilbert space is the or standard Hilbert space, n-level system, with this Hamiltonian, this new Hamiltonian is related to the old ones by this relations that I told you. It's just straightforward calculation. Now, this whole description that I gave you here, therefore reduces to one Hamiltonian little h over the standard Hilbert space that you know. So this is standard quantum mechanics. But you see all of this related for one patch of the bundle. So this is a local description of this theory, and local description is ordinary quantum mechanics. But this bundle doesn't need to be a trivial bundle. So we need to know how to go from one patch to the other patch. And this leads you to what I call geometric extension of quantum mechanics. So it involves one more ingredient, which I have to describe. If you take Hermitian operators over this vector space VR, this is an inner product space, which comes because it has an inner product. I can talk about its Hermitian operators. The Hermitian operators over this space form a real vector space, as we know. We identify them with Hermitian matrices, and Hermitian matrices form a real vector space. I'll call UVR. I denote this vector space by UVR, and then to each point of the base manifold R, I assign a copy of this vector space to construct a new vector bundle. Now, this is a real vector bundle because its fibers are real matrices, real vector spaces. So the typical fiber will be UN. Why did I choose U? Because, the vector space of Hermitian operators is essentially the Lie algebra of unitary matrices. So that's the reason I use U here. And then you can actually determine the transition functions of this real vector bundle, UVR. Again, the formulas are not very important, but this is well-defined object. So the axioms of this generalization of quantum mechanics is the same. You need a Hermitian vector bundle E, which I started my talk with. This one is going to come with some metric compatible connection A. You have to have a global section of this vector bundle of operators, so which assigns to each point of the base manifold some Hermitian operator acting on that fiber over it. And you need to have some curve in the base manifold. So these are the four great ingredients. State vectors of the system, of any system at time t, are elements of the typical of the fiber over CT of this bundle E. Observables are global sections of this new real vector bundle, which are observable omega, are sections of this thing. So they map points of the base manifold to Hermitian operators acting on the fiber over that point. Measurement axiom, the most important axiom of quantum mechanics, is left completely intact. Why? Because suppose you want to measure some observable omega, which is now a global section in some state, vector psi. So at time t, so what you do at time t, you know what CT is, okay? And you evaluate your global section at CT. This gives you a linear operator acting on the fiber over T, right? And what you do, you take the expectation values and you calculate your expectation values. The projection axiom doesn't change because it happens at a single value of time. So when you have fixed time, you have a Hilbert space and a linear operator, which is Hermitian. So you do the same thing as quantum mechanics, you know. What about the evolution, time evolution? Remember I said you need to have a global section of this bundle that plays the role of the Hamiltonian. And the time evolution is defined by this global equation. This is covariant time derivative written globally. And this H sub E is this global section that you have to have. And to define it, this dt, you use the connection. So you see all the ingredients have been used. Now, if you again restrict to one local patch, what will happen? The connection gives you local connection bond forms, which defines what this time covariant time derivative is. Locally, it's given by this. Remember, you go use this the mappings, trivialization mappings to get the local covariant time derivative, which happens to be given by this. And this is what I call H sub A. I use this global section Hamiltonian to get its local representation. That's this HE that we had before, the generator of vertical evolutions. And then what replaces the Schrödinger equation globally, locally gives you this. You see this d sub t gives you this d sub t, which has this form. So you get this term from here, from this term, and the right-hand side, this gives you ht, you get that. So you multiply I by I, you get a minus, you move it to the right, you recover the equation I started with. It says this Hamiltonian now has a geometric part and a vertical part. So the simplest example that I could work out is, because I wanted to have a non-trivial vector bundle, is a two-level system on a sphere. The calculations are quite lengthy, so I don't want to talk about the calculation, what the connections can be and so on. But you can find out all the details in this reference. And I could also work out the Heisenberg picture for this generalized geometric quantum mechanics, and this is reference on that. Well, let me conclude. To get a resolution of the problem of the identification of energy operator for a system whose Hilbert space is time dependent, we need to formulate quantum mechanics using vector bundles. This in turn leads us to a proposal for a geometric extension of quantum mechanics. Locally, it's identical to quantum mechanics. Locally means that if you restrict to one patch of the bundle, you have what you know. The dynamics is given by, the dynamics is given by generalization of Schrödinger equation to this bundle, which involves a global section of this section of the bundle of observables, and this represents the energy observable really. Locally, the Hamiltonian has two pieces, one which comes from the connection, the other one comes from the energy operator. And these, as I mentioned, generate horizontal and vertical evolutions. You can describe everything in a single Hilbert space together with this Hamiltonian locally. This is a Hermitian of Hamiltonian. It also splits into two pieces. And this is ordinary quantum mechanics. In other words, what I'm saying is that every quantum Hamiltonian that you write down actually has two pieces. One of them you don't see because you're making a particular choice, which makes this HA equal to 0. But it should be there. If you do transformations from one Hilbert space to another, and this transformation is time dependent, you have to have that. So what is open is obviously what does non-trivial topology of these bundles E and U of E that I talked about, what are the physical meaning of the non-trivial topology? They can have trivial topology, which doesn't change anything because trivial bundles can also have non-trivial geometries on them. But if they have non-trivial topology, what does that say about physics? I do not know. Well, these are again the two references I gave you, and that is all I had to say. Thank you for your attention.
Okay, we thank to the speaker. There is a question actually. Are you able to read the question?
Yeah, I can speak it. I can ask it.
Okay,
I'm
okay,
apparently co-host. So, yeah, I'm co-host. Yeah, so I understood what you did, and in fact, that is something that is also something one does in time-dependent Hamiltonians, for example, in quantum field theory in Kurtz space-times, which are time-dependent backgrounds. The construction of this bundle. But I did not understand in general, what is the physical meaning of the base space M? If I give you a physical system, can you construct the base space M?
Yeah, so it depends on what you want to do. For example, suppose you have the situation that you have a particle on a surface and the geometry of the surface is time dependent. Then the parameters which enter in the metric of your geometry give you this set of parameters. So it depends on how you want to make your Hilbert space time dependent. These are parameters which govern the time dependence of the Hilbert space.
But could I not just take the base space to be one dimensional time, and then all other, at each instant of time, then the Hamiltonian would be something specific, and it will change as I change the time. The surface, for example, has some parameters which enter the Hamiltonian, but at each instant of time, I got a value of that parameter, and therefore the base space can just be one line, right? Simple time.
Yes, it can be a line or a circle. In that case, the bundle will be trivial.
Yeah, okay, good. So the statement that I wanted to make was that, in fact, that is exactly how one does in quantum field theory in Kurtz space-time. You might be just interested in knowing that in time-dependent backgrounds, that there is a vertical component to the evolution vector field, and there is a horizontal component, exactly what you said. But the base space in that case is trivial. It is just either you can take it with time, or you can take it with scale factor, and or scale factor and its time derivatives, 2 dimensions. And so this has been something that, for example, Ivan Aguio and I have written very detailed papers on this. You might be interested in that.
Sure, thank you.
There is actually another question. Are you able to read, or should I read it to you? Onur Pusurul is asking, standard quantum mechanics can be also generalized for pseudo-Hermitian systems by using the framework of bio-orthogonality. In this case, the overlaps between the eigenstates of the Hamiltonian defines the Gram overlap matrix, which connects the dual space with the usual one. Does this matrix play a similar role with the metric you defined?
So this framework of bi-orthogonal systems, this actually the tools that I used in 20 years ago, it's completely equivalent to choosing the metric. So that the whole, what they say by orthogonal quantum mechanics is nothing else than using that, defining this eta to, so what the eta does is to map between the two bi-orthogonal vectors. You have a basis and you have a bi-orthogonal dual vector basis for that. And eta just takes one basis to other basis. And when you do this for calculating the physical quantities, expectation values, you see that you need to use this eta. So that it's nothing new. This is the rewriting of something well known in a different language, which confused many people.
Maybe Onur Pusulu can react. Is it okay with you, Onur?
Yes, Hocam. Thank you very much for your answer.
Okay. Are there any questions, any extra questions to the speaker for this interesting talk?
Dear Demir, I actually have a very naive question. But,
Sure.
So, dear Mostafazadeh, it's actually about the beginning of your talk. You did mention that, so the Hamiltonian doesn't transform by a simulated transformation between equivalent Hilbert spaces, right? So you present it as a theorem. And yeah. I presume that's a specific case for Hamiltonian, but not other operator spectrum in the Hilbert space.
That's right. The observables transform by similarity transformation.
Good.
Hamiltonian doesn't. It has an affine part.
Yeah, and I presume that's because Hamiltonian does generate the evolution between Hilbert spaces, like in a standard quantization of a given manifold. I presume that's correct, right?
Well, the time dependence comes from the fact that you're using a time-dependent operator, right, which maps between spaces.
I meant like if I start with the manifold and let's do a radial quantization, not time quantization, right? Like what's, or just pick an Euclidean manifold and choose an arbitrary direction and do a quantization. Like in other words, foliate orthogonal to that direction, right? And the Hamiltonian in that direction would generate the evolution of Hilbert spaces on those foliations, right?
Yeah.
So, and I presume that in that particular generator, let's call it Hamiltonian, we would have the similar situation that it wouldn't be related by a simulated transformation between equivalent Hilbert spaces, right?
Yeah.
Okay, so that's kind of like trivial to see, but is there any physical intuition to understand that? Why it happens this way? Or it's just a mathematical fact?
I mean, if you insist that both of them are going to give you unitary evolutions, you don't have anything else. I mean, this is the only way. The transformation comes from requiring that both these two pairs give you time evolutions which are unitary. So unitarity forces you to have this relationship.
Okay, I see. So basically just a mathematical result. Okay. Okay, thank you so much.
Can I have a question, by the way? Suppose we start with a base manifold in which Hamiltonian is just 0, okay?
Okay.
Then can we make a map of this sort to generate an Hamiltonian, for example, in the vertical direction?
Yes, you can.
Yes. Okay. I'm just trying to figure out Professor Ashtakar's question, because in quantum gravity, Hamiltonian is 0. Is it because of the triviality of the base manifold that we don't have any non-zero Hamiltonian in the vertical direction?
No, I don't think so. These are different things. So when you say Hamiltonian is 0, essentially what you're doing is to go to the Heisenberg picture, right?
Yeah, that's right.
So in the Heisenberg picture, nothing moves, so the Hamiltonian is 0. Whereas in the Schrodinger picture, you don't need to have a 0 Hamiltonian. So it's the same thing.
Yeah. So, but you can go to a frame in which you generate this Hamiltonian because there is this affine change in the transformation, essentially.
Right.
Okay.
Right.
Are there any questions to the speaker? Okay. We thank you very much for this interesting talk, Professor Mostafazadeh. Thank you.
Hello.
Hello, Misha.
Hi. So
Hi, Misha.
Hi.
It's an honor to have you here, my old collaborator. It's nice to have you here.
Yeah. Thank you. Thank you.
Okay.
So my talk is in 10 minutes, right?
I don't know. If you wish, we can start now. I don't know. It depends on you. Do you like?
We can actually start now if it's okay, for you.
So, Misha, let me read a little bit of your bio then. Okay. Professor Misha Shifman is from University of Minnesota Theoretical Physics Institute. He's a very well-known figure in this high-energy physics theory, and he has been working on quantum chromodynamics, supersymmetry, operator product extensions, flavor changing, weak decays, all sorts of interesting topics. And today he will tell us about the inception, the concept, and the second life of supersymmetry, our beloved supersymmetry. So, Misha, the stage is yours now. Okay.
Okay. Can I share the screen?
Sure, you should be able to share, Misha.
Okay. Okay. Share. Okay. Do you see the screen now?
Yeah, we see. Perfect.
Just a second. Just a second more. I don't see you. That's the problem. Maybe it's not important. Okay. Just a second.
We see you. That's fine.
Oh, now I see you.
Okay.
Now I see you, and you see the screen, right?
Yeah, we see the screen, Misha. Yeah.
Okay. Okay. Good. Good. Then let me begin with some kind of a statement. When I got this invitation to this conference to present a talk, I thought a lot about what should my talk be, whether it should contain maybe some recent works which are more technical or a broad review of the subject. And I decided that given the present situation in high energy physics, that it undergoes very dramatic changes, and given the fact that there are so many young people in the audience, I decided in favor of a broad review of a subject with some lessons to young people. So I will start with showing, maybe towards the end of my talk, I will show some relatively new results which have not been presented at major conferences so far, but it's not clear whether I will have enough time for that. Okay, I will start with the following slide where I show you the quantum tree. That's my design and my idea of how quantum physics developed. At the top of the tree is the very beginning of the 20th century. It's the inception of what is called the old quantum mechanics, the quantum mechanics of Max Planck, Bohr, Sommerfeld, Einstein's work on photo effect. So it's the very beginning of the 20th century. And then the new quantum mechanics, which started with the works of Heisenberg and Schrödinger around a little bit after 1920. So you see, it's 20 years, almost 100 years of this quantum tree. It's almost 100 years of quantum field theory, which is the basis of modern fundamental laws of nature. All phenomena we are aware of today, which have been confirmed and measured experimentally and understood theoretically, they rely on the quantum field theory. So the founding fathers of the quantum field theory are listed here. Usually 3 major papers are quoted. Bohr, Heisenberg, and Jordan 1926, Dirac 1927, and Heisenberg and Pauli, 2 papers in 1929. Of course, the name of Bohr, Heisenberg, Dirac, and Pauli are known to every student, not a physics student, I mean, not so with Jordan, although he is known in mathematics for his Jordan algebras. That's the right pronunciation, by the way, of his name, not Jordan, but Jordan, because he was German. But other than that, at least my student never heard of him, and for a good reason. He was a child prodigy, you know, a genius at very young ages. As you see, he was a founding father of QFT and a number of other important works. But in 1933, he traded his divine talent for ideology. He became an ardent supporter of Hitler, a very hateful ideology. And since then, eventually, he withdrew from physics, and his name was completely faded away. So this is lesson number 1 for young people: never trade your talents and gifts for something very dubious. Okay, now you see that during these 100 years, these three branched into 3 or 4 major branches. And we're now mostly discussing the branch on the right-hand side. This is, you see, high energy physics, which grew from nuclear physics, then particle physics, then high energy physics. And now currently it's in the process of dramatic transformation. It may the fastest to grow is astroparticle physics for good reasons. There are lots of experiments, also mathematical physics, supersymmetry, and so on. String theory branched off from particle physics in the late 1960s. It grew fast through 80s and 90s, and now its growth more or less hampered, or tempered, if you wish. There is no way to grow, or almost no way to grow. So you see it's represented on my plot by string mathematics, swampland, and mathematical physics. Now, quantum field theory, I won't comment. Everybody understands that it's one of the basic trees, and the huge and practically probably most important is the condensed matter branch, which includes all quantum chemistry, all of the material science, currently nanophysics, and again, of paramount importance and expectations, promise, is quantum computing. So I will go mostly along this branch, high energy physics and quantum field theory branch. Here on the right, you see a mushroom, a red mushroom with white spots. It's known to be almost poisonous. I marked it as PAS, PAS. It's abbreviation from post-empiric science, which to my mind is a very dangerous new development. There was a founding conference titled Why Trust a Theory in Munich of 2015, which basically denounced the main principles of physics as we knew it from Galileo and Newton, because the main thesis of this post-empiric science, that post-empiric science doesn't need any empiric or experimental confirmation. By the way, this is not absolutely poisonous mushroom, and you know, people from the north in the 9th, 10th century used a drink made of this tree to make themselves ferocious and fearless before every battle they had to fight. So it's a
quality of the reports.
In a sense, a hallucinogenic project. Okay, also on this tree, you see this arrow here in the middle. It says that it indicates 1970 approximately. So now we're right this year, we are celebrating 50 years of supersymmetry, whose a theory of quantum field theory in 4 dimensions was invented by Goldman and Lichtman in 1971 in the Soviet Union, and by Wes and Sabine in 1973 at CERN. They were at CERN at that time. Very quickly about the founding fathers. Here you see Goldman and Lichtman at around 1970. They were the first to figure out that the basic geometric conservation laws can be extended. Basic law, the only one which has been known since Newton's time, was the energy momentum conservation, and people strongly believed that there is no way it could be extended, and they proved by construction that it can be extended if conserved quantity have spin, if they are of the fermionic nature. Here you see their major relation, which we derived in a painful computation for the anti-commutator of 2 supercharges. You see Q bar and Q commute to produce the energy momentum, the energy momentum vector, given here in spinorial notation. If you want to use the vectorial notation, you have to convolute with this sigma matrix. The supercharges Q's are given here as while supercharges in the while notations. So what should I say? I should add, many people, by the way, almost all people believe that that was their not only the main, but their only achievement in the birth of supersymmetry, that they derived the superalgebra. I want to state here, which is especially important for young people, that's not true. They have also derived by a very time-consuming direct calculations the first supersymmetric 4-dimensional model, which was super QED, with even including the mass term for the photon fields. In abelian Young-Mills theory, a mass term is possible. Here you see this equation in the middle of the page is from their short article published in the Russian journal Letters to Journal of Experimental and Theoretical Physics. The terms which I crossed out are proportional to the mass of the photon. If you want massless SQED, then you don't need it. There was one minor typo, but otherwise here in the first and the second lines, you see the modern version of super QED. You see also here is the list of references. It consists only from one entry. And this entry refers Schwaber's textbook, Introduction to Relativistic Quantum Field Theory. This is an extremely, only in Newton's time, this might be the case, because they had nowhere titans like Newton had nowhere to refer to. And this is, since it was fully absolutely pioneering paper, they had nowhere to refer to. So everybody might be proud of producing a paper with only one reference, one relevant reference in the list of references. Okay, here I briefly, before I go to present Wes and Sabine, I briefly go to supersymmetric, to non-abelian generalization of SQED, which is called supersymmetric Young-Mills theory, pure supersymmetric Young-Mills theory, or sometimes supersymmetric gluodynamics. You see, it's a very simple theory. It has gluons, the Lagrangian at the bottom. It has gluons and gluinos. Gluinos are fermions. You can take them either in the Weil or Majorana representations of the Lorentz group, and they are also in the joint representation of the gauge group. And thus, the number of degrees of freedom matches. We have 2 physical degrees of freedom for gluons and 2 physical degrees of freedom for fermions, which are considered as Majorana fermions or as Weil fermions. Now, the supercharge, when applied to boson, produces a fermion, and when applied to a fermion, produces two boson. That is an important consequence of the superalgebra. In fact, this important consequence was first noted in an unpublished paper. It remained as a preprint by Lichtman, Golf, and co-author. I believe it was 1971. That if supersymmetry is unbroken, then the vacuum energy density vanishes exactly. It's the consequence of the unbroken supersymmetry. In fact, to some form, to a reduced form, the result as a conjecture was known to Pauli in 1947. In 1947, shortly after his return from the United States back to post-war Europe, he had a series of lectures, and in this series of lectures, in connection with the problem of the vacuum energy density, he noted that the bosons produce positive contribution, fermions produce negative contribution, and if they are degenerate in mass, and the number of bosonic and fermionic degrees of freedom match, then there is a consolation. And the vacuum energy density vanishes. Of course, at that time, he meant only consolation of one loop, and it was an observation which he never pursued later on. This was a kind of marginal observation at that time. Okay, so this construction was worked out by Ferrara-Zumina, as you see, in 1974, May 1974. And supersymmetry in the West was discovered in 1973. Here you see the founding fathers. Here is Wes, Julius Wes, and Bruno Zumina. As I mentioned, they have been at CERN. At that time, this was a very CERN had a huge and very active, very creative theory department. So their result, their breakthrough discovery, was immediately shared by very many people from CERN and around, spread over all Europe very quickly. And this gave rise to a whole industry of supersymmetry. In particular, I should mention Salam and his co-author Straddi. Salam at that time was in Trieste at ICTP, and he and Salam and Straddi and some other people worked out a superfield formalism which allowed one to produce supermodels on an hourly basis. I mean, it's very easy. You want a model, you get it just immediately from superfield formalism, superspace superfield formalism. Okay. Phenomenology based on supersymmetry started rather fast. I mean, already mid-late 70s, there were a number of papers devoted devoted to supersymmetry-based phenomenology. And then this number grew, I would say, in geometrical progression. Especially, it's the exponential growth started after the 1982 famous paper by Ed Wheaton. Now, yesterday I used Google Scholar to Google supersymmetry or supersymmetric. It gave me almost 140,000 references. Also by hand, I Googled Inspire, which gave significantly less, but okay, for obvious reason, because I had to do, I don't know how to do it automatically. So altogether, the truth is probably in the middle. If you calculate the number of papers produced in these years, you will roughly get 3,000 papers per year, 10 papers daily. Not so now, by the way, and I will come to this point. Now the question is why so many people embrace supersymmetry-based phenomenology, and therefore sincerely thought that this will really save our novel, advance immensely our knowledge of the world. Because at that time, the paradigm was based on the knowledge of the notion of naturalness. Every physical theory was considered to be nice and good and useful if it was natural in the sense that there was no need in parameters fine-tuning. So supersymmetry this problem, at least for the one practical hierarchy, namely the question why the Higgs mass is not at the Planck scale, but is 17 orders of magnitude lighter than that. Because in supersymmetric theories, if you set the parameters in such a way that the Higgs lies at 120 MeV, as shown here, it stays at this energy. No further fine-tuning is needed. That's the property of supersymmetry. Consolation between bosons and fermions. There is another huge hierarchy, namely why the vacuum energy is so incredibly small compared to the Planck mass. And as I said already, Pauli addressed this issue in 1947, but it remained and still remains unsolved. Even supersymmetry could not help because it was known to be broken in nature. At that time, it was believed that it was broken at the TeV scale. So TeV, one TeV is still what 16 orders of magnitude lower than the Planck mass. So this problem is still there. There is no solution to it, and probably the solution won't appear in the near future. Now I will quote myself. I will read for you this citation from Edward Wheaton's paper. It's not very well known, but it explains the enthusiasm of the SUSY-based phenomenology researchers at that time. Supersymmetry, if it holds in nature, is part of the quantum structure of space and time. In everyday life, we measure space and time by numbers. It is 3 o'clock, the elevation is 10 meters, and so on. Numbers are classical concepts known to humans since long before quantum mechanics were developed in the early 20th century. The discovery of quantum mechanics changed our understanding of almost everything in physics but our basic way of thinking about space and time has not yet been affected. Showing that nature is supersymmetric would change that by revealing a quantum dimension of space and time. Here, Witten refers to superspace, not measurable by ordinary numbers. This quantum dimension would be manifested in the existence of new elementary particles, which would be produced on accelerators and whose behavior would be governed by supersymmetric laws. This is the year 2000. Okay, 20 years have elapsed, and none of us, none of experimenters, I should say, have ever seen any traces of superpartners, despite very heavy searches, very meticulous searches at LHC, and it's highly unlikely that the current run of LHC will show something, some supersymmetry. So the general mood now among physicists that if supersymmetry is still a part of nature, it doesn't show up in the 10 TeV range, or maybe even in higher ranges. Perhaps it shows up in 100 TeV, 1000 TeV range. We don't know, but it doesn't matter because in the next 20, 30, maybe even 40 years, this could not be couldn't be tested experimentally. It's highly unlikely that a new accelerator in this range will be constructed in the current geopolitical and financial situation. So we have to settle for what we already have. So today, the general perception in the community that naturalness is gone. It was a belief. It is not something imposed by existing data on observation. And in this sense, it was on par with the belief that string theory is the ultimate theory of everything, which also dominated or had a very strong impact on the community beginning since 1985 and for the next, maybe 35, 40 years. Now, both beliefs faded away, postponed, at least postponed for some time, maybe a long interval of time. And due to this, due to the cancellation of these beliefs, and due to the unknown ways that high-energy physics have to work out today and to find out today, this post-empiric science sort of grows, and I think it produces a very negative influence on some, at least some of part of the community. We know that, as I mentioned, since Galileo and Newton, physics operated differently. The most important element of physics was experimental observation, then came theory, then prediction, then falsification or triumph, and then again. So since experiment in high energy physics now is mostly concentrated in astroparticle physics, that's where the focus of the research shifted. So anyway, the lesson number 2 for young people, that we have to live, at least for the time being, without naturalness and the ultimate theory of everything, and still continue to do physics without these two major beliefs of the previous decades. What does it mean to live without naturalness? Let me show you a picture made by Mats Strassler 9 years ago. These first two drawings illustrate natural situation when small changes in the position of this flower, of this flowers bouquet doesn't change anything. And this is the situation, as he understood it, unnatural situation where this flower bouquet somehow glued to the table. It holds on steadily, but we don't understand why it holds on and who takes care of forbidding small, relatively even small variations of the parameters from occurring. So either we just how to live with it, or eventually we develop some new deep understanding why this situation is natural. There are some trivial obvious understandings like anthropic principle, like multi-universe, and so on. Similar or even intelligent design could be mentioned in this respect, but I don't think that these are explanations. These are just these are just some kind of religions to say that we don't know at the moment what's going on. Now the crucial question to ask: does the current situation? Maybe I should return back for a while to this tree. And you see these branches, which are healthy, alive and well. They are indicated by green. Astroparticle, mathematical physics, supersymmetry, but not phenomenological supersymmetry, the one which I'm going to tell you a little bit later on. Again, mathematical physics and all of the condensed matter tree, including quantum chemistry. All these trees, by the way, I forgot to mention that they are strongly intertwined with each other. I indicated here only 4 bridges. In fact, there are hundreds of them. I just couldn't place them on this simplistic plot. And they feed on each other. Okay. So, does it mean that supersymmetry or string theory should not have been thoroughly studied? The answer to this question is no. Why the answer is they should have been studied? Remember the history of Young-Mills theory. Well, most of you cannot remember it because it was created way before you were born. In 1954, Young-Mills theory was created by Young and Mills to describe the interaction of the raw methods. These were some conspicuous resonance, as we know now, consisting as UND quarks, which had been discovered shortly before 1954. So their purpose, their motivation was totally different. And at that time, it didn't work properly. You see, by the way, I should note that Pauli also knew, Pauli discovered Young-Mills theory about a year before Young and Mills, but he didn't want to publish it. It's only can be found in a private letter which Pauli sent to Pais. The reasons why he didn't want to publish it, I know them, but I don't have time right now to explain. Maybe if a question will be asked. So the second birth of Young-Mills theories occurred only in the late 1960s. Why it occurred in the late 1960s? Because it was figured out, so 15 years passed, because it was figured out that it can be the theory of the electroweak interaction on the one hand, and on the other hand, people learned, Fadeev and Popov figured out how to quantize it in the covariant gauge. Nobody knew how to quantize it. And then, of course, in 1973 came the discovery of asymptotic freedom. So it became understood that our world is run by Young-Mills theories in general, the way we see it now. So between the first discovery, let's say 1953, and the full confirmation, it's a time gap of 20 years. So, okay, now we are talking about 40, 50 years time gap, but the mathematical structures worked out both in string theory and in supersymmetry remain to be very powerful. I'm not expert in string theory, but I will tell you today about remarkable successes of these structures, mathematical structures in supersymmetry. So, as I said, what we have to do now is to redefine our goal and just adjust our task, our everyday task, to bring them in correspondence with what physics actually is. Now I explained, this slide is already explained that supersymmetry has revealed its power in physics, but in which part of physics it showed up so significantly. Let me tell you, let me answer the question. You see, most of the field, as I said, quantum field theory is the pillar of modern fundamental physics. Whatever branch, take you condensed matter or high energy physics and even gravity, in a sense, at short distances, it is based. It is based on quantum field theory, the way we understand it now, and the quantum field theory of today is most exclusively quantum field theory at strong coupling. If the first 50 years of quantum field theory was the weak coupling triumph, the triumph of perturbation theory and triumph of QED, weak coupling expansion was combined with the symmetry-based consideration, and this all culminated with the discovery of asymptotic freedom of QCD in 1973. Starting from this mid-70s, the focus is steadily shifting towards strong coupling, quantum field theory, and it occurs not only in high energy physics, it occurs everywhere. High energy physics, condensed matter, and all other applications of quantum field theory which are used today. Now, at strong coupling, quantum field theory has much more modest advances than at weak coupling. It does have some advances, especially in two-dimensional field theory. Starting from the 1960s, exact solutions started appearing. Let me mention also a very famous Schwinger model in 2 dimensions, which is QED in 2 dimensions. That's 1969. It was solved in many different ways and gave rise to some nice understandings. But other than that, there was not so much progress, except for a fact here, a phenomenon there, mostly used on supersymmetry-based consideration. So we badly needed some tool in order to start understanding what goes on in strong coupling quantum field theory, and in particular in Young-Mills theory. The phenomenon, one of the most dramatic phenomena which sort of guided us in this direction, because of its omnipresent importance, you know, our world exists only because quarks are confined. The potential between them grows linearly, and this explains all of the hadronic world, and everything we see around is built out of protons and neutrons, and some other hadrons appear for a short time. So the first people who started speculating about that, it was probably Gross, Wilczek, Politzer, and Polyakov. That was about 73 and 74. But these speculations were more or less in the form of the speculations in terms of the any kind of advances towards formalism. Not much has been achieved. So the difference between the standard type, let's say electromagnetic force, which is or gravitational force to that matter, which is omnipresent in nature, and the linear confinement occurs among quark and anti-quark. Normal forces, normal potentials, you see here, they satisfy the Coulomb law. That means that the potential is 1 over r. The force is 1 over r squared. It falls off at large distances, and this is extremely good because otherwise our world could not have been exist. No galaxies, no separate stars or planets, no life, no nothing. Now, what happens with the quarks and gluons? This is an experimental, I emphasize, this is experimental fact. Till mid-70s, people believed, or most people believed, that quarks and gluons should eventually show up as separate objects, and they continued searches. Only in the mid-70s, people started thinking that maybe something is wrong with this idea, and they suggested this paradigm that the potential between two quarks connected by non-abelian force grows linearly with distance, the force is constant, and quark can never be separated from anti-quark, or quark from a diquark can never be separated in nature because infinite energy is needed. Okay, so the question is, do we understand this phenomenon? You may say, who cares? This phenomenon is very well established. It exists in this stage, at this stage already for what, 50, almost 50 years. We know for certain that it takes place, and why do we need a theory? I think that this is not a right thing to say. I think that the phenomenon is understood only if a mathematical theory exists for it, not a model, not a conjecture, but a mathematical theory. It's a difficult to understand phenomenon, but in order to understand its at least qualitative features to a deep level, we need an analytic solution. We need an analytic solution badly. The idea for this solution was suggested by these three gentlemen back in 1975. It was suggested as a pure conjecture, a hypothesis. You see, Mandelstam, Nambu, and Toft. This is Mandelstam, Nambu, and Toft. And they, here I want to give you, to read a citation from Toft, published in 1976. Why I want to cite it? Because it's the only paragraph in the proceedings of a very minor conference, which is almost impossible to get hold of. Toft sent me a copy of this proceedings paper. That's monopoles turn to develop a non-zero vacuum expectation value. Since they carry color magnetic charges, you see here, the vacuum will behave like a superconductor for color magnetic charges. What does it mean? Remember that in ordinary electric superconductors, magnetic charges are connected by magnetic vortex line. Now we now have the opposite. If the color charges that are it is the color charges that are connected by the color electric flux tubes. So this is now known as a dual Meissner effect, or dual, if you wish, dual superconductivity. You see in the standard superconductivity, what happens in the standard superconductivity, you see the picture. This is the dual superconductivity. In the standard superconductivity, we know that the Cooper pairs, electrically charged pairs, condense in the ground state. Since they condense in the ground state, you see, since they condense in the ground state, they don't, condensed electric charges don't tolerate magnetic fields. They push them out. Either superconductivity is destroyed or magnetic field is pushed out. It's the Meissner effect. So what happens in the nature in a superconducting sample, if it is large enough, and if you have monopole charges, say magnets of different polarity, plus or minus poles emerge into the superconductor, then the electric field has to be squeezed in a flux tube, which is known as the Abrikosov flux tube. The tension of this tube is constant, and therefore there is a constant force or linear potential between the monopole, anti-monopole poles, which is developed because of the action of the tube, of the flux tube. Now, Nambu, Mandelstam, and Hort figured out that something of this kind should have probably takes place in non-abelian Young-Mills theories, except everything is dualized. Everything electric becomes magnetic, and everything magnetic becomes electric. So it's the monopoles. I would put here monopoles in the quotation mark, because what is monopoles in non-abelian Young-Mills theory is not clear. It's not clear how to define it, but whatever they are, the monopoles should be condensed in the vacuum on the Young-Mills theory, and then chromoelectric fluxes will form, as it is shown here, and quark and anti-quark will be forever confined by the linearly rising potential or by the force. Here, these snowflakes denote condensed monopoles. And this is a chromomagnetic flux tube, which people are looking for the decades. Here is this slide. I won't dwell on it in any way, because it describes, it gives a picture. You can find it in every good text on condensed matter. It describes the phenomena of superconductivity and dual Meissner effect. You see here a sample, a superconducting pair sample. In pink are shown condensed Cooper pairs, electrons, and then two magnets of different polarities. If the sample is large enough, then the magnetic flux doesn't spread over and bypass the sample. Rather, it is collimated into a thin string of the magnetic flux with the fixed tension. Tension is determined by the mass of the Higgs photon inside the superconductivity, inside the superconductor. That was, by the way, discovered by Abrikosov when he was, these Abrikosov strings were discovered by Abrikosov when he was still a graduate student in the early 1950s. I think it was his first or second probably paper. And 50 years later, he received the Nobel Prize for his discovery. So lesson number 3: it's good to be a good graduate student, and it's nice to follow Abrikosov's example. Okay, now we need to figure out a theory in which everything electric condensate becomes magnetic, and magnetic flux became electric. This is a numerical confirmation that this indeed takes the place. This is SU2 Young-Mills theory. Experiment means latest calculation. This is a quark, this is an anti-quark, and you see here in green and yellowish, you see that some kind of object stretches between them, and this is presumably the dualized Abayakosev or some other string of this type. Now we had to wait, the community had to wait 20 years. So it's approximately the same gap as for the Young-Mills theory before supersymmetry developed, non-perturbative supersymmetry developed and was used in 1994 by Seiberg and Witten in order to find this exact analytic solution in a supersymmetric theory, which is not exactly Young-Mills, not exactly QCD, but it's a cousin of QCD. It's not first cousin, probably it's the second cousin, because it's not only supersymmetric, it has 8 supercharges, twice more than the minimal supersymmetry in 4 dimensions. And it was really, really a breakthrough paper, which rejuvenated all the efforts of people devoted to understanding of Young-Mills theories. So since I'm doing okay with time, I will say a few words what have they done and why supersymmetry played a crucial, completely instrumental role in their analytic solution. This happened because what is now known as the power of supersymmetry, power of supersymmetry, or what is known also as holomorphy, that many quantities in supersymmetric field theories depend on certain complex parameters in a holomorphic way. And to find out a holomorphic function from theoretical arguments is much easier than to determine just a function. Because if you know the positions of the singularities of the holomorphic function, and if you know their nature, then you basically know the function. So the brightest idea of Seiberg and Witten was to use the holomorphy of this extended supersymmetry. They need extended holomorphy in order to determine the position and the nature of singularities, fully reconstruct the function, and show that under certain circumstances there is a linear confinement in these theories with the magnetic flux tube formation. Indeed, the conjecture of Mandelstam, Nambu, and Hooft put forward in 1975 was confirmed in this way, and this is lesson number 3, that good conjectures are better to be confirmed by good theories. Okay, so first of all, what kind of particle content this theory has? It has, of course, as here, it has gluons and gluinos, but this theory has this theory whose Lagrangian you see here at the bottom has 4 supercharges. It has only spin 1 and spin 1/2 fields, gluons and gluinos, which was not enough in order to solve, it still is not enough. This would be, by the way, a huge triumph again if somebody learns how to solve this theory. This is almost QCD after all. Because gluons and quarks, okay, quarks are in the joint, not fundamental representations, but they're quarks enough. And if there are some progress in this theory, there are some analytic understandings on this in this theory, some bright results, but they are not the solution. And if some of you will find a solution, would be one of the greatest achievements. So returning to Heisenberg and Witten, n=1 supersymmetry turned out to be not strong enough. They used 8 supercharges, and in addition to quark and in addition to gluons and gluinos, this theory have the second gluina, which is exact copy. And the second gluina has in turn its superpartner, which is spin 0 particle, a complex scalar field. So we have gluons, we have Dirac fermions, because 2 Majoranas comprise one Dirac fermion and one complex scalar. So it is QCD, of course, but it's pretty not that terribly far from QCD. Okay, so what can we do? The crucial observation that the phi field is complex, so some can establish some particular laws of nature, some mathematical formulas as a complex as a function of a complex parameter. That's exactly what I said about the power of supersymmetry, holonomy. So this parameter trace phi squared can vary in can take any value in the complex plane. Classically, it's a so-called flat parameter. It means that there is indefinite equilibrium, and for the ground state it can take any value. And if we let him a value which is large compared to the dynamical scale, the theory is in the weak quasi-classical regime. And the solution of this theory is known basically from the old time. First of all, we know that large expectation value of phi squared provided the breaking of SU2 gauge symmetry down to U1, or better to say in modern language, the Higgsing of the theory. Out of three gauge bosons of SU2 theory, 2 becomes heavy, plus and minus, and 1 remains massless. So U1 gauge symmetry persists. And what do we get? We get exactly the Georgi-Glashow model. After that Higgsing, if we look at the theory, this is at the low energy sector, it's a Georgi-Glashow model. The famous model where the Hopf-Polyakov monopole had been first discovered in 1974, magnetic monopole. This photon emanates in the form of the magnetic field from this monopole. Okay, this is the first step. We have a theory very similar to Young-Mills, to QCD, which does have some well-defined object, which is a magnetic monopole. However, in the classical regime, or in the regime when phi squared is much larger than QCD, the monopoles are very heavy, as you understand. Very heavy objects cannot condense in the ground state. They have to be massless to be able to condense. Now, the brilliant point, or a key point of Heisenberg and Witten investigation is that they use the power of supersymmetry to define the so-called, to determine the so-called pre-potential in this supersymmetric theory. This is the kinetic term. Pre-potential is the kinetic term in front of the gluons, in front of G mu squared, and then exploring this analytic function as a function, they found that at 2 particular values of phi, the theory is special. There are some massless objects which develop in this theory, and they identify this massless object as monopoles. because they were continuously traceable to the Hopf-Polyakov monopoles at weak coupling. These 2 points, the Seiberg-Witten points, are of course at very strong coupling, at the strongest possible coupling in the theory. So in this theory, they found 2 points on the vacuum manifold where the monopoles are massless and are ready to condense. This is already almost infinitely close to what we need. Now, okay. Now what they have done, they introduced a small breaking of supersymmetry from 8 supercharges to 4 supercharges. They dualize this theory. You see, in supersymmetric theories, the dualization can be readily achieved. So they could have replaced everything E to everything electric into everything magnetic. It turns out that under this small deformation, the theory is exactly solvable analytically. Monopoles do indeed condense, and the flux tube between heavy probe quark and anti-quark, which in the original theory, it's chromomagnetic flux tube, does indeed develop. Thus, the dream of the 25-year-old dream of the theory community to have some analytic understanding of the confinement phenomena came true. And it only became possible because of supersymmetry. So far, there is no other tool which would allow one to produce such types of theories and strongly coupled Young-Mills and non-Young-Mills theories. Okay, now my time is running up, but I still have a few minutes to make some other remarks. So as I said, people tried very hard to reduce the degree of supersymmetry and to proceed from the Seiberg-Witten theory to this theory, the minimal supersymmetric theory, which was known long ago, which is very, very close. If this would be possible, then it would mean that people are approaching to QCD proper. And many discoveries have been made on this way due to the power of supersymmetry, the power of holonomy. I don't know which one to show to you. I wouldn't be able to show all of them. For instance, I can show you as an example of the discovery what have been found in N=1 supersymmetry, the simplest supersymmetric Young-Mills theory by George Duvalli and myself, is that this theory supports domain walls of various types. And not only it supports domain walls, it was shown by Witten a little bit later that in terms of string theory, these domain walls are D-branes of the string theory, but in super Young-Mills, they of course appear in flesh and blood as a composite objects, definitely at very strong coupling. But despite the strength of this coupling, that it's deeply strong coupled theory, the tensions of this domain, the tension of this or all other tensions of all possible domain walls in this theory are calculable, and not only calculable, they are exactly calculable. That's an example. And this, by the way, that's one of the example of the power of supersymmetry. Is it the full solution? No, it is not. Does it add something new to our understanding of the strong coupling dynamics? Certainly it does, because similar discoveries were made in many other theories as well. Another interesting phenomenon which has been revealed due to the supersymmetry, it's called 2D 4D correspondence. Okay, what does it mean? Here I show you an example of it's not chromomagnetic flux tube, but a certain theory. I won't go into details. This is a theory from the same class as Seiberg-Witten theory. You see here the authors of this finding. This theory has a strong, well, it can be solved. No, this theory, it can be shown that at this theory, at strong coupling, there exist chromomagnetic flux tubes. What is interesting and important, and those are the first solution, the first finding of this type, that the flux tubes there are two types of them. If we're considering SU2 Young-Mills, there are two types of the flux tubes. In SUN, there would be N types of the flux tubes. They are exactly degenerate in mass, and therefore, being exactly degenerate, there can be a transitional domain between them. Here on the plot, you see two such flux tubes. On the left is the first type, on the right is the second type. Energetically, they're totally degenerate, and this is a transitional domain which is known as a kink. In this, the mass of this kink can be determined by supersymmetry, and then here comes this 2D 4D correspondence. The theory, the theory which appears here, the theory of the kink, if you view it as a theory on this flux tube or string wall sheet, it's strongly coupled. It's strongly coupled CP1 model. It's strongly coupled at theory V. But because it's a two-dimensional model, it's exactly solvable. So people know the mass of the super kink in this model. Now, let's look at this solution in 2 dimensions from the 4-dimensional perspective. In 4-dimensional perspective, we have a physical kink made of flesh or blood, made of a 4-dimensional Young-Mills theory. And how do we interpret this kink? In fact, using the power of supersymmetry, one can show that this kink, which doesn't look at all as a monopole, as a Hopf-Polyakov monopole, has nothing to do with that, in fact. Well, if you look at the mathematical expression, in fact, this is the descendant from the Hopf-Polyakov monopole, which in this model is confined. It's eternally attached to 2 strings, one from the left, another from the right. This would be absolutely impossible to do. This is an interesting phenomenon, absolutely impossible, inconceivable, if you don't have the string theory, if you don't have supersymmetric theory, which allows analytic transition from weak coupling to strong coupling regime, because in this theory we can start from weak coupling, where we have just the Hopf-Polyakov monopoles with no string attached, and then start changing a complex parameter adiabatically. The function which governs this change is analytic. We bypass all singularities, and we come analytically to this plot at strong coupling, where instead of the Hopf-Polyakov monopole, you see at the center a kink, 2 strings attached to them, and CP1 model on the string wheel sheet.
Dear Shifman, since we are running out of time, could you please wrap it up?
I'm wrapping up. That's the last transparency.
Thank you.
And then very short conclusion. So you see here a mathematical formula with the solution for the mass of the king. It's logarithm of square roots, not something terrible. But the point is that into the one and the same mathematical expression, analytic, it's the mass of the king in 2 dimensions and the mass of the 4-dimensional monopole in 4 dimensions. Okay, now I come to my conclusion. I'm sorry, I still have a minute. First, conclusion that Young-Mills theories run our world. Today, at a fundamental level, we don't know any alternative to them. Second conclusion, supersymmetric Young-Mills theories are alive and well. Results ensuing at strong coupling proliferate. A large variety of exact results in 4D, 3D, and 2D theories, including mass spectrum, exact beta function, etc., help us to unravel mysteries of strong coupling in non-supersymmetric theories, although there is a lot to be done in this direction. Thank you very much. Hello?
Durmuş Hocam, could you please unmute yours? Okay.
I'm sorry, I cannot
Thank
hear.
you for this wonderful talk, comprehensive talk. Are there any questions to Mr. Shifman? Any questions?
Yeah. Can I ask a question?
Sure. Please go ahead.
Yeah. Okay. Misha, it was a wonderful talk as usual, very, covering many developments. But I would like to understand your viewpoint a little bit better. I'm very sympathetic with the idea that even though supersymmetry has not been discovered or is not likely to be discovered in the next 2 decades, as a mathematical physics endeavor, it is something that should be continued. But I would like to sort of say that, for example, another example of a mathematical physics endeavor would be dimensional regularization or Euclidean quantum field theory. Our real world is not Euclidean. We live in 4 dimensions, but they are very powerful techniques which enable us to do something about 4 dimensions. Except that in those cases, we finally, take the limit epsilon goes to 0 in the dimensional regularization. We do weak rotation here in the Euclidean sector to get to the physical theory. Unfortunately, here we don't seem to have a way of turning off supersymmetry and get the results we want to get. So why could it not be that, in fact, these fascinating ideas of Mandelstam, Tauf, Nambu, they gave us some intuition, but why couldn't I take the point of view that was more like old quantum mechanics, where we had the pictures of electrons orbiting around the nucleus, and that was kind of fine, but we shouldn't take it too seriously. They are good intuitive tools, but we should not try to really show that the electron goes around the orbit. What we had was just the Heisenberg Schrodinger model of atom, Pauli or Schrodinger model of atom, and that's physics. So here, why couldn't I take the attitude that I forget about supersymmetry? I just do lattice QCD. I predict the spectra of the masses of all the protons, etc., and that somehow is physics. And why should I go and try so much to reproduce the intuitive features?
I understand your question. Let me try to answer. First of all, I do not want to diminish the role of numerical calculations. For the mass spectrum, for some other quantities, mainly for static quantities, numerical calculations, numerical simulations on the lattice finally reached the level of practical importance. The numbers are reliable. You can use them as predictions for future experiments and building block of your models and so on and so forth. However, you still don't understand in this way basic regularities, because numeric calculation is always a numeric calculation. It's limited in scope. And therefore, each time you need, you discover some new phase of the given phenomena, or you change a model a little bit. For instance, sometimes let's say you introduce temperature, okay? Or another example when numerical calculations are not so useful, if you have a hierarchy of quarks, massless, moderately heavy, and very heavy. It's very hard to deal with this numerically, because each of this element of the hierarchy introduces its own analytic features. You need to be able to change the parameters and in order to understand what's going on. Now, therefore, I truly believe that the more we know analytically, the better. The closer we approach analytically to the nature is the better. But you are right, in a sense. Take, for instance, turbulence. Turbulence is a classical phenomenon, okay? Had been discovered long, long ago. Navier-Stokes equation was suggested 150 years ago. People struggled, really struggled, and continue struggling to this day to give some analytic theory, to develop analytic theory of turbulence, which is a much simpler phenomenon. However, there is none. There are numeric calculations, but look in the window and see. We cannot, with analytic calculation, we cannot predict the weather in turbulent situations for larger than reliably cannot predict for 2 or 3 days. I look in the newspaper, I see the prediction for tomorrow. Next day, I look in the window, I see totally different. Why is that? That's the drawback, the negative side of analytic calculation, okay? So should people stop thinking in favor, should stop thinking about doing something analytically with turbulence? I don't think so. They cannot develop a theory, they try a model. Let them try a model to do it as analytically reliable as possible. They still have some progress to make. Do they have to stop doing numerical calculation in anticipation of the future analytic progress? No, I don't think so. We do what we can. Nature is very complicated. I gave to you an example of classical phenomena, much, much simpler than quantum phenomena. And we still have to work from every different side in order to become closer to the final answer, to reliable and exactly. You know, Feynman once told that if we wrote somewhere that if you have a home assignment to solve a problem and you are smart enough to solve it in a different way, in a number of different ways, you can ignore the ways which you which look less aesthetical and solve it in the most aesthetical way you can. But in real life, in the attitude to real nature, we don't have this luxury because it's too complicated. It's not for certain that we will always know everything in the real nature as we now. And this would be good, okay? Assume that another Feynman's prediction or option, that the ultimate theory of nature is done. Like in geography, we discovered all pieces of lands in the ocean, including rocks. What is there left from science then? Going to become historians or not? We are.
I think we are on the same wavelength. I'm perfectly happy with you. That my view is very similar to what you're saying. But I think you would also agree that if in fact, there was a mathematical physicist by name Balaban who at one stage thought that he actually had using mathematical techniques, rigorous mathematical techniques, proof of confinement. It didn't really work out. But if something like that happened without using any supersymmetry, you'd be equally happy. but it's just, I mean, as opposed to numerator.
Yeah.
Is that?
You see, they say it is better to be rich and healthy than poor and sick. Certainly, it's better to be healthy and rich than poor and sick, but that's all we have for decades, not even for years.
Yeah, thank you.
Let us thank Mr. Shifman for his wonderful talk. Unfortunately, we are not able to take any more questions, and there will be a few minutes, so break. Then we will start the next session. Okay. Thank you, Misha.
Thank you. Thank you.
Okay.
Nice to see you, Misha.
Nice to see you, Misha. Thank you very much for everything.
Thank you. Thank you. I don't see you. You see, for some reason.
You don't see me, Misha.
I don't see. I see like 50 small windows, and some of them are,
I see. I get this.
Some of them I don't know how to do. Maybe I can do it that way. If you speak, okay.
Let me see, perhaps my hands. Okay.
Okay. So, thank you. Goodbye.
Goodbye.
Demush, how are you doing?
Thank you, Qaisar. How are you?
I'm okay. Yeah, I'm at home at the moment.
It's very nice to see you here. Thank you.
See you. Yeah, we are kind of finishing our final gradings and semester.
Yeah, just like me. I mean, we are here also struggling with the students, grading, all sorts of stuff. Qaisar, I mean, it's so difficult.
Yeah, but it's coming to an end. The semester. This is the final week.
Yeah. In summer time.
Are you also finishing teaching and so on?
Yeah. We are almost finishing teaching. Then we will be able to travel around. I mean,
Nice.
Yeah. These nice times are coming.
Good. We hope so. Yeah. And maybe we can have this meeting. This is a very nice meeting. Hopefully, once again in Turkey, right?
Yeah, Qaisar, let's have it physical again in Istanbul. That would be great.
That would be, yeah. We missed you actually in the last meeting just before COVID, right? 2020.
Yeah, just because of COVID, and I mean, it took so time. But this COVID was kind of hell. I mean,
yeah, but the meeting was nice. The weather was good in Istanbul.
That time's meeting was very nice.
There was this window of opportunity, and then COVID came, of course.
Yeah, again, it was organized by Ekrem.
Ekrem, of course, Ekrem organized it, and he knows how to organize his big meetings.
Yeah. He's excellent, actually. He's excellent.
He's very good at that. It's not trivial now.
No,
any plans to come to the East Coast? Are you planning to come to the East Coast?
Well, not in this summer, but if I come, I'll let you know. Definitely, I'll be very happy to visit you.
It would be a pleasure, of course. Yeah, it would be a pleasure to see you. Yeah,
Ilya, you and you guys. I know. I mean, that would be great to see you again.
Yeah. Okay. But you are now, you're in Istanbul now at the moment, right?
I'm in Istanbul. Yes, I'm Sabancı University. This is kind of a private university. If you happen to come to Turkey, please.
I'll let you know, of course. Yeah, of course. You're not going to Suzy, are you? There's a meeting, Suzy 2022, right, in Greece.
Yeah, I know that. I couldn't attend it, but I know. They organized a Suzy meeting, and you were one of the speakers. I remember. Huh?
I believe so. Yeah.
Yeah. You are
it's the end of June. Yeah.
End of June. I'm sorry, I confused the dates. Okay, Qaisar. Yeah. You are
last week in June, basically.
Okay. Yeah. I got it. No, I passed chairing to Professor Ali Övgün. He will be chairing your session. Qaisar.
Nice seeing you again. Yeah.
Thank you very much. Nice to see you, and we are now listening.
Bye-bye. Yeah, bye-bye.
Okay,
of course. See you.
Okay, Ali. Stage is yours.
Yes, thank you very much. Welcome, everyone. Thank you for joining us for today's session. I'm Ali Övgün from Eastern University, Cyprus. Just a little housekeeping before we get started. If you have any question during the presentation, please type them into the chat box in your Zoom control panel. And we will also have time for question at the end. And I will bring them up after the presentation. And I would like to remind participants that they have also maximum 15 minutes for their presentation and 10 minutes for question at the end. Now we will turn the time over to our speaker. I would like to welcome Professor Qaisar Shafi from University of Delaware, who will speak on monopoles, strings, and gravitational waves. And Qaisar Shafi is a Pakistan-American theoretical physicist and inaugural Bartle Research Institute professor of physics at the University of Delaware, and he studied physics at Imperial College London, where he received both his BS honor and PhD. His PhD advisor was the late Nobel laureate Professor Abdus Salam, and Shafi was awarded an Alexander von Humboldt Prize, and Shafi has done pioneering research in areas ranging from grand unification to the Kaluza-Klein theories to inflationary cosmology and supersymmetric theories, and he is widely regarded as a leader in these fields. He has published more than 300 papers in research journals, among them many of the most prestigious in the field, and lectured at the close to 250 conferences, workshops, and universities. Now I would like to hand over to you, Professor.
Thank you very much for your kind invitation and introduction. It's a pleasure to be here, and I would like to thank Ekrem and all his colleagues for organizing this wonderful meeting. Since I'm using an iPad, you won't see me when I'm speaking, but hopefully this won't be a problem. So I'm going to share the content, share the slides, right? So just give me a moment, please. Let me see. Oh, there it is. Sure. Why it's not showing up. Just 1 moment. How about this one? See, doesn't want to show. What about this guy here? Okay, let me work with this one. This is almost the same talk, at least. Can you hear me at least?
Yes, now we are seeing.
You're seeing this, right? Yeah, okay.
Yes,
I couldn't find the latest one, but this is almost good enough. Should be good enough. So the title, of course, is Monopoles, Strings, and Gravitational Waves. Now, monopoles actually were invented by, if you like, by Dirac more than 90 years ago. And he basically showed that you could explain electric charge quantization if you had a magnetic monopole and merged it with quantum mechanics. And the reason this topic is so interesting is because the discovery of a magnetic monopole really would have far-reaching consequences for physics beyond the standard model. Indeed, if you could measure its mass and its magnetic charge, we would probably be able to guess the extension of the standard model gauge symmetry. We know that the standard model is a very, very successful theory based on a gauge symmetry SU3 cross SU2 cross U1, but it's widely accepted that this is a theory in which the hypercharge component is non-compact, and therefore there are no topologically stable magnetic monopoles in the standard model. So the discovery of one would really mean that you have found some higher symmetry beyond the standard model. And indeed, if we are very lucky, we could may even pin down, as we'll see some examples as we go along, as to what that extension could be. Cosmic strings, well, we know about strings and vortices from superconductors and superfluids. And of course, cosmic strings arise in realistic extensions of the standard model. Again, there are no topologically stable strings in the standard model. The discovery of a cosmic string would again provide us with immense information about the extension, possible extension of the standard model. And gravity waves are important because it took about 100 years and now they have been found a few years ago. And this has reignited interest in cosmic strings as another source of gravitational waves. So I will say a few words about that. And just for completeness, I should mention, I mean, there have been many collaborators of mine over the past years, but George has been working with me for a long time. We both studied with Abdul Salam. Tom Kibble, unfortunately, has passed away, did pioneering work in cosmic strings. Tanya Vachaspati, I will mention some work we did about a year ago with him. And Rinku Maji is a postdoc in India. And without him, I think our work related to gravitational waves and cosmic strings could not be completed. So he played an essential role in that, actually. So if in case Rinku has joined, he would be able to answer any questions you may have about it. So let's move forward. Dirac, as I said in 1931, pointed out that if you had a magnetic monopole, electric charge quantization could be understood. After all, the standard model has no explanation for it. In practice, I might be using units in which there will be a 4 pi sitting here, but that's not a confusion or anything. So Dirac said that if you have a magnetic monopole, then electric charge is quantized in units of 1 over g with n being an integer. One simple way to see this is to follow this explanation of Wu and Yang, where if you had a magnetic monopole, then you need 2 vector potentials, say in the upper hemisphere and in the lower hemisphere. And of course, the two vector potentials, let's say where they overlap, in regions where they overlap, for instance, at theta equals pi over 2, they should be connected by a gauge transformation. So basically, and of course, the 2 potentials are the same. If there's no g, if g vanishes, then they are the same potentials, vector potentials. And this leads us to this quantization condition that Eg is n over 2. So basically what we are doing is we have a sphere, and then we take an equatorial circle, and we are mapping this circle. On each point of this circle, there's a gauge transformation. So we are mapping this circle S1 into another S1 into a U1 circle, let's say. And this essentially carries over when we do a more realistic model. Now, the next big step was taken by 't Hooft and Polyakov, I believe around 1973, when they considered a toy model, basically a theory SU2 broken to U1 electromagnetism. Though of course, we now know that this is not a realistic model, it's a toy model. SU2 could be, so you could have a theory, this is a theory with W plus minus, let's say, in a photon. So it's not a realistic theory. And we can, with a suitable ansatz called the hedgehog configuration, so that the field at far away from the center goes back into its minimum, but it's otherwise pointing in this r hat direction, and you require that this be a localized solution with a finite energy. And by imposing this condition and making a suitable ansatz for the scalar field and the gauge fields, you essentially discover that there is a topologically stable solution available for you, which is a source of magnetic field, electromagnetic field, if you like, at large distances. And the monopole mass is related to the symmetry breaking scale and then 1 over alpha, and the size of this, the core, there's a core here in the center, and then far away there's the B field. And this is the topologically stable solution, basically, and which has a size of, so you balance essentially the magnetic field outside the core with the gradient energy, and so it gives you a nice field configuration. Note that this is not the case for for the Dirac monopole. In that Dirac monopole case, it's ill-defined in a way, unless you can tell us what the U1 field is, because in the standard model, the hypercharge field is sort of the gauge group is non-compact, if you like. Now, the monopoles become important when you look at unified theories. Now, unified theories are a very plausible, realistic looking extension of the standard model. And they have many interesting properties that I won't discuss today. But one of the most important one is that they have electric charge quantization, because the gauge group is compact. The electric charge generator is part of this gauge symmetry. And so the electric charge is quantized. This would make Dirac happy because, in fact, even though the electric charge is quantized for a different reason, these theories all predict the existence of topologically stable magnetic monopoles. In practice, the monopole is a little more interesting than the toy model of 't Hooft and Polyakov. And their mass, again, is about an order of magnitude larger than the symmetry breaking scale. This is the case, typically, if you have a spherically symmetric solution. And a good example of this is provided by SU5, which breaks to the standard model, SU3 cross SU2 cross U1. Now, normally we think of this as a global direct product of three gauge groups. These are topological spaces, but in practice, once you embed the standard model in SU5, basically there is this, there are 3 points on the, in SU3 space, topological space, if you like, that are common with the U1 electromagnetic circle. So U1 circle and then this SU3, and the monopole mass again turns out to be this related to the symmetry breaking scale, essentially. So that's what happens in this. So in other words, the mass of the monopole would depend on the kind of gauge symmetry you are talking about and the scale at which the gauge symmetry is broken. So basically, what we are saying is, if you have an SU5 monopole, you break it to the standard model. This is a bit sloppy. I mean, this is SU3 cross SU2 cross U1 divided by Z6 or something like that. And then you subsequently break the standard model with the Higgs vector into that. The electric charge generator, let's say in the 5-bar representation, the fundamental representation of SU5 is the D quarks, the anti-D quarks, if you like, and the lepton doublet sits here, 0 and -1. That's the electric charge generator. And notice, if you have this kind of a generator, you need to do a 6-pi rotation because of this 1/3 to come back to the identity element, right? You have to do a 6-pi. So in the Dirac case, with the electron, you only had to do a 2-pi rotation. So that's an important difference. In other words, you might expect that the monopole now carries 3 units of Dirac charge because of the presence of these quarks. But these theories actually are very clever. So what you do is, basically, you can do a 2-pi rotation as if it was just the Dirac amount of rotation with this one. So you end up with this element, right? If I do a 2-pi rotation, I get essentially this thing, this element here. But now I can do a 2-pi over 3 rotation with the color generator. Remember, the unbroken symmetry is, of course, SU3 color cross U1 electromagnetism. So basically, what we are saying is that we do a 2-pi rotation here and the remaining rotation in SU3 space. It's an unbroken gauge symmetry. And so now we return to the identity element, because once you do this rotation, nothing happens here. They are this color singlet entry. So therefore, there's only this rotation. So what do we conclude? Well, we can come to the conclusion that the monopole carries only 1 unit of Dirac magnetic charge, but also carries color magnetic charge. So this is interesting, right? I mean, you might have naively thought 3 units of charge. Well, because of color, so long as the monopole carries some color magnetic charge, you end up with a monopole with 1 unit of Dirac charge. Now, of course, color magnetic charge, if color electric charge is confined, quarks are confined objects. So color magnetic charge, we expect, is screened, which is just as well beyond, let's say, QCD scale. In other words, beyond the QCD scale, you will see a monopole. So here's the monopole. This one, SU5 monopole, far away beyond lambda QCD to the -1, right? There are no free quarks, and therefore you don't need, there are only electrons and protons and so on. integer charge objects. So therefore, you don't need the monopole to carry 3 units of charge. But of course, if you take a quark around the center of this monopole below the QCD scale, shorter distances, like the SU5 distance is tiny, then of course free quarks exist here, and therefore the monopole should, to get the phase right and get the Dirac quantization condition correct, you must also assign some color magnetic charge to the monopole. So you get a very consistent picture. And what we conclude, therefore, is that all grand unified theories, the standard one, SU5, SO10, E6, all these theories must contain a magnetic monopole with 1 unit of Dirac magnetic charge, topologically stable, of course, and some color magnetic charge. So if this is really we're talking about SU, then it's kind of all sorts of structure here, and then at far away you see the magnetic field. Now, this what I have been saying is true also for SUSY or non-SUSY theories. I mean, supersymmetric grand unified theories have a lot of attractive features that I don't have to discuss today. In addition, one of them being, that gauge coupling of the standard model gauge coupling seem to unify if you invoke supersymmetry in the TeV region. But let us just think about non-SUSY SO10 for simplicity, if you like, because if you have non-supersymmetric SO10, gauge coupling unification typically requires you to introduce an intermediate scale. And that can introduce some really new features in the system, right? So if you have, for example, a group like SO10, more accurately spin 10, it's like this is the analog of SO3 and spin 2, which is SU2 or something, spin, right? So the unbroken symmetry is H again. And so monopoles appear when you map a two-sphere into the vacuum manifold G over H. And if G is simply connected, then this is like pi1 over H, which is similar to what we did earlier, where we said the equatorial circle maps into the U1, right? Here, of course, you map into H, the unbroken group. And in our case, that was SU3 cos U1. So there are magnetic monopoles. In other words, no matter how you start, as long as there is electric charge quantization, there will be magnetic monopoles. And that would make Dirac happy. The mass would depend on the symmetry breaking pattern. Now, what about cosmic strings? Well, for strings, you have to have you go around like this, right? You go around the string. There's a topologically stable string in the theory. You take a circle and far away, and this distance here, you should map it into a vacuum manifold. So the circle maps into the vacuum manifold. And this, if G is simply connected, actually becomes the pi 0 of H. It just checks if H has disconnected pieces. And this, it turns out for SO10, if you break it with tensor representation, is basically Z2 essentially. So there are topologically stable cosmic strings in SO10, provided you only break it using tensor. So no 16-dimensional, let's say, of SO10, Higgs gets a web or something. Then you will have that. Why is that interesting? It's important because it doesn't matter the way you break the symmetry. You can take your SO10, break it in any way, and people write down about n different chains. It doesn't matter how you do it, you will have strings. And how the fate of that string will, topologically stable string, and the fate of that string would depend on how you break it, how you decide to break it. So clearly, we should consider possibilities where the string can survive inflation, as an example, right? So this is the point. Intermediate scale monopoles and cosmic strings may survive inflation. So as an example, if I have a Party-Salam type theory, one of the earliest, perhaps the earliest model of electric charge quantization, not a grand unified theory in the sense that there are 3 gauge couplings, but it doesn't matter. The theory is still has electric charge quantization. And in fact, the lightest monopole carries 2 units of Dirac magnetic charge. So here again, you see, if you find a monopole, in the SU5 case, we found that the lightest monopole carried 1 unit of charge. This one is 2 units of magnetic charge. And why is that? Normally, we think of when people who work with this theory work with bifundamental representation. So there are quarks and leptons, and we know quarks carry 1/3 and 2/3 electric charge. Well, it turns out this theory, if you stare at it a little bit, actually the smallest charge could be E/6. In fact, to see that this monopole carries 2 units of charge, just look at it and say, what about a representation 1, 2, 1, for instance, which we don't see in nature, plus let's say its complex conjugate or something, vector-like particle. Well, it turns out that this carries a charge E/2, right? E/2. So therefore, the monopole must carry 2 units of charge. Actually, it turns out because of that, it also must carry some color magnetic charge because you have these 1/6 guys here. So E/6 is the charge, basic charge in this theory. In fact, these guys, I think Partey and Salam wrote a paper on things called preons, which they thought were even more elementary than quarks and leptons. I don't think this is a good way to think about it. These things they thought were preons, but that's not the way one has to think about. One should think of them as this elementary representation of this gauge group. So if this comes out of a string theory, you probably would expect similar objects in that. And in fact, Wen and Witten some time ago showed the presence of stringy states which carry fractional electric charge and were color singlets, right? Exotic states. In the beginning, some people thought that perhaps this would be a signal of string theory for some reasons, perhaps. But we see that no, these are present in ordinary 4-dimensional theories also. So suppose I take this breaking in non-SUSY, this would be a perfectly realistic model. And in fact, people work with that all the time. And now as I said earlier, any grand unified theory of the standard type must contain a monopole with 1 unit of charge. So now, but we said that Partey-Salam breaking here carries 2 units. So this must be 1 unit, right? There's no other monopole left. So this is 1 unit, this is 2 units. So this must happen. So in other words, now we have a situation where the 1 unit magnetic monopole is super heavy, heavier than the 2 unit charge, not possible in SU5. So this is what I meant. If you would measure the magnetic charge of a monopole, of a primordial one, presumably, this you can't make at CERN. If you a primordial monopole, suppose you would find one and the monopole carries 2 units of charge, then I would say we should really consider these guys. If it's 3 or something, it will be different, of course. But for 2, this would be a good way to think about it. This monopole, the first one is produced here because you look at pi1 of 422 and then 422, and then you'll find that this actually is non-trivial, even though because of the way it's embedded inside SO10. Of course, you can now look at E6, just as for completeness, of course, another realistic extension of the standard model. Well, E6, suppose I break it through this symmetry, SU3 cross SU3 cross SU3. That is sometimes called trinification. In case you see this monopole, actually, if this breaks to this, you will make a monopole with 3 units of charge. So therefore, the first unit must come from here. All theories must have this guy. Not all, I mean all grand unified theories. So this must be 1. And indeed, this is 1 unit of charge, much heavier than 3 units of charge. So if you find this chap here, then you know that you should go to this theory rather than this one. You can look at the more interesting structures and maybe you can see similar things in condensed matter. For instance, if you take this one and we saw that if you break it directly there, you get a monopole with charge 2. But of course, if you break it in this step here like this, then you make 2 monopoles, red and blue, and then these can combine and make this monopole that you expect. But of course, with these 2 guys and these flux tubes here, you can make all kinds of interesting objects called necklaces and so on, and maybe produce them in the primordial universe, depending on the symmetry breaking scale that you have with these theories. So this is an example of the trinification monopole, which can have substructures and things like that. Now, of course, these monopoles, if they are heavy clearly like SU5 or something, then of course they are produced in the early universe, we assume, we think, possibly, in which case the typical mechanism is called the Kibble mechanism, where symmetry G breaks to H, and these monopoles are essentially configurations of the Higgs field which are trapped where the 0 is trapped and the Higgs acquires a vacuum outside and goes to its vacuum expectation value. And the number density typically through the Kibble mechanism is very large. The number of monopoles, relative number to the photon, is about 10 to the minus 2. The number of baryons to photon is about 10 to the minus 9 or 10 to the minus 10. And of course, so this is very large, especially because the monopoles are now very heavy. So this is clearly highly unacceptable. And this is called the primordial monopole problem. Typically, we can use inflation to sort this thing out. And depending on the measurement, I won't have slides to show, depending on how you use inflation, the intermediate mass monopoles may survive inflation. In other words, when I have a symmetry breaking of this type, let's say, if I have a symmetry breaking of this type, then I can look, this is the gut scale, let's say, and this is the intermediate scale. And depending on what this intermediate scale is relative to the Hubble parameter during inflation, depending on how these two match, it could be that this phase transition, the second phase transition, doesn't experience 50 or 60 E-foldings, but a smaller number of E-foldings, in which case these monopoles may be present in our galaxy at an observable level. So this requires a discussion, a different type of discussion, which I won't have time to do here, but it's certainly an interesting topic. The bottom line is that we should not rule out this possibility of expecting some primordial monopoles with intermediate mass scales. Is a realistic scenario you can construct. What is the in searches and colliders? If this symmetry is broken, if these symmetries, which are not grand unified theories but have monopoles, as we have seen, they are not truly unified without making additional assumptions. But electric charge is quantized in these models, and therefore, if the mass is a few TeV or so, the monopoles may be accessible in high energy colliders. So if you can construct realistic models of these theories, then you can have monopoles which are observable. We wrote a paper, I guess Digesh and myself and Anil Thapa, on this kind of model where we showed that the symmetry breaking scale could be 10 TeV or so, in which case the monopole is about 100 TeV. We are not aware of any lighter monopole than this, which is topologically stable and so on. So and of course, one should remember when I said that there are objects with charge E/2, like because in the fundamental representation, let's say, of the 4-2-2 symmetry, one should also mention that because of the fractional charge E/6, the quark in that theory as an example, then of course these guys, an E/6 quark can combine with, let's say, a D bar quark to make a charge E/2 object or something, whatever, right? Plus E/6 and D bar could make an E/2. So as we think, right? So you could have mesons and baryons, in fact, carrying fractional charges. Exotic states in principle are predicted. And not just in these models, but even in string theoretic constructions and so on. Experimentalists are searching for monopoles at colliders and trying to use maybe the Schwinger, the magnetic analog of the Schwinger mechanism to produce monopoles and so on. The current limits are only about 100 GeV or so. So we are talking now about an improvement of a couple of orders of magnitude at least to get to be able to produce actual monopoles. Now, the next thing I want to say a few words about another kind of monopole that you could have, which was pointed out by Nambu some time ago, actually. He considered, remember the Tuhov-Polyakov ansatz used a triplet phi I field, right? The triplet which broke SU2 to U1 electromagnetism. Nambu considered the possibility of a configuration of the Higgs doublet which broke this SU2 left, which was a triplet under this SU2 left. This is a compact group. This is the non-compact part, right? So he said, suppose we consider the Higgs in this configuration. Usually we just take the Higgs to be this one, right? 1, 0 or something. In this case, you see, the monopole, because this is now, if you just think of this as SU2 left broken to U1 left or something, let's call it W, right? SU2 weak broken to U1 W. But this is W3, right? Which is a linear combination of Z and gamma. So therefore, with this configuration, for the Tuhov-Polyakov toy model, there was really the magnetic field of electromagnetism. But this one, of course, is U1W or U1 left. And therefore, this is a linear combination of Z and photon, right, flux. And you can compute the flux the magnetic charge is quantized like the Polyakov example, and the charge, because it's associated with SU2 left, it's 4 pi over G, where G is the SU2 gauge coupling, right? And this can be seen also here, where the Z flux is this thing and the electromagnetic flux is this one. And if you add the two up, you'll get 4 pi over G, basically. These are fluxes, right? These are flux, electromagnetic flux, and so on. Of course, if you have guts, then sine squared theta can be predicted. And that's how George Lazaridis and I found these objects, and then realized that Nambu already had considered those directly from SU2. We were motivated from a different point of view, which I can, and Nambu actually looked at it more carefully and pointed out that that because the monopole, this is a monopole which carries photon electromagnetic flux, when there's a Z tube attached to it, it basically ends up another anti-monopole here. And therefore this monopole, anti-monopole thing he called a dumbbell, and estimated that the mass is around in the few TeV region. So, but these topological structures, these structures, electroweak monopole, if you like, structures also appear in guts such as SU5 and SO10 and so on, it turns out. And as an example, if you're looking at SU5 models with Higgs in the 5 bar and 24 representation, then you notice that the SU2 triplet scalar in this one can get a Web, induced Web. And basically, so the new feature is, in contrast to the electroweak part, is that there's an additional triplet. So the monopole has an internal core in addition to what the Z core that Nambu had, and so on. So it's basically the same thing. And I don't think I need to say much more about it. Suppose, so let me show a couple more slides about the monopole thing, which is amusing. You have, so we are saying there's SU2 left, and there's U1Y, right? And this is the Dirac monopole, and this is the Nambu thing. Let's call it the Nambu monopole, right? Nambu monopole, right? So there are two kinds of monopole. Remember, this is not compact in the standard model, but for the sake of argument, imagine that there's a minimal hypercharge in the standard, given in the standard model. And so therefore the magnetic charge will be following Dirac will be this one, right? The minimal thing is G prime over 1/6 hypercharge, something. So you get this thing, right? G prime is the gauge coupling of U1Y. And now the Nambu monopole we have already seen has a magnetic charge, which is 2 pi over G over 2 n prime, right? We said it was 4 pi over G, remember, 4 pi over G, and then n prime just tells you the integer associated with it. So therefore, if I imagine a combination of the Dirac and the Nambu monopole, you take a conglomerate of n of these and n prime of the other ones, then you can add up the Z and the A charges of these guys, right? So now we know, you see, the Dirac monopole is a hypercharged monopole. So it carries a tube with it. It's semi-infinite tube, right? This one also we saw carries a semi-infinite Z tube. So therefore, these guys are not the monopoles with finite energy on their own. Of course, you can combine monopole and anti-monopole and make dumbbells. But we are looking for something else. We want to see whether, so Nambu considered these and made dumbbells with it, and with the Dirac, I can do a similar thing. But now I want to see if I can put these two together, the Nambu and the Dirac together, to make a monopole which doesn't have these tubes coming out. And if you do this little calculation, you find that basically n prime, if you have n prime equals 3n, the number of these 3 Nambu monopoles with one Dirac hypercharged monopole with 3 Nambu monopoles, you can put a configuration together where the flux tubes are all balanced out, essentially. And the electric charge, the magnetic charge, if you like, is 12 pi over En. So in other words, in figure, what have I done here? Well, this is a U1Y monopole. Yeah. And I've put a circle here to say that this is coming from some well-defined theory. It's not a point-like object like the original Dirac proposal is. It has a certain size, let's call it red, and then it combines with these 3 Nambu objects to make a configuration that essentially has no tubes coming out. So it's just at the end of the day, all that comes out is the electromagnetic flux. And so that is something you could try, right? But how these configurations actually worked, I don't know. No one has tried to put these configurations together. You could also imagine a situation, a colored U1Y Dirac monopole. And so, because you see, if you have SU3 cross SU2 cross U1, the U1 hypercharge knows about the center of SU3 and the center of SU2. So that should be taken into account. And you can have different possibilities and so on, which I don't need to discuss now. We can see it in the slide. In the remaining few minutes, maybe I have about 10 minutes left, 5 or 10 minutes. I should say a few words about cosmic strings from SO10. These have been known for some time. The reason people are interested in these strings in recent years is after the discovery of gravitational waves. It has been known for some time that if you have gauge strings, in theory, a gauge symmetry like SO10, this SO10 symmetry is broken to, it's a perfectly nice theory, it's a perfectly nice extension of the standard model, right? You break it at the gut scale, SU4 color cross SU, this is C there, SU4 cross SU2 cross SU2, and then you break it to there's a full stop here, and then mass per unit length of the string is this related to this intermediate scale, and we are assuming that this is much smaller than the Planck scale, of course, this thing, and the strength of the string gravity is determined by the dimensionless parameter and the string parameter G mu. So in the old days, people thought that if this was a gut scale, this would be like m over m Planck squared, right? And so delta rho over rho in the O, we thought before inflation finally took over, is that if m is of order 10 to the 16 GeV, and this is 10 to the 19 or so, this is of order 10 to the minus 5 or so, and then maybe this could be a source of density fluctuations. We don't use that, we don't think that's the way it goes anymore, because if they are gut scale strings, they are probably inflated away with the monopole, and so but intermediate scale strings can survive. So therefore, here is an example of monopole. At any given time, there are strings that go through the monopole, through the horizon size, and then some of these guys intersect, and they can make closed loops, and these closed loops then may oscillate and eventually collapse, and as they oscillate and collapse, they radiate gravity waves. And that's what people have been estimating and calculating and so on. So this actually is a perfectly, why is this interesting, by the way? This is not an academic exercise, this is a realistic model. Why? For instance, already this theory, before many, many years before neutrino masses were found, predicted that there are 16 chiral fields in the theory you should have. So the standard model is 15 plus 1. So this one is the right-handed neutrino, essentially, right? So the theory already had right-handed neutrinos. The symmetry was broken at this scale, intermediate scales, and the right-handed neutrinos get a mass. So the theory explains why the right-handed neutrinos don't have a Planck mass, right? In the standard model plus right-handed neutrino, you can write down a mass term m nu r, right? Or something like that, right? Majorana mass. And this m could be arbitrarily large. Well, because in the presence of this theory, you cannot write down this term. Just as in the standard model, you cannot write down a mass for the quarks and leptons, the charged leptons and the quarks, unless the gauge symmetry is broken, the electroweak symmetry is broken. You can't write down. In the electrodynamics of Schwinger and Feynman and Tomonaga, you can write down a term EL bar ER, right? The mass terms are written down. And you just assume that this is half an MeV. In the standard model, you say, no, you have to write this thing and then provide the Higgs mass. Similarly, in the standard model, you can write down a bare mass term for a right-handed neutrino field, but not in this theory. And which is just as well, because now the mass of the neutrinos is of order m Dirac square or something like that, divided by the right-handed neutrino mass. And this could be of order 0.01 or 1 electron volt or whatever you need, something like that, in that ballpark, right? For atmospheric. So these things predict non-zero neutrino masses. They can even do electric charges quantized. They can do leptogenesis because of the right thing. Many, many nice features that the standard model doesn't have. So this is a perfectly realistic theory. And they predict also these cosmic strings and topologically stable strings. And so therefore it's worth investigating the amount of gravity waves that are radiated and how to test these things. This is the older version, of course. It doesn't. So I should also mention maybe in words that you can also break this symmetry and produce an extra discrete symmetry here. Let's call it C. So, but if there's a C here, remember here you make monopoles when SO10 breaks, but because of this C, you also make a string. And this C is such that C takes Q to minus C is such, sorry, let me just write it. C is such that it takes Q to minus Q, the electric charge generator. So therefore the C is charge conjugation symmetry. So you make a string with charge, a string at this stage, but now when you break it, the charge conjugation symmetry is broken, and so you get a string connected to domain wall. So the string becomes a boundary of a domain wall. So at this level, there's a discrete symmetry C. When you break the dissymmetry, there's a domain wall. But the string C was connected to a string. So what it finally turns out, and this was shown a long time ago with Kibble and George and myself, that these are domain walls, strings bounded by domain, as are boundaries of domain walls. Now, of course, these are interesting topological structures. And I wanted to show a slide, which I don't have here, but perhaps I can. I wonder what are these things, and apparently these things, there's a paper like 2019 which people have shown that you can come up with, you can have phase transitions between phases, symmetry breaking phases, like we have, right? We have SO10 broken to 422 and then broken to 321. So there are these two, so you make string here and then wall here, and then you get a string wall system. Well, it turns out in superfluid helium 3, people have found these things. If you can tell me, I don't understand them probably yet, what they found, but basically they are saying these wall configurations have been found in condensed matter systems. So let me go back to the SO10 world again, which is here. And since I only have a couple of minutes left, here's one example. There's a paper with George Lazaridis and Rinku Maji and myself, which is a fairly recent paper, in which we sat down and said, okay, let's take a complete model, which is realistic, we think, with a Pechi-Quinn symmetry, axion symmetry. And this axion symmetry makes dark matter, of course. There's a Z2 symmetry here, unbroken, which makes strings and dark matter too. It has another dark matter candidate in the theory. And basically, for those, the reason I mentioned axion domain, the domain wall, is because there's always a axion physics always has strings wall system. And you have to make sure that if inflation is not invoked to resolve the domain wall problem, this symmetry is broken at some intermediate scale. And this is done by adding some new fermions. And basically, so what you get now is a theory where you started off just with cosmic strings, you thought you had that, but because of this domain wall thing, you end up with a new dark matter candidate. So it's almost like axions and WIMP-like dark matter, depending, except that this is not an ordinary WIMP, it can be very heavy, actually, super heavy things. And so the first breaking makes monopoles that can be inflated away, presumably, because these are much heavier than the Hubble parameter during inflation. The second breaking makes the intermediate scale cosmic strings, which can survive inflation, and even the monopoles may survive inflation. And then there's dark matter necessary just to model building. You see, you are just led to have such dark matter. It's WIMP-like, but it's, of course, it can be very heavy. In fact, it's not necessarily. So basically, as I showed a little cartoon-like figure here, you have these strings of various type at any given time, strings of various sizes, and then the universe keeps extending. You make larger loops larger open strings and so on. So you have to put it all together, and a number of years effort by a number of people have shown us how one can make such diagrams. And in fact, for this particular case, I suppose here is an example of what happens if the mass scale, depending on the symmetry, intermediate scale of the string, in some intermediate scale, 10 to the 11 and GeV. Of course, why is this interesting? It is interesting because these scales cannot be probed so easily at the Hadron Collider, even at the 100 TeV. We are talking of orders of magnitude more. So only primordial production of these objects can be useful. And we are seeing that in future colliders, these strings can be probed in these various proposed experiments and so on. You can think of some more interesting thing. If you have a symmetry breaking pattern of this type, that G breaks to H cross U1, which breaks to H, for instance, where H, and so that by definition, when you have this kind of a symmetry breaking, you would make a monopole. And then now when you break this one, the monopole has gone, right? Because it gets connected by the strings. This breaking makes a string. So now, because from G to H, you don't see any monopole or string, but in this intermediate scale breaking, you see the monopole and the string. And if depending on the mass scale of these monopoles and relative mass scale, these strings can be, we call it quasi-stable. In other words, if you have a long string, you cannot quantum mechanically break it. That those strings, those strings we can call metastable strings in the literature. So we've decided to study these quasi-stable strings, which basically can only be broken if the string is there and some primordial, the heavier monopoles, and re-enter the horizon and get connected to that. So now we have a system where you have closed strings, some open strings, and then also a system where there are strings of this type connected by monopole anti-monopole pair. And of course, these things also can be considered. And if you work that out, you find that lower frequency things are, you don't see in this region here less power than previously. So this thing also, such things also can, these are the stable strings here, right? And then these are the quasi-stable ones. And this thing can be distinguished from others. So here is an example of another system which can be tested in future colliders. By the same token, you could have a theory where you take into account inflation. You know, the strings undergo partial inflation and then re-enter the horizon and so on. And that can also change the picture a little bit. So I think this would be a good time to stop. Thank you very much.
On behalf of everyone here, I would like to thank you for an interesting presentation. Do you want to ask any question? Are there any questions? Yes, please write in the chat box, or you can also raise your hands and ask. Okay. Dear Hamza, please ask.
Hello, everybody. Thanks for the talk. Could you please say a few words about how to construct a relevant potential in this context that drives inflation?
So how to drive inflation?
I mean, could you comment on how to construct the relevant potential in this context? I mean, the potential that drives inflation. I mean.
Yeah, as you probably know, there are many models of inflation. For instance, to partially inflate this thing, you mean for this particular, how to keep some monopoles and or any general inflation, you mean?
So it's not inspired from this. I mean, there's
imagine you were breaking G. Suppose you had a U1 theory and you wanted to U1 B minus L or something, and you wanted to break it. Right, this symmetry, right? The simplest model I know, or probably the one, my favorite model is a supersymmetric version of this. And it's is a paper I wrote a long time ago with Dia Diwali and Bob Schaefer, in which you write a supersymmetric quartic inflation potential. And basically it is a potential where there's a scalar field which rolls down this minimum and does inflation, and then which reaches a certain point, it triggers a waterfall field which is sitting here to basically go into its minimum. So this phi field, which breaks B minus L, rolls into its minimum after inflation is completed. So this is the period of inflation driven by a singlet field, which is required by supersymmetry, and then it rolls down here. And at some point when inflation has come to an end, this U1 is still unbroken. So what happens now is that when it reaches this point, this is called the waterfall field. It can also be done in non-SUSY models, by the way. This waterfall field basically runs down to its minimum and breaks the symmetry. And you make cosmic strings after inflation. So therefore, this this horizon problem is solved. And this actually is a very nice theory because it's more like a superconductor. At high temperatures here, S is the temperature, let's say, compared to the temperature. The supersymmetry symmetry is at high temperature, symmetry is restored, so U1 is not broken. As you come down, as the field rolls down, eventually it sits at 0. As it comes, let's say 0, not quite because SUSY is broken slightly, 1 TeV or so. But suppose it comes down, this is like a temperature coming down. And as the temperature reaches a critical temperature, you enter the superconducting phase. So U1 symmetry is broken, you can make Cooper pairs, and so strings are produced. And then the field rolls down, you're at 0 temperature here. So that's the simplest. You can do it in a hybrid form, non-supersymmetric or supersymmetric. I can tell you the nice thing about such a theory is that delta T over T, okay, I can write it here. Delta T over T or delta rho over rho, delta T over T, in this theory is of order, the symmetry breaking scale of the thing you were talking about, let's say B minus L divided by M Planck squared to a good approximation. So, and this is of order 10 to the minus 5, as you can see, this is of order the gut scale. So this is, in my opinion, a very simple model of inflation, which is connected to some physics. It's not there some random scalar field driving inflation, but it's really, we are saying in this theory, inflation is connected with a phase transition, the symmetry breaking, let's say, of a U1. Why is that easy? Because the standard model, as you know, is a beautiful model because it's all local gauge symmetry. But it has a global accidental B minus L symmetry, right? And if you make it local, then you will need right-handed neutrinos to cancel anomalies. And now you have a local theory there, and you can do inflation with this one. And then the physics is nicely tied also to this one. So that's one example of doing inflation, but there are numerous other examples, of course, of inflation. Yeah. So one can write down those models and put them together with cosmic defects and so on. Yeah. This was an example. I just showed you how cosmic strings will survive inflation.
Thank you very much. It looks like we have 2 more questions. Yes, dear Wang, please ask your question.
Yes. Yeah, I enjoy your talk a lot. And so I wonder, do you have some kind of constraint on the string scale, say from cosmology or from some other things?
Okay, yeah. Yeah, I mean, I think there are some, depending on some assumptions, there are some constraints. You mean on the string scale?
Energy scale, on the string energy scale. This is mu you're talking about.
Yeah, that's right. Yeah, that is correct. Yeah, like you're saying, like G mu is of order, should be smaller than something, right? Because of from delta rho over rho, and that's right. Yeah. There are some constraints.
What is the constraint?
Pardon?
What is the value? What is the constraint?
I think the intermediate scale in the simplest thing, I think the intermediate scale should be less than or of order 10 to the 14 GeV or something. Rinku, is that correct? Something like that? Or 10 to the 13 GeV?
Okay.
Yeah, it's significantly smaller than the gut scale, right? So this is G mu 10 to the minus 10, or maybe it depends on the, I think if you don't do anything to it, let me show it, see if I can see it here. Where was that? If you have stable string, you see G mu 10 to the minus 10. So probably this is the, yeah, to 10 to the 5, 10 to the 14 or so GeV, that's right, something like that. Because otherwise, if you make it heavier, it will go ahead and go into the pulsar timing array bound, right? So that, yeah, roughly in that ballpark, about 10 to the 14 GeV, roughly, I think.
So in the electroweak symmetry breaking, do you have a string of that scale in the electroweak scale?
Oh, that's electroweak, yeah. That's the, you mean the Nambu type of thing, right?
Yeah.
Yeah, that is a low energy thing, of course. Yeah.
Yeah. Okay.
That is, yeah, that's right. Yeah.
Thank you.
Thank you.
Yeah.
Yes, we have another question by Rama Alasadeh. Yes, please ask.
Good evening, Sir Qaisar. My name is Rama. I am a second-year undergraduate student. Therefore, please excuse my question if it's a bit irrelevant to the argument. My question is, what's the difference between a magnetic monopole and electric charge or electron?
Yeah. Well, electron is an object that carries electric charge, which is conserved because, and there's Gauss's law, right? Yeah. So it's a source of electric fields. An electric charge is a source of electric field. A magnetic monopole is a source of magnetic charge, magnetic field, right? B field. That's the difference, right? An electric charge emits E fields, electric E fields, right? We have these E fields and B fields. As you know, there's an E field and a B field. In Maxwell's equation, normally we take div B to be 0, right? In Maxwell's equation, we have studied div E is equal to rho or something, right? The electric charge. And div B we normally put is equal to 0, but now we have a magnetic monopole, so we should put a J there or something, right? For the magnetic charge. And so we can't use B equals curl A so easily, because divergence of a curl vanishes unless there's some singularity. And in the example, I showed that you should use 2 vector potentials. So basically, electric charge emits electric E field, and one is a source of B field, right? That's the main difference. Yeah.
Thank you very much.
E field and electric charges exist in nature, but we haven't seen an isolated magnetic monopole. So that's the point. So in the theories that we have in the standard model and so on, the objects we put in the theory carry electric charges, right? And the dual, so there's the electromagnetic field, remember F mu nu, and so the electric components are EIs are like F0I, and the B fields are Fij, sort of related to Fij and so on. So that's the answer, I suppose.
Dear Professor, thank you very much for your answers. I have one small question. I wonder if it is possible to observe these monopoles or cosmic springs by the Event Horizon Telescope.
By the Event Horizon Telescope?
Yes, Event Horizon Shadow.
That is an interesting question, because you see, so here, if you look at this thing here, we said there's a cosmic string, right? And it's connected with this Z2. But this Z2 is a gauge symmetry. It came from SO10. So it's a gauge symmetry, right? So it's a very important symmetry. It's a part of, so therefore the black hole in principle carries quantum here, Z2 charge. So probably these strings and the quantum here can be detected using some interference experiments, yeah. Now, whether we can see it in the with the event, I don't know with the event, but there is a paper, there's a nice paper by Coleman. I don't know whether you're familiar with that. Are you? Coleman, Preskin, some years ago, Preskin and Wilczek, on which they take an arbitrary U1 and break it to Zn or something, right? So they say, look, we have a string. U1 is broken to Zn. Surprisingly, they were not familiar with this paper, which came before them with Kibble, this paper, 82, right? And this is a realistic model. And what's so interesting is this Z2 is connected also to dark matter. So if black holes also have dark matter around them, there could be some new physics. So I like your question, by the way, because I've been thinking about it, similar things myself. But whether this Event Horizon Telescope, I don't know. But the black hole carries this quantum here, and there are cosmic strings also present. And this is the reason for the stability of dark matter, even in non-SUSY model, even in this non-SUSY model. So whether there's some intimate connection between dark matter, cosmic strings, and black holes, and so on, is worth thinking about. There's also a paper by Maldacena, a preprint at least, a couple of 2-3 years old, in which he considered magnetic monopoles in the standard model and some possibility of Hawking, some change in the Hawking radiation rate and so on. So it's all, it could be, there could be some good deep connections there. It's a good question, actually. Yeah.
Thank you very much. Yes, we should check it. I would like to thank again our speaker for his very interesting and stimulating contribution. Now, let's continue with our last speaker. Okay, thank you very much again.
Hi, this is
yeah, it's my pleasure to introduce our last speaker. So I would like to welcome Steve Lamoreaux, professor of physics at Yale University, and who will speak on the laboratory research for the dark matter, squeeze vacuum state sensitivity, and achievement for a galactic halo axion search. And Steve Lamoreaux is a professor of physics at Yale University, and he received his PhD from the University of Washington, where he developed precision experimental techniques employing optical pump mercury and applied those techniques to the measurement of spatial isotropy and time reversal symmetry. He worked on the US-UK ultra cold neutron electric dipole moment experiment, EDM, led by the Professor Norman Ramsey, and he returned to the University of Washington, where he became a research associate professor and conducted research in ultra cold neutrons and precision laser spectroscopy, and proposed a new technique to measure the neutron EDM. He made the first high accuracy measurement of the Casimir force in 1996, and Steve became a laboratory fellow and worked on a quantum cryptography, quantum computing, and ultra-cold neutron physics, and led the dynamic materials weapon physics and team, which developed the novel techniques for stockpile stewardship. And then he joined the Yale Department of Physics in 2006. He presently is the principal investigator of haloscope at Yale sensitive to axion called dark matter. Now, I would like to hand over to you, Professor.
Well, thank you very much for the wonderful invitation, for the wonderful introduction, and thank you for the invitation also. And I hope everybody can hear me okay and see me.
Yes, everything's fine.
Good, okay. And I'm sitting in my lab right now where we actually built the instrument. It's in a different location, but this is actually the most convenient place for me to give talks. I was teaching quantum mechanics last semester, and so there's undergraduate quantum mechanics on the blackboard behind me. And I'll start my share screen now. And so I'm going to talk about the haloscope at Yale sensitive to axion cold dark matter. And looking for the axion is a little bit like looking for the proverbial needle in a haystack. And that was sort of the joke of the name. The graduate students came up with that. Also like to call this particle astrophysics in a can, because our detector really isn't much difference in size or shape than a ordinary soup can, you know, a little bit bigger, but not a lot. Our work has been published. It's available on the archive, and it was published in Nature just about a little over a year ago. And we've already said this, haystack sounds for haloscope at Yale, sensitive to axion cold dark matter. And haloscope means we're looking for dark matter in the galactic halo, and the dark matter we're looking for is in the form of axions. Now, we've heard a lot of talks about this, and you know, there's viewers of varying levels. So I will go through a little bit and not spend too much time on this, but there's many indications of dark matter in the universe. Generally, it's attributed to Fritz Zwicky, who in the Coma cluster in about 1933, noticed the rotation curves were really much faster than what could be calculated. And, you know, it's a little bit of a mystery, and I think maybe he proposed dark matter at that time. And dark matter means it's invisible matter. It means the light can penetrate through it easily. And it's the only way we can really detect its presence is through gravitation. So the initial idea, it comes from Zwicky based on astrophysical observations of galactic rotation curves. And I'm going to talk about today about quantum enhanced detection of dark matter using our haloscope. And before really going into the details of the experiment, I just thought I'd give a little bit of a background. You know, everything has to be quantum nowadays. We have quantum this, quantum that, but you know, this really works. Quantum enhanced detection. It doesn't necessarily make a big difference, but a factor of 2 doesn't sound like much. But LIGO, advanced LIGO, incorporated squeeze state detection in their detector, and you can see here that came along in about, you know, probably a couple of years ago. This is some arbitrary time scale of different running periods. But after they introduced the quantum enhanced detection via squeeze states, you can see their detection efficient rate went up by more than an order of, really roughly an order of magnitude. So a factor of 2 increase in sensitivity offered by the quantum enhanced detection, you know, it was really close to about 1.6 for them. But if you take 1.6 to the 3rd power, that's 4 times greater distances to which the gravitational wave detector is sensitive. And they incorporated other improvements too, you know, about a factor of 2 with other things. And so they got about an order of magnitude increase in detection sensitivity. Now the idea in LIGO and what we do, if you have quantum fluctuations, in the case of their laser interferometer, it's basically the shot noise associated with the coherent field, and you can squeeze that state. And so you have regions in your signal which are extra noisy and regions which are extra quiet. And so the trick is to do the squeezing, then look for the signal you want to detect in the relatively quiet region. And I'll explain a little bit about how this works. I just thought I'd give you a little picture before we started about where this talk is going and what it means. And just mention that advanced LIGO and our experiment here at Yale are really the first 2 experiments to use quantum enhanced detection in a data production experiment. And so back to the brief history of dark matter. You know, Zwicky wasn't the first to observe the irregularities, but you know, it goes back to Oort, and he also used the term dark matter, and this was really roughly the same time as Zwicky. Then in the 1970s, Vera Rubin did extraordinarily nice, precise measurements of rotation curves on a lot of different galaxies, and really sort of firmed it all up, and it's completely accepted as fact nowadays. And you know, there's lots of evidence. There's galactic structure, galactic formation, cosmic microwave background, anisotropy, gravitational lensing, the filamentary galaxy distributions. And its qualities are as plentiful, weakly interacting, and non-relativistic. At least some of it's non-relativistic. And you know, there's pictures like the bullet cluster. Nobody really fully understands this, but it looks like 2 galaxies collided. The dark matter kept going, and something galaxies scattered away. And this is something that's being analyzed to this day. My colleagues at Yale set up a new type of a detector, and they've actually detected a galaxy which is 99.9% dark matter. It's barely visible, but you can see that there's stars bound in this region. And if you look, this is sort of a picture of the whole universe, and you can see the galaxies tend to be distributed along these filamentary structures. And I don't know if you remember back in the 1980s, there was a huge program of people trying to use computers to calculate how this filamentary structure might have been caused due to the interactions of ordinary galaxies. And there really wasn't enough matter to do this. Well, the dark matter solves this problem too. And it gives a structure under which galaxies can form, and can form these filamentary structures in their distribution in the universe. So there's a lot of evidence for dark matter, and in particular cold dark matter. And this is a picture we've seen a few times already today. And of course, atoms, the ordinary matter that we're all made of, is only less than 5% of the mass of the universe. Dark matter turns out to be about 24%. And dark energy is, over 70%. This is very speculative. We've heard some speculation on that today and what this could be, but I'm not even going to talk about that now. That's far beyond my my skill level. But dark matter is something we can understand. It's roughly diffusely distributed in the universe. In the galaxy is about a few 100 times higher density than in absolute space, and on the average in the universe, maybe a few hundred times more dense than the galaxies. And we think we can, with the Earth-based system, perhaps detect this. There's been a lot of different experiments set up to look for dark matter. And one of them is whether or not there's something at the weak scale. And one problem with all this now is there's no signal at the LHC of any supersymmetric particles or any extraneous particles that might that could constitute the dark matter. Of course, there could be other particles, and you can speculate anything you want, any mass you want. And again, with all these things, for example, primordial black holes and machos and all this have been speculated upon. And in an earthbound detector, these things might have a different signature. If you have a resonator or something like that, these things could come in and hit it, cause a resonance, or some distribution of primordial black holes might account for a lot of the what we call dark matter in the universe. But primordial small black holes, if they're in abundant, we'd probably see their effects now and then on the Earth. But who really knows for sure? This is all speculation right now. Another question is, maybe this is all just a modification of gravity, and I think that this is probably pretty unlikely because we understand gravity quite well. And there was something called the Pioneer anomaly, where the Pioneer spacecraft was appeared to be speeding up at a rate higher than predicted by Newtonian dynamics, but in fact that turned out to be extra thrust due to heat from the spacecraft at a very, very low level, but nonetheless it was accounted for. And that's so I have a feeling that the modified gravity probably isn't a good explanation for all this, but then again, one has to have an open mind. Now, the other question is neutrinos, and they can't be standard model neutrinos. We know that their mass is on the order of 1 electron volt. And if you look at the Fermi energy of the 1 electron volt particle at the required density, the Fermi velocity is too high for it to be bound to the galaxy. So you can rule out standard model neutrinos right away with no problem. Unless one of the standard model neutrinos turned out to be very massive, but that's pretty unlikely. There could be heavy sterile neutrinos. There's been some speculation on this in high energy experiments, but that's a little more speculative. And the idea is that this is the wrong handedness, for the neutrinos interact with ordinary matter and they could have a higher mass. And a lot of experiments were built looking for these types of particles, these many ton cryogenic detectors. I can't even remember their names now, Xenon 100 and Lux and various Dama was one of them, and looking for heavy particles that come in and scatter and leave energy in a detector. And those experiments have pretty much run a course where, in order to, their sensitivity is now such that the coherent neutrino from the sun would overwhelm any type of a signal they could measure with one of those detectors. That, coupled with the fact that there's no LHC signal, questions return now to what something called light bosons. And in fact, what I'm going to talk about today is QCD axions, which are a well-motivated particle. And traditionally, these were a little bit ignored in the, as a serious contender for what dark matter might be. And even though this work was started in the 80s, even by the time I started working on this field in 2010, there was hardly any other experiments. Now this is the, this and other axion-like particles are the particle du jour, if you will, for what dark matter might be. And if you look just about every day, there's a new paper out on the archive about QCD or other axions and their role in regard to dark matter. So the field's kind of exploded. And you know, I've been working on this now for 12 years, and this really has changed with the realization that these big, large cryogenic detectors are really are not seeing a signal that they had hoped that they would see. And that, coupled with the lack of the LHC supersymmetric particles, kind of is forcing us to look in a different direction. I'm not saying those experiments should be stopped or anything like that, but I think the field's a little bit more open than anybody had realized even a few years ago. So the dark matter problem is in fact nearly invisible matter except by its gravitational effect. And it's gravitationally bound to galaxies. For us, that's about 10 to the minus 3 of the velocity of light. It can't be neutrinos. It's assumed to be particles. And the higher the mass of the particles, the higher the effective temperature of the particle. Not that that really matters that much, but it's kind of interesting to know what temperature of the particles we're looking at. And as I said, the main focus has been on WIMPs, weakly interactive massive particles, or supersymmetric particles. And there's another class of experiments, this electric dipole moment of the neutron and other particles. And that's really, that together with the LHC signal, the LHC not seeing a signal of a supersymmetric particles, is really kind of making the model, supersymmetric model, really not able to explain much in this field, because you know the particles are becoming so heavy that they end up not being relevant. The axion has been long known as a possible solution, and now is receiving renewed attention, and it actually has other applications in astrophysics. For example, stellar evolution, the axion could have implications depending on its mass. In fact, that's one way that the mass of the axion can be limited and constrained. So as I said, its velocity is about 10 to the minus 3 C. The effective temperature is about 6 times 10 to the minus 3 Kelvin per unit mass. And 20 microelectron volts implies a temperature of about 100 nanodegrees Kelvin. So the question is, you know, how did that dark matter get so cold? Well, it had to have been formed early enough in the universe that when the universe expanded, it ended up like the 4-degree Kelvin background radiation. Its energy was shifted down to a lower level. Since it doesn't interact with anything, it stays cold. And you know, as far as we know, the dark matter in regard to galaxies is about is really in a halo distribution with a local volume density about 0.3 GeV per cc. That's, you know, about a third of a proton per cc, and that's about 300,000 times the average in the universe. Now, the dark mass in galaxies does not follow the light. It's completely separate matter, and it seems to be having its own dynamics. And it's, you know, of course, it's going to be gravitationally affected by the galaxy itself, but that's a small fraction of the whole thing. And locally, the smallest length scale in which dark matter is clustered is in the Milky Way dwarf spheroidal galaxies, where the dark matter has a characteristic length scale of about 1 kiloparsec and slightly higher mass density. And this is ascertained by precision measurements. Well, let's shift now to the standard model of particle physics and ask what the dark matter might be, and in particular what relevance the axion might have. Well, the standard model of physics has been amazingly successful in the gauge sector, except for the overall phase of the quark mass matrix is physically meaningful. And there's many problems in the flavor sector. There's considerable success in correlating data, but at the expense of many phenomenological input parameters. And the axion solves one particular problem, and that is the lack of CP violation in the strong force, or in other words, CP charge and parity conjugation symmetry in the strong force. And the axion causes the strong force to be CP symmetric. Now, there's a whole history of adding particles to provide symmetry or conservation laws in fundamental interactions. The Higgs, the neutrino was introduced to allow energy and momentum conservation and beta decay. The photon, Einstein's photon, was introduced to conserve momentum in atom-light interactions. Basically, if you have a plane wave coming in and an atom emits a spherical wave, if you had a cell full of atoms interacting with the thermal field, the atoms would continue to increase in energy because the spherical waves wouldn't have any momentum kick. They're spherical, whereas the incoming light would be have a direction associated with it. And the photon model seems to be pretty good. And along those lines, we introduced the axion to give us CP symmetry in the strong force. Well, the strong CP problem, I'll tell you about that a little bit. It comes from the QCD Lagrangian. And we know that in ordinary electromagnetics, we can add a term to the Lagrangian of this form. And it doesn't cause any difference to the system because at least a term like this, but the forward divergence causes no observable effects in electrodynamics. So it's irrelevant. If you want to add it, you can, but it has no observable effect. On the other hand, if you it's different. If you try to add a similar term in quantum chromodynamics, the divergence no longer is zero. And you can add another term to the QCD Lagrangian of this form with theta's dimensionless parameter alpha s is a strong coupling constant, and the G mu nus are the gluon fields. And this is called the theta term. And based on experiments, theta is extremely small numbers, about 10 to the minus 10. And you say, well, if we want to have CP conservation standard model, we could just set this term equal to 0. That should be fine. But you can't do that because there's no CP violation in the standard model. If you try to calculate it, the calculation diverges at 14th order. And in fact, theta could be a dynamic variable. Péchet-Quinn mechanism is this, and it implies a new symmetry. And after they propose their model, Péchet and Quinn propose this, we'll check, and Weinberg both suggested that this suggests the existence of a new particle, which we'll check, called the axion, because it cleaned up the strong CP problem. The axion was a laundry detergent product that was popular back about that time. And the idea is that if you have unlike electromagnetism, if you imagine some virtual field around some particle, there's a chiral anomaly. Outgoing processes don't match the incoming processes. So that theta term becomes, and leads to an observable effect. And so if you introduce the axion, you can kill that effect by having interaction with the axion field at these vertices. And that solves the strong CP problem. So it wasn't too long after that that Sakivi and Abbott suggested that axions could be dark matter. And so we'll see in 1982, the axion came out in roughly early 1980s. So it's right away they came up with this idea, and they studied the production of the axions in the early universe. And in fact, there was a lot of uncertainty about the exact nature of the axion at that time. And in fact, this standard model axion was ruled out. And what they came up with was a light axion. There's nothing in the standard model that sets its mass. That's a completely experimental question, as far as we know. Maybe there's a theory that would predict it, but we don't know what that is yet. But there could be an invisible axion, which is a very, very low energy. And that axion, since it's doing stuff like canceling the neutron electric dipole moment, it has to have electromagnetic form factor, and that can couple to the electromagnetic field. And Sakivi worked out all the physics of that. And the axion is has an electromagnetic form factor, and it can actually decay into 2 photons. And this is a very, very, very slow process. But you can speed that up if you apply a strong static field. The axion can scatter from that field and produce a photon and conserve energy and momentum by giving up some momentum to the static field. And that enhances the rate tremendously. So that suggests an experiment that you apply a strong magnetic field and you can convert axions to photons and perhaps detect the photons. And this is equivalent to a Primakov process, for example, when the pi0 decays anomalously fast in the electric field of a nucleus. And this is a similar situation. So you can work out, based on parameters in the standard model, what introducing between the mass, axion mass and the Peche wind scale is roughly this. It's 10 to the 12 GeV, 5.7 times 10 to minus 7 micro EV over FA. And the photon axion coupling is given here. And so you can relate the coupling directly to the mass as usual in these types of situations. And it turns out that the range of axions could be anything from 10 to the 7 EV to 10 to minus 12 EV. And this is just some a parameter space on possible axion masses. And there's 2 models of what the axion, how it could interact with the standard model. One is based mostly on quark interactions, and one is both leptonic and quark interactions. And there's the KSVZ and DFSC models. Anyway, they predict values for F alpha and G. So there's 2 lines possible. They're about a factor of 3 difference in these. The KSVZ is about a factor of 3 larger G axion gamma. And this is a plot of possible coupling constants versus axion masses based on different processes. For example, if the axion had a mass of 10 to the 7 EV, coupling constant of 10 to the minus 6 inverse GeV, there have been an anomalous cooling rate of SN 1987A, and other supernovas. You also get Big Bang nucleosynthesis and X-ray emissions from the sun and stars, and so these are all observational. CAST is is a experiment that looks at for axions made at the sun. There's a big magnetic field and it's a telescope basically. And if axions are coming from the sun, it would convert in the magnetic field and form a beam of X-rays or, photons. These aren't really X-rays anymore, but, and so you can see there's been a big swath of this region cut out, but there's a big swath that hasn't really been investigated yet. And our experiment right here is haystack. And the way the haystack experiment works, if the axion has some fixed given mass, when it converts to a photon, it's going to have an exact precise frequency. So it's going to be a very, very sharp frequency somewhere in this parameter range. And so in that regard, it's going to be very, very sharp signal pointing down in this two-dimensional plot when we see it. Now here's our current experimental limit. There was an early experiment called ADMX, which is still running, which is looking at lower frequencies, so they have a little bit broader frequency width, but nobody knows where this is. So we're gonna have to scan this whole parameter space until we find this sharp, really very, very narrow radio frequency signal. And these are proposed experiments and what they hope for their sensitivity. So these theoretical lines are sort of hopeful levels of sensitivity. And you can see there's hope over the next few years that, decades perhaps, that all this will be filled in. But for the time being, you can compare that slide to what was earlier. And for the experiments that actually achieve a region of good sensitivity, there's really only haystack and ADMX, and the region of interest here kind of covered up stuff here. But these our experiment CAP is one that's being begun in Korea. That's actually had a very, very limited data set, and that's coming online. But right now, there's only 3 experiments that really are running that can hit the level of sensitivity that are needed to address whether or not the axion exists. And as again, this is a hope for the future that this is all going to get filled in. There's a lot of different experiments being proposed, some for very low energy. And there's a different motivations for where you should look for this. And for a while, it was right around 20, 25 microelectron volts. That corresponds to a frequency of about 5 gigahertz. That's where we were running originally, and we actually operated there basically because that's the Wi-Fi frequency, so you can get 5 gigahertz components fairly easily. But now the feeling is it's probably going to be a little bit higher energy, maybe 100 microelectron volts. So there's a push to go to higher and higher energy. And again, this is a plot of different experiments and what people hope to get in the near future. So these are the Sakivi equations is copied over again, and the main thing we look at is this term right here, and this term in the electromagnetic coupling of the axion gives an effective current, and that creates an effective magnetic field. And so if there's an axion, you have a strong magnetic field, the axion converts, you'll get a magnetic field that's toroidal like this. And the axion density is so high that the field is classical. We can just think of this completely as a classical field. And it has a coherence length, and I'll talk a bit more about that in a moment here. And basically, you want to capture that magnetic field, convert it into electrical field, which in a sense is oscillating. You put this in an electromagnetic cavity, this oscillating magnetic field will create an oscillating electric field. And if it's a resonant cavity, then we can pick off a signal and thereby detect the presence of axions. And the basic experiment then is we have a magnet, produces a magnetic field. Axions penetrate this from any direction, comes from anywhere. They convert in the magnetic field. the cavity builds up an energy density, and we can tap that off, send it to an amplifier, then send it to a data analysis system. An axion would show up as a little peak in a noise signal. So this is very, very narrow. It's only one frequency, assuming there's one axion, which as far as we know in the standard model, there's only one. Other models, there's in string theories, there's hundreds of different axions, but if it's the standard model axion, it's going to be at one single frequency, and we don't know where that is. And it's a very, very narrow line. The intrinsic line width is about 10 to the minus 6. That means it has a Q of about 1 million. And the signal that we observe, the power, is going to be the coupling constant squared times the density of axions, the number density of axions, times the magnetic field squared, times the volume of the cavity, times this C factor, which gives the overlap of the electromagnetic mode with the axion, and the Q of the cavity. And it turns out that 10 to the minus 24 watts is an interesting level of power. And that's an extremely small amount of power. If you imagine lighting a match on the surface of the Earth and viewing it on the moon, that distance, lunar to Earth distance, amount of light hitting your pupil, viewing that match is 10 to the minus 24 watts. So it's a very, very, very small signal. In fact, what we have with this experiment is the most sensitive radio receiver ever built. And again, this is where we're going to be looking. And, this is ADMX was an earlier experiment. Originally, we called our experiment ADMX HF, but we changed it to Haystack to reduce confusion between the two experiments. And this is the same picture again. We have the cavity, the magnetic field, and there's some cavity line width. And that's always going to be much narrower than the axion. Remember, I told the axion line width is very, very narrow. It's about, the Q is about 10 to the 6. It's hard to get a cavity with Q better than about 10 to the 4 or 10 to the 5. With the problem being, we can't have a dielectric in the cavity. It has to be a special type of cavity to interact with TEM010 mode. And those aren't that high Q of cavity modes. If you put a dielectric in the cavity, all the energy ends up in the dielectric, and that really spoils the signal. So it has to be an all metal cavity. And I'm not going to go through this too much, but
sorry, sir, last 15 minutes.
So there'd be a peak in the radio signal. So this is the response. This is the response of the radio receiver, and the axion would be a little sharp peak in the noise signal that we see come out of the radio. So if you imagined static coming out of your radio, and then you heard a very sharp tone, that would be equivalent to what the axion would be, a very sharp frequency and presence of a lot of noise. And it turns out that the if it was a random uncorrelated field, the axion would be very broad. It'd be much broader than the cavity, but the axion actually has a pretty long coherence length, and it's about 100 meters. And that means that the axion Q for its interaction with the cavity is really very sharp, like I said before. Now, the signal noise that we can expect from the system is given by the Dickey radiometer equation, and we're working at 5 gigahertz, so that says the effective temperature is 240 milledegrees Kelvin. That means we have to have our system at a lower temperature than that. And I'm going to skip that. The way we detect the signal, if we use an ordinary amplifier, there's just too much noise, you can't do it. And so what we use is something called a parametric amplifier. And there's a lot of examples of this. One is if you ever see a child on a swing, you either move your legs in and out, or you stand up and down, you can make it pump energy into a swing. If you oscillate the plates of a capacitor, you can make a parametric amplifier with an electronic circuit. There's something called the dynamical Casimir effect. If you oscillate one of the plates of a Casimir experiment, you actually promote some of the photons, the 0-point photons, into real photons. And we also see that in black hole evaporation. These are parametric fluctuations, the surface of a black hole. There's nothing fixing it. There's a shock wave, so that can fluctuate around a little bit. Well, those fluctuations cause parametric oscillations of the vacuum, and the photons in a black hole can evaporate. And what we have is something called a Josephson parametric amplifier. What it is a string of Josephson junctions, and it's there's an oscillating magnetic field applied to this at twice the frequency we want to amplify. Just like in a swing, you pump it at twice the swing frequency. You lower your center of mass at the center, you raise your center of mass at the top. Well, in this case, you modulate the flux across the Josephson junction that changes its impedance, and you can affect a amplification through that, which is almost effectively noiseless. The next thing we use is something called squeeze states. If you look at the XP of a harmonic oscillator in the zero state, this little nice sphere, well, it turns out that you can make the minimum uncertainty state of a harmonic oscillator in different ways. You can compress the momentum dispersion and increase the Y momentum dispersion. In fact, the Heisenberg uncertainty regulation, the momentum commutator, we can expand either one of these. That's still equal to the commutator of X and P, and that's equal to IH bar. Well, these are dimensionless units. And so we're free to squeeze one direction, expand the other in the 0 point motion of an oscillator. And also we can displace that oscillator. We can do an amplification. And you can do it in different directions. You can squeeze in different directions and expand in different directions. In fact, you can generalize the lowering operator by this same parameterization I have up on the commutator here. And the coherent states were actually really first discussed in 1930 by Schrodinger. He's trying to make classical particles of plane wave states. So the ideas behind all this go back a very, very long time. And so if you have an original state that looks something like this, you can squeeze it. And if you have just noise, that would be this band here. You squeeze it, then you have regions where in the phase where this is the momentum and this is the position, say. We squeeze in the X direction, so the momentum part has extra low noise and the position part has less noise. And you can do that with, you can add a signal to it, and you can squeeze and displace. And so these correspond to different directions of squeezing relative to the displacements relative to the squeezing direction. And this was an experiment that we designed on my blackboard in my office back in May 26, 2010. So it's just almost the 12th anniversary when I began working on this project. And the overall scheme is, it's just pretty much like I showed. There's the electromagnetic cavity, a magnet. There's a dilution refrigerator, and the amplifier has to be in a magnetically enclosed region. Otherwise, the fields would wreck the Josephson parametric amplifier. Here are some pictures of the experiment. The first version, where this was phase 1, we didn't have the squeeze state at that point. Later on, we put in the squeeze state. In order to control the magnetic field at the location of the Josephson parametric amplifier, we have these persistent coils that cancel out the magnetic field from the big magnet. And the shielding factor of all this is about 1 billion. And we had a few mistakes. One time the magnet quenched and this copper shield actually expanded. This is Lenz's law. This would be a nice picture for teaching undergraduate physics. And the forces actually distorted the experiment. This was the mixing chamber plate that's supposed to be flat. We were able to repair that and get it back online. And now we have this squeeze state system in here. Basically what that is we squeeze electromagnetic, the electromagnetic field in the propagation direction. We bounce that off the cavity and then amplify this by Josephson parametric amplifier. And it bounces off the cavity because the cavity is highly detuned. And what that does is it increases the bandwidth and increases the rate at which we can scan the experiment, and without a loss in sensitivity. And we have a new dilution refrigerator. Again, this is the way it works. We have the vacuum state. We squeeze it. We reflect it from the cavity, and we have the squeeze state plus the cavity state. Then we can amplify in the quadrature direction and reduce the overall noise of the system. And here's some pictures of some of the components. And this was a test cavity. And this is our noise signal with the squeezing off. When the squeezing turns on, the noise goes up and the outside of the region we're interested in, and it goes down where we're interested. And it's a big job transferring from the lab in Colorado. This is actually Conrad Lehnert and his students and postdocs built this. They brought it to Yale, and we incorporated it into our experiment. And it's not so simple, but we got it to work. And here's some more pictures of it. And here's the microwave cavity itself. We changed the frequency by rotating this off-center rod. So as this rotates, this rod gets closer to the wall. And by doing so, it changes the frequency. And there's a piezoelectric motor, which turns this rod very, very slowly in very, very small steps. And there's something called the hot rod problem. If you ever, in the United States, there's people like to make their cars extra powerful. It's called hot rodding. Well, in our case, the hot rod problem is that this rod doesn't cool very well, and it's stuck at about 200 milledegrees Kelvin. And that's just a temperature we don't want to, where we have to be below in order to get rid of the background photon noise. So this is an extra noise source. We're working on solving that right now, but it's extremely tricky because this coupling the outside has to be through insulators. Otherwise, it ruins the Q of the cavity. It couples the conversion energy outside of the cavity and ruins the experiment. Well, anyway, I've already showed some pictures of the magnetic shielding and all that, and this is just another picture of the new experiment. Here's all of us working on it. Kelly Backus graduated about a year ago, and this is looking up the bottom of it. All these cryogenic shields have to be extremely well aligned, otherwise they touch, cause heat leaks. And the resonant frequency of the Josephson parametric amplifier depends on magnetic field. And you can see our magnetic shielding works pretty well. This shift in this curve barely changes when the magnetic field's applied. And what we find in our experiment is we get about 4 dB reduction in the variance of the signal. And that gives us an increase of scan rate of about a factor of 2. And we think we can do better. And here's Kelly adding the squeeze state really made the microwaves system a lot more complicated, and but it works and it's worth it. And this is again just another picture of what goes on. We have the vacuum state. We squeeze it in one direction. The cavity, if there's an axion, displaces that. Then we can amplify it in the direction that is orthogonal to the extra noise and recover a signal which has relatively reduced noise compared to a straight linear amplifier. The way this experiment works, we just take data over a long time. We take just measure the voltage out of the amplifier and just do recordings of that, do a Fourier transform. So we have a noise power as a function of frequency. This is a Fourier transform of the noise. And then if there's an axion, it would show up as a little peak somewhere in the signal. So we just do this over and over and over again. We just tune slowly. And if there's a candidate, we have a procedure in place for doing a rescan. And the systematics are okay. If we see a signal, it's easy to get rid of. We just have to turn off the magnetic field and the axion conversion goes away. And so we don't have to blind the data or anything like that. Yet we're still planning on doing that because we want to make sure our analysis is working properly. We want to compare our analyses of different groups, our collaborators, and our groups do the analysis, and we all want to make sure the whole thing is the whole analysis is consistent between groups. And we do this procedure of looking for the peaks, then throwing them away, taking more data on those peaks. In order to really get the final limit, we have to we use Bayesian analysis. And this business of looking for the peak in the signal is equivalent to what's called the alarm problem. And it goes back a long time when the 1950s, when radar was waiting for Soviet bombers to come over the pole and you get a radar signal back. You have to decide whether or not the radar signal is real or not. And this Bayesian analysis was developed for that. And it's in several books on statistical theory of communications from that period. So.
Last 5 minutes.
What's that? 5 minutes, yeah. So this is our data run, and we put that on a graph, and you can see where our this data set comes into is reaching the KSDZ line. And we've finished our squeeze state enhanced run. We excluded to about 1.4 times the KSDZ limit over the covered range. And we showed that the quantum detection can improve haloscopes. And here's a picture of my collaborators. And this work was supported by the National Science Foundation, Simons Foundation, the Wright Laboratory at Yale, and the Joint Institute of Laboratory Astrophysics, and Yale University and the University of California. And it was very difficult running this experiment through the COVID time, but we were able to do it and get the data set I showed you here. And with that, that's the end of my presentation. Thank you for your attention.
On behalf of everyone here, I would like to thank you for a most interesting presentation. And let's look at if there are some questions. Do you have any questions? Yes, you can write in the chat box and I can read, or if you want, you can ask. Yes, Professor Robert Mann, with one question. Yes, please go.
Yes, hi, thanks for a very interesting talk. You may have said this and I missed it, but suppose the experiment sees no evidence for axions. What do we learn about the axion then, or the whole idea?
Yeah, well, that's
like
interesting.
What's the best, tightest bound you can get on whatever?
Yeah, the question is these two models for what the axion mass and interaction should be, if that was completely wrong, then we would never see it. But it can't be that wrong. It has, the axion does something. If it's going to do something in the standard model, it has to have some mass, and it's not going to be wildly different from those predictions. But if we don't see it, it's we're both detecting the axion and showing it's dark matter, so it's a double detection sort of thing. And so it's an interesting problem in physics. The presence of it would verify the existence of the axion and verify it as the dark matter. So there's a double consequence of seeing the radio signal we're looking for. And if we don't see it, we actually don't learn that much. We just learn where it isn't. We learn that its coupling constant maybe is too low. And
don't you get a bound on that, or a range?
Yeah, that's right. Yeah, you get a range from where the bottom of it is. But you have to make some assumption that that dark matter is, well, that's what it would be there, but you don't really know that. So it's a strange problem. What if the dark matter was something else entirely? And what if the axion was real? They're not mutually inclusive. They're not mutually exclusive, but they're not mutually inclusive either. So you can't really use this as a constraint on the existence of the axion, because we don't really know that it had been produced in the Big Bang. Now, if we assume it had, if all of our QCD theory is correct, and we have some model of the universe early, and we show that these things could be produced, then it's a question of how confident are you in that theory. And, so it'd be a double discovery to see it. And if you don't see it, then what you conclude depends on what you put into your assumptions, I guess I would say.
Well, that's kind of what I'm getting at. What's the best? Something's got to be wrong with some of the assumptions. If you see nothing.
Yeah, that's right. So
and I'm old enough to remember when everybody promised we'd see supersymmetry at the LHC, and we didn't. So.
Yeah. Well, I remember when I was promised that the proton was going to decay. I was encouraged not to go into theoretical.
Too.
I was told not to go into theoretical physics. This is all solved in a couple of years. It'll all be finished. So don't go into theoretical physics. That was back in 1980. Yeah. And of course, the proton didn't decay. So, and this is a little bit different situation because there's no firm evidence that the axion exists. It's all inferential, but there's a lot of evidence that it does. The QCD theta parameter being small is very important, and it's just time to look for evidence, and something is going to happen somewhere that's probably might show it. And until that happens, it's all very speculative. And right now, this is, I won't say it's the best we can do, but the WIMP, the heavy supersymmetric particles as an explanation of dark matter is kind of ruled out. The question is, where do you look next? And these are, pretty simple experiments, pretty cheap. Maybe, it's $1 million every 3 years. That's pretty much low cost. And, it's the whole collaboration.
Well, it's cheaper than the LHC, that's for sure.
Oh, yeah, that's right. So,
Yeah, I'm not saying it's not worthwhile, but I mean, I think this should be at least thought of in more detail and discussed if nothing is seen. I mean, I think that's quite conceivable.
Oh, yeah.
With
so,
all due respect to the ingenuity of the experiment. That's all I'm saying.
Yeah. Well, I leave that, I'm really an experimentalist, so I leave that the theorists have to decide what they wanted to conclude from it. I'm taking the data, and there's a lot of papers being written on axions. There's about, there's several a week coming out. It goes in spurts, but for a while there, we were getting 3 and 4 a day. And so there's a lot of speculation and discussion, and, something, some data that's maybe of limited use is better than no data at all in the end. So.
Yeah. Okay. Thank you.
Yes, thank you very much for this fruitful discussion. Yes, have you got any question? Okay, I would like to thank again our speaker for his very interesting talk and contribution of all the participants. So let me conclude by thanking all of you for your time and valuable talks. Okay, now please, Professor Ekrem Hoca.
Okay, thank you so much, dear Ergün. I'd like to thank the chairs of this afternoon session, dear Demir and Ergün. So that concludes the first day of our symposium. So we will be meeting tomorrow at the scheduled time.
Yes, thank you very much. See you tomorrow.
Today, it was very beautiful day for me. I am happy to see you here. We have listened very nice talk today. Thank you very much for your nice talks and your participants. See you tomorrow. Goodbye.
Bye-bye. See you tomorrow, everyone.
Bye-bye. See you tomorrow. Good night.
See you tomorrow. Bye-bye.